All right. So hello guys. Let us begin with a very simple scenario. Okay. So we have some scenario over here. The scenario looks like this. So let us take two people. So we have Ruchika in the chat and we have Akshat. Right. So let us say that we have two people, Ruchika and Akshat. Right. Now both of these people, Ruchika and Akshat, they created an algorithm for sorting. Right. They created a sorting algorithm, and the challenge is that whoever's sorting algorithm runs faster, that person will win the contest. Okay, and they will get some prize. Is that fine? Cool. Now, Ruchika and Akshit both test their program, and here are the results. Right. So Ruchika uses an algorithm called Ruchika sort, and we benchmark that algorithm, and it turns out that Ruchika sort takes 5 seconds to run. Okay. On the other hand, Akshit uses his own algorithm. So Akshit's algorithm, and Akshit's algorithm takes around 10 seconds or 20 seconds to run. Okay, cool. So who do you think wins in this particular contest? Who do you think has a better algorithm, has a faster algorithm? Is Ruchika's sort better or is Akshit's sort better? Well, it seems like Ruchika is the winner over here, right? It seems like Ruchika is the winner over here because her algorithm runs in only 5 seconds, whereas Akshit's algorithm takes 20 seconds. But Akshit says, wait. This is not fair, right? Ruchika was running her algorithm on a top-of-the-line MacBook Pro, right? Ruchika was running her algorithm on a top-of-the-line MacBook Pro, whereas Akshit was running his algorithm on his mobile phone, right? So it is obvious that, hey, Ruchika's algorithm will run a little faster because she was running it on a better computer. So we said, okay, that's fair enough. Let us try to run both the algorithms on the same MacBook Pro. Okay. So Ruchika's algorithm takes 5 seconds once again, but Akshit's algorithm now takes only 1 second. Yes. So when we ran Akshit's algorithm on the MacBook Pro, it took only 1 second. Now, who is the winner? Is it Ruchika or is it Akshit? Well, now that we have standardized the underlying hardware, now it makes sense that Akshit is the winner, right? But we are not done yet. We were trying to declare Akshit as the winner, but Ruchika said once again that, hey, let's just wait a second. We are trying to run this algorithm to sort 1,000 different items. Okay, we were sorting 1,000 different items using this algorithm. Ruchika said that instead of sorting 1,000 elements, if you instead sorted 1 million elements, right? If you instead sorted 1 million items, then Ruchika claims that her algorithm will run faster. Right? Now that sounds a little weird. For 1,000 items, Ruchika's algorithm is slower, but for 1 million items, Ruchika's algorithm will be faster. But that totally happens, right? Depending on the complexity of that algorithm, that can totally happen. So I hope that you can understand from this particular scenario that analyzing the time complexities of different algorithms is not that simple, right? We cannot simply measure the time. We have to do a lot more careful analysis. Is that clear? So we have to do some sort of a careful analysis. All right. So here are the things that we need. So we want a way that takes the following into account. So number one, it standardizes the underlying hardware, right? So we want to make sure that whenever we are testing two algorithms, they are running kind of on the same hardware. Or basically what we want to say is running on a faster computer should not change who the winner is. Does that make sense? Yes. So just because some algorithm is running on a slow computer, some algorithm is running on a faster computer, that should not change who the winner is. Right? The second requirement would be programming style. It could be that Ruchika is a very, very good coder and she knows how to perform that coding, how to optimize her program a lot. Right? Whereas it could be that Akshit is kind of a beginner and Akshit does not know how to optimize the cache maybe and how to write the program so that it is very, very efficient, right? So we have to make sure that while comparing algorithms, we do not compare the programming styles, we do not compare the underlying hardware. And finally, we have to make sure that we are testing with large enough data, large enough input, right? So just because for a smaller set of inputs, Ruchika's algorithm ran slower, that does not mean that Ruchika's algorithm is in fact slower. Right? We have to test it for a very, very large input. So we are trying to come up with a way of analyzing algorithms that satisfies all these three criteria. Is that clear? And the way we do that is by talking about, instead of talking about the time it took to execute, we instead talk about the rate of growth of the algorithm, right? Or we talk about the time complexity of the algorithm. Is that clear, guys? Yes? Perfect. So let us see how we model this in a mathematical manner. Okay. So let us take a few more examples before we move on to the mathematical definition. Right. Let us suppose that we have two functions. Okay. We have two functions. One of the functions is, let us suppose, log x. Log x. So what does the graph of log x look like? Can someone tell me what the graph of log x looks like? So the graph of log x looks something like this, right? Log of 0 is not defined. Log of 1 is 0. And as x increases, the value of log x increases monotonically, right? But it increases slowly. This is the graph of log x. Let us look at another function. Let us look at, say, x equals to 10. Right? So what will the graph of x equals to 10 look like? Well, it will look like something like this. It will look something like this. Yes? So what do you think? Which function is larger? Which function looks larger? Is x equal to 10 larger than log x? Does that make sense? Well, on the graph, we can see that it is certainly above log x, but that is not perfectly right. Okay. So the thing is that as we keep on increasing the value of x, right? As we keep on increasing the value of x, there will be a certain point. There will be a certain point which will be, let's say, x is around, let's say, 2000. After which this log x line, the graph of log x will eventually cross the graph of x equals to 10. Oh, sorry, not x equals to 10, y equals to 10, my bad. Y equals to 10, y equals to 10, right? Does that make sense, guys? So eventually what will happen is the graph of y equals to 10, this graph will become less than the graph of y equals to log x. Yes? Now, why does that happen? Why does that happen? That happens because we are talking about the rate of growth of two functions, right? This particular function, y equals to 10, this function does not grow at all. 10 is a constant, right? Is everyone aware what a constant is? Y equals to 10, in that 10 is a constant. Whereas when y equals to log x, this log x, this is not a constant. It will grow with increasing values of x. It will continue growing and growing, right? So when we are comparing the time complexities of different algorithms, we do not want to compare the runtime, the time it took for one particular instance. We want to compare how the function grows. All right. Let us look at one more example. Let us suppose that we have this graph once again. So we have log x that looks like this. And we have y equals to x by 100. Right? So y equals to x by 100 will look something like this. Y equals to x by 100. Right? So now which one do you think is the faster algorithm? Which algorithm do you think is better? Well, currently in this particular part, till this particular point, y equals to x by 100, this was larger than log x, right? However, from this point onwards, log x was actually greater than y equals to x by 100. Yes. So should we say that log x is slower? Log x takes more time. Should we say that? Well, not necessarily. If we keep on increasing the value of x, what we will encounter is that log x grows much more slowly, whereas the graph of y equals to x by 100, that eventually crosses the line of log x. All right. So eventually for very large x, we will always find that x by 100 will be larger than log x. Now the challenge here is that we have to choose sufficiently large x, right? We can't talk about small values. We have to choose a large enough value of x. Does that make sense? Right? Yes, cool. Now let us ask a couple more questions. If I take this x equals to 100 graphs, right? And if I compare it with log x, instead of comparing this x equals to 100 or y equals to x by 100 graph, if I multiply this with some particular constant, right? If I say that instead of comparing x by 100 versus log x, what if I compare 1000 times x by 100, right? Times x by 100 versus log x. Is that going to change which algorithm is faster or which algorithm is slow? Yes or no? By multiplying a particular function by some amount, should that change if an algorithm is faster or slower? Well, that should not change the winner of the algorithms, right? Why should that not change? Because this is like running it. This is like running the program on faster hardware, right? Multiplying this value x by 100 by a constant amount 1000. This is like running that same program on a faster hardware. So we already wanted a method. We want a method in which change in hardware does not really affect our winner, right? Irrespective of which hardware we run the program on, the winner remains the same. So this should not affect the value. Similarly, if instead of multiplying with a constant, if I add a constant, right? If I add a constant, this also should not change the winner of my contest, right? This should not change the ordering of my algorithms. Is that clear? And the way we talk about this mathematically, is called the asymptotic notation, right? Now you will come across a lot of different asymptotic notations. The most common being the big O notation, designated by something like O of Fn, right? Then there is the omega notation. This is designated by this symbol, and we have the theta notation, which is this, right? So we will be talking about in details about what each of these different notations and each of these different methods mean. Is that clear? Any doubts till now? Repeat the hardware part. Okay. So basically, what I'm saying is, let us say that we have two algorithms, A and B, right? Let's say that A took T seconds to complete, while B took M seconds to complete, right? Now, if I measure which algorithm is better based on the time it took to complete, that measurement is not a very good measurement. Why? Because it could be the case that I could be running A on faster hardware and B on slower hardware, right? Or it could be the case that a genius programmer coded A while a newbie programmer coded B, right? So we want a way that abstracts out these differences. We want a way that does not care about the underlying hardware. We want a way that does not care about the underlying implementation, right? Which is why we want a method that makes sure that the rate of growth of algorithms is compared rather than the time it took. All right? Okay. So now let us look at the definitions of these asymptotic notations. So first of all, let's look at big O, right? Big O notation. This is denoted as O of Fn. So let us first write the mathematical definition of this, and then I will explain what this means. So big O of Fn is actually defined as a set of functions that grow at most as fast as f of n. Does that make sense? So we are saying that any function whatsoever, if that function grows at most as fast as f of n, then that function is part of big O of Fn, right? Mathematically, so we will talk about the rate of growth. Mathematically, we will denote this as big O of Fn is the set of all functions Gn, right? Big O of Fn is the set of all the functions Gn such that the function grows at most as fast as Fn. How do we denote this? How do we denote this mathematically? How do we denote the rate of growth mathematically? All right. So let us look at how do we denote the rate of growth mathematically. So first of all, we want to make sure that the multiplicative constants, the underlying hardware does not really affect, right? The underlying hardware does not really affect it. So we are going to say that, okay, Gn must be less than or equal to Fn, but we can allow for some multiplicative constant. We can allow you to multiply any constant C over here. All right. So we are saying that for any constant C, for some constant C, right, there exists a constant C such that this holds, right? That's the first thing. We do not want multiplicative factors to affect our rate of growth. Secondly, we want to make sure that we are measuring for a large enough input, right? We do not care about small inputs. So we will put another constraint over here. We will say that this will hold true. This will hold true for all n which are greater than some value of n, right? Which are greater than some base value. Now we are not defining what this base value is. We are saying that it should be just greater than some particular value. After this value, no matter what value of n you choose, as long as you have some constant and your value is greater than n0, then Gn will remain less than or equal to Fn. Does that make sense? Yes, this is how we define grows at most as fast as fn. Basically, let us suppose that this function is fn, right? And let us suppose that this function is gn. Now we want to define, we want to check if gn is a part of big O of fn, right? So we are going to say that, all right, let us first not talk about small values of n, right? Let us not talk about small values of n. Let us define a very big value n0. Let us define a very big value n0, and we will only be considering all the values of n that are greater than n0. We will only be talking about this part. In this part, it could be the case that gn is above fn or gn is below fn. However, if I'm allowed to multiply fn with a constant c, which is greater than 0, and I can make sure that by doing that, fn is always above gn, right? If by multiplying fn by a constant c, I can make fn always above gn, then I can say that fn grows at least as fast as gn, or I can say that gn is in big O of fn. Does that make sense? Yes. So once again, big O of fn is the set of all functions that grow at most as fast as fn, right? Mathematically, it is defined as the set of all functions gn such that there exists a constant c which is greater than 0, and for all n is greater than n naught, right? For whenever these constraints are satisfied, then gn must be less than or equal to c times f of n. This is how we mathematically represent this statement. All right, these two statements are completely equivalent. Cool. Now let me take some questions. Let me take some simple questions. So let us suppose that we have fn equals to n plus 6. All right. This is one function, fn equals to n plus 6. Let us try to list down what big O of fn is, right? So can someone try to guess what big O of fn is going to be? Can someone try to give me an answer over here? Sumit asks, do we need to know this part to calculate the complexities of in a program? Yes, Sumit. Understanding the meaning of big O notation and understanding the meaning of asymptotic notations, asymptotic complexities is very important. Right? If you do not really understand that part, then you might end up at incorrect answers and you will not understand why your answer is incorrect. Cool. So what all functions do you think are part of big O of fn? Well, of course, y equals to n is definitely a part, right? So basically f of n equals to n. It is slower than n plus 6. Does that make sense? Well, what about fn equals to n by 100? Is that also a part of big O of fn? Yes, that is a part of big O of fn. What about fn equals to 100n plus 600? Well, it seems that 100n plus 600 is greater than n plus 6. Right? It seems that 100n plus 600 is greater than n plus 6. But please remember that we have this constant that we are allowed to use. Right? We are allowed to multiply fn with a constant. So this is also allowed because we can simply multiply fn. We can multiply fn with a constant like 1000. Right? And then 100 plus 600, 100n plus 600 will be less than 1000n plus 6000. Right? So this is definitely a part. Well, there are a lot of other functions that are also part of big O of fn. For example, fn equals to, or let me call these gn's. Right? Let me call these gn's. Gn equals to log of n. Log of n also grows slower than n plus 6. So this is also part of big O of fn. Right? Similarly, under root of n. Right? Similarly, log n to the power 5. All these functions are part of big O of fn. In fact, this set is infinitely large. Right? There are infinitely many functions that are part of this set. Is that clear? Yes? Perfect. Okay. So now that we understand what the big O complexity means, let us quickly look at the order in which we know that let us look at some rules of big O complexity. Okay. So let us compare the following things. So we have a constant. We have a constant function. This is represented as fn equals to some constant c. All right. On the other hand, we can have some sort of a logarithm, right? This is represented as fn equals to log of n, right? With some base b, right? With some base b. Okay. We could have a square root right? This would look like fn equals to under root of n. We could have more. We could have something like linear. Right? This will look like fn equals to n. We can have quadratic, right? Fn equals to n square plus 10 maybe, right? And so on and so forth, right? So we can have cubic, we can have any polynomial with any degree, right? Then on a high level, we can even have exponential. We can even have exponential. So this will look like Fn equals to 2 to the power n, right? Fn equals to 2 to the power n, or Fn equals to 1.5 to the power n. Whenever the base is greater than 1, then it is exponential, right? Cool. Then is exponential the highest complexity that we can talk about? Certainly not. We can keep going, right? So we can define something like factorial maybe. We can define factorial. So this would be Fn equals to n factorial maybe. Right? We could have nested exponentials. So we could have Fn equals to n to the power n. Right? We can continue infinitely. We can continue infinity both in this direction and in this direction. Right? Can something be slower than a constant though? So not in this direction, but over here. Can something be slower than a constant? No, right? Because a constant literally does not grow. A constant does not grow at all. So the constant is the least amount of growth that is possible, right? But there are functions that can lie between this and this. Does that make sense? So this is in increasing order. Is that clear, guys? This is an increasing order of the complexity. Constant grows the slowest. It grows the slowest. So if a function grows slower, what does it mean? What does it mean? Is the algorithm faster or slower? So if there's an algorithm that takes this much time, and we are saying this function grows very, very slowly, right? In fact, this function does not grow at all, grows slowly. So what can I say about the algorithm? Is the algorithm fast or is the algorithm slow? Right? So when the complexity grows slowly, the algorithm is fast. Algo is fast, right? Whereas when the complexity grows quickly, the algorithm is slow. All right. So we want our algorithm to have a complexity that grows very, very slowly. Does that make sense? So an algorithm that runs in constant time, that algorithm is the fastest algorithm. An algorithm that runs in logarithm time, that algorithm is pretty fast, right? An algorithm that runs in factorial time, that algorithm is extremely, extremely slow. Is that clear? Yes? Cool. So let me ask you a couple of questions. Of course, you will find many more questions. I will be giving you a couple of questions over here, but if you want to practice more questions, you will find the link in the video description. Right? So in the YouTube video description, you can go and there will be a link to a set of questions over there. Just go over there and try those questions out. All right. So I hope that you understand this distinction between active learning and passive learning. Right? If you just watch a lecture like a movie, right? If you just listen to that lecture, you do not take notes and you do not practice, then you will be getting some of the benefit, but you won't be getting all of the benefit, right? On the other hand, when you actually take notes, when you actually write your notes yourself, and once the lecture is over, when you actually practice the problems, that is going to help you out a lot. Cool. So this was a lot of theoretical stuff, right? This was a lot of theoretical stuff about what asymptotic notations are. Now let us actually look at some code. And try to see if we can figure out what the asymptotic complexity of that code is. All right. Now, figuring out the asymptotic complexity of a particular piece of code can be very, very difficult, right? So for example, if you have a recursive function, or if you have a complex data structure, right? Then analyzing the time complexity of that piece of code can become a little more difficult. So we will not be covering this today, all right? However, we will be taking a class. We will have a complete set of classes on recursion, right? We will have a set of classes on recursion. We will have a set of classes on different data structures as well. So when we talk about recursion, we will talk about analyzing the time complexity of recursion as well in that particular session. All right. Today we are only going to look at very simple pieces of code and trying to analyze the complexities of those pieces of code. Cool. So let us begin. So suppose I have written a program that looks something like this. I declare a variable int x equals to 10, right? And then I do something with, maybe I do print x, right? Let us suppose this is my piece of code. How much time do you think this code takes? How much time does this code take? How much time do you think this code takes? Well, whenever we have trivial operations like this, whenever we have trivial or simple operations, then usually those operations take a constant amount of time, right? A constant amount of time. So this particular operation, this is a declaration, and there is also an initialization, right? So what will happen is the computer will allocate some memory, the computer will populate that memory with the value 10, and the computer will move a lot of stuff in and out of the CPU, in and out of the RAM, in and out of the cache, and things like that, right? Similarly, when we are calling the print function, what will happen is the computer will load the address of X, right? It will load the address of X. It will load the address of this print function, right? And then it will invoke this print function with this particular address, right? Whatever this print function does, it will also do that. So we are assuming over here that all these operations take a constant time each, right? So this one takes O1 time, this one takes O1 time, all right? So overall, this entire program takes a constant amount of time. Is that clear? Very simple, very easy thing, right? But this is not that simple, right? We have to be a little more careful. For example, let us say that I have, instead of x equals to 10, I have a vector of int, right? So vector of int is just a list of it. So if you are coming from a programming language like Python, so this is in C++. In Python, you would just have x equals to list of something, right? In Java, maybe you will have x equals to array list, right? Array list of integers and so on, right? Let us suppose that we have a vector of int. So we are saying x equals to vector of int, and it has, let's say, a size of 1000 elements, right? 1000 elements. Or let us say that it has a size of n. It has a size of n. What if I try to do something like this? Print x. How much time do you think this print x will take now? How much time do you think this print x will take now? Well, earlier we said that print x was going to take a constant amount of time, right? But now it will not take a constant amount of time, because in order to print a large array, it will have to go through that entire array, right? It will have to go through that entire array. So whenever we are talking about very simple data structures, whenever we are talking about the basic data types, right, like integers, like floats, then the operations on them will be constant amount of time. But when we have larger data structures, for example, when we have vectors or when we have hash maps, right, then operations on them can take more time. So for example, in this case, the print function will take order of n time. It will be linear. Does that make sense? So we have to be careful over here. We have to be careful before we simply say that, okay, this is constant time. We have to be a little more careful. Okay. So now let us move on to some control flow structures. All right. Suppose that we have code that looks like this. If condition, right? And if this is the condition, then we do some work over here that takes O of fn time. Else, we do some work over here that takes O of gn time, right? So basically, we are saying that if this condition is true, we will go into this part, we'll go into this block, and the time complexity of this block is order of fn, right? Whereas if this condition is not true, we'll go into this block, and the time complexity of this block is order of gn. So if this is the case, then what is the time complexity of this overall piece of code? What is the time complexity of this overall piece of code? Well, the time complexity of this overall piece of code is, it is the maximum out of fn comma gn, right? So you will basically say that this is order of max of fn comma gn. Is that clear? Cool. Alternatively, you could have also said that this is order of fn plus gn, right? Even though depending on this condition, you will only go into one of these blocks, right? It is not the case that you're going into both these blocks. However, asymptotically, this and this, they are exactly the same. Why are they the same? Can somebody tell me that? Because these are related by a constant factor, right? These are related by a constant factor. If I just multiply this value by 2 times, right? If I just multiply this value by 2 times, then this value, 2 times this maximum value, will become greater than fn plus gn, right? Which is why it doesn't really matter which one we say. Is that clear? Cool. Now let us move on to loops, for example. All right. So we just covered if-else statements. They are a part of control flow. Let us move on to loops. So let us suppose that we have a for loop, something like this: I equals to 0, I less than n, I plus plus, right? And in this loop, let us say we are doing print I. Yes. So whenever we are talking about loops, we have to look at the time complexity in different parts. Okay. So first of all, we will say what is the time complexity of this inside block. What is the time complexity of this inside block? Well, this is constant. Right? Printing a particular value, it takes just one step. Right? So this inside block is constant. Then we will see, okay, how many times are we going to run this inside block? So this inside block, although it takes a constant amount of time, it is not going to be run once, right? We are going to run this again and again. How many times are we going to run this? Well, how many times this loop will run, right? So that is how much this loop goes from 0 all the way till n minus 1. So that is n times. Yes, that is n times. So it turns out that the complexity of this entire program is n times order of 1, right? N times order of 1, which is nothing but order of n. Is that clear? Cool. Let us look at nested loops. So nested loops are very similar. So suppose that we have for I goes from 0, I less than n, I plus plus, right? And we have suppose j as well. So we have a nested loop inside this for j goes from 0, j less than, let's say, n, j plus plus, right? And over here we do print, suppose I plus j, right? Suppose this is our code. Then once again, we will look at the innermost block. And we will say, okay, what is the time complexity of this block? Right? What is the time complexity of this block? Well, the time complexity of this block is just order of 1 because we are printing an integer, right? We are printing a single integer. So the time complexity is just order of 1. Then we will ask ourselves, okay, how many times are we going to run this block? Well, the answer is not so simple, right? The answer is not so simple because both these loops are going to run this block again and again. So let us break it down further. Let us say that, okay, let us not worry about the outside loop. Let us look at this piece of code, right? What is the time complexity of this piece of code? Well, we just saw it earlier, right? The time complexity of this piece of code is order of n. This is order of n. Why? It is order of n because we are running this O1 operation n times, right? This loop will run n times. So this time complexity is order of n. Then we will say, okay, now this blue block here takes order of n time, and we are going to run this blue block n times, right? So what is the overall time complexity? It is n times big O of n, which is big O of n square. Is that clear? Right? So I hope that you now understand how to calculate the time complexities of nested loops. All right. Now we have to be a little more careful once again. In this particular loop, why was this loop taking order of n time? So if we have a loop that looks like this for I equals to 0, I less than n, I plus plus, we say that this loop ran n times. Does everyone agree that this loop ran n times? Yes. What about if we had a loop that looks something like this? For I equals to 0, I less than n, I plus equals to 2. Right? Instead of incrementing by 1, what if we incremented by 2? Or what if we incremented by 200? Now the loop will not run n times, right? Now how many times will the loop run? If this is the case, then how many times will the loop run? It will run n by 200 times. Yes, n by 200 times. Well, let us look at the time complexity in that case. Let us say that inside this, we were doing O1 work, right? Inside both these things, we were doing O1 work. So the time complexity of the previous block was n times order of 1, which was order of n. The time complexity of this block is what? It is n by 200 times order of 1, which is what? Which is order of n by 200. Well, order of n by 200 is actually the same as order of n. Is that clear? The order of n by 200, the big O of n by 200 is actually the same as big O of n, right? Because as we said, in the big O time complexity, in the asymptotic notations, we kind of ignore the constant multiplicative factors, right? Any constant multiplicative or additive factors can be ignored. Is that clear? Yes? Cool. So these are separate loops, guys. These are separate loops. These are two different pieces of code. We are saying what happens when we do I plus plus, whereas compared to that, what happens when we do I plus equals to 200. All right. This loop will run n times. This loop will run n by 200 times. These are different pieces of code, right? They are not nested loops. Okay. These are not nested loops. Yes. So yes, it is true. It is true that this particular loop, this loop runs 200 times less right? This loop runs only n by 200 times, whereas this loop runs n times. But the time complexity, asymptotic time complexity of both the loops is the same. Is that clear? Okay, so Saurav has a question over here. Saurav says that, okay, when we did this if-else condition thing, you told us the following. You told us that big O of Fn plus Gn is the same as big O of max of Fn comma Gn. Right? This is what I said. Let us try to prove why this is the case. Okay, let us try to prove why this is the case. All right. So let us go to the definition of big O once again. Let us go to the definition of big O once again. Let us look at this particular part over here. Right? Let us look at this particular part. So I am going to prove that for large enough n, right? When the value of n0 is large enough, and for some constant c, I'm going to prove the following: Fn plus Gn is less than or equal to c times max of Fn comma Gn, right? And this will be for all n greater than n naught. Yes. If I can prove this, then what will that mean? That will mean that Fn plus Gn is actually an element of big of max of Fn comma Gn. Is that clear? Does that make sense? Cool. So let us see if this is true or not. Well, let us fix n naught. Let us say n naught equals to 0. Okay, let us say that n naught equals to 0. So we are having a very small value of n naught, that does not matter. Let us now choose a value of c. Let us say that c equals to 2. Okay, let us say that c equals to 2. Well, if c equals to 2, then does this equation hold? Fn plus Gn is less than or equal to 2 times max of Fn comma Gn. Is this equation true? Yes, this is true. Why is this true? Well, we don't really know what is larger. What is larger between Fn and Gn? But let us suppose that Fn is larger. Right? Let us suppose that Fn is larger. So what will this be? This will be 2 times Fn minus some delta value, because Gn is smaller than Fn. Whereas on the right hand side, we have 2 times the maximum of Fn and Gn will be Fn itself. So that will be 2 times f of n. So we see that yes, this equation in fact holds, right? Which is why we can say that Fn plus Gn is an element of big O of max of Fn comma Gn, right? Similarly, we can do this the other way around as well. We can also prove that max of Fn comma Gn, this is in fact less than or equal to some C2 times Fn plus Gn for some large enough value of n, right? So we can prove this the other way around as well. So that will mean that this does not just go one way, right? This is true, but also this is true. Max of Fn comma Gn is an element of big O of Fn plus Gn, right? So this is also true. And if we put these both together, we see that, hey, irrespective of what function I choose, I can say that this function grows faster than this function, right? If I am telling you that x is less than y, x is less than or equal to y, and I also tell you that y is less than or equal to x, what does that mean? If I have both these equations, what does that really mean? It means that x is just the same as y. Yes? Is that clear? So over here, we can say that f of n plus g of n is the same as max of Fn comma Gn, right? But this is not correct, right? This is not correct. We have to be careful. We do not mean equals to over here, right? We do not mean equals to over here. Clearly, these two functions are not equal. We mean the order of growth, right? We mean the order of growth is equal, right? Now this equation is correct. Is that clear? Yes? Perfect. Cool. So let us look at one more for loop, for example. So suppose we have a for loop that looks something like this. So we have for I goes from 0, I less than n, I multiplication equals to 2, right? Then print I. How much time do you think this particular loop will take? Well, let us look at what happens in this loop, right? What happens in this loop. So initially, so let us start with I equals to 1, in fact. Let us start with I equals to 1. Right? So initially I equals to 1, right? Then we will print 1. Then what will happen? I will be multiplied by 2. I becomes 2. So we will print 2. After that, I becomes 4. Then I becomes 8. Then I becomes 16, and so on and so forth. Right? So I is doubling each and every time. Right? I is doubling each and every time. So if I has to reach n, right, how many steps will it take to reach n? That is the question. If I keeps doubling each and every time, how many steps will it take to reach n? That is the question. Will it take n steps? Will it take under root of n steps? Will it take n by 2 steps? Will it take log n steps? What do you think is the answer? Well, this is the answer, right? It will actually take log of n base 2 steps. Right? It will take log of n base 2 steps. Is everyone familiar with this? Right? This is via the definition of log n. Right? I hope that everyone is familiar with this. If you are not super comfortable with this, not a problem. Just join the discussion. Right? In the chat, there will be a link for the discussion. Just join over there, and I can explain that to you in much more detail. Why this is going to take log n steps. All right? Cool. So this particular loop, this particular piece of code, this takes order of 1 time, and we are going to do that log n times. So the complexity of this code is overall going to be order of log of n. Is that clear? Yes? Perfect. Let us look at another example maybe. Let us say that we have for I equals to, let us say 1, right? And we can say that, okay, let us have j is less than n, I plus plus. Okay, so please note over here, let's not make it j. Let us say that this is k. Let us say that this is k. So we are going from I equals to 1, we are incrementing I, and we are checking the condition with respect to k. And inside the loop, we will write k equals to k plus I. Is that clear? Is this program clear? Initially k equals to 0, and we are going from k equals to 0 all the way till k equals to n, and this is the program. So let us see what will happen. So how much time is this inner part going to take? What is the time complexity of this inner part? Well, very simple once again. This is just order of 1 time. Right? This just takes order of 1 time. But how many times are we going to execute this? Right? How many times is this code going to run? Is this loop going to run? Let us try to analyze that. Right? So initially k is 0 and I is 1. Right? Initially k is 0 and I is 1. So when we do this, k will become 1. Right? When we do this, k will become 1. Okay. Then what happens in the next step? We go to this thing, right? I plus plus. So I becomes 2 now. Right? So when I becomes 2, what will k become? K will become, so k was earlier 1 plus 2, which will now be 3. Right? So k equals to 3. Yes? Does that make sense? Let us look at the next step. So now I equals to 3. K will become 1 plus 2 plus 3. Right? 1 plus 2 plus 3, which will be actually equal to 6. Right? So we will print k equals to 6 and so on and so forth. So how much time do you think it will take for k to reach n? Right? How many steps will it take? So after the first step, k was 1. After the second step, k was 3. After the third step, k was 6. After the fourth step, k will be 10, and so on and so forth. So after how many steps will k be greater than or equal to n? That is the question, right? What is the delta here? The delta here keeps changing, right? Initially it was 1, then it became 2, then it became 3, then it became 4, and so on. It will keep on increasing, right? So that is the question. So can someone tell me the answer? Well, we will have to do some mathematics over here, right? So basically what is happening with k is, at the ith step, the value of k is equal to 1 plus 2 plus 3 plus all the way till I. Do you guys agree? At the ith step, this is the value of k. Yes, because that is what we are doing, right? We are incrementing the value of I and we are adding it to k every time. So at the ith step, this is the value of k. All right. So let us try to solve this. So do you guys know this? Do you guys know the formula for this? What is the value of 1 plus 2 plus 3 all the way till n? Right? You can also write this as the summation for I equals to 1 till n of I. Right? This is the sum of first and natural numbers. Can someone tell me the formula? This is simply the same as n into n plus 1 by 2. Right? This is also known as the nth triangular number. This is also the same as n plus 1 choose 2. right? You can represent the same thing in multiple ways in mathematics. You can say it like this, 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 and you can say it like this. All right, so many different ways. Okay, so now that we know this formula, what we are basically saying is that at ith step, k equals to 1 plus 2 plus all the way till I, which is nothing but I times I plus 1 by 2. Right? That is what we are saying. At the ith step, k will have this value. Right? Now our question is, at what step will k be greater than or equal to n? Right? That is the question. Is this clear? So we have an equation to solve, right? So we are basically saying, if at the ith step k is this, then at what step will k be greater than or equal to n? So let us simply place the value, right? We want I times I plus 1 by 2 to be greater than or equal to n. Yes, I into I plus 1 by 2 is greater than or equal to n. Right? So basically I into I plus 1 is greater than or equal to 2n. Right? And if we solve this, if we make it in terms of I, right? If we make it in terms of I, so remember what we have to find. We have to find the value of I, because we want which step, how many steps does it take. So it will turn out that I will come out to be of the form square root of n. Right? It won't be exactly square root of n, it will have some particular value over there, but the effective will be that I will be order of square root of n. Is that clear? Yes. Yes, how do you actually solve for I from this? How do you actually solve for I from this? So you can make it into a quadratic equation, right? So you can say I square plus I is greater than or equal to 2n. Then you can say I square plus I minus 2n is greater than or equal to 0. Then you can solve it with the minus, so minus b plus minus root over of b square minus 4ac by 2a. Right? You can put the value of b, the value of a, and the value of c to find the final value. And it will turn out that I will be of some form of root n. So I is the order of root n. So what we are essentially saying is that the loop will run order of root n times. Yes, the loop will run order of root n times. And how much work are we doing in every single iteration? In every single iteration, we are doing a constant amount of work. Right? In every single iteration, we are doing a constant amount of work. So overall time complexity will be order of root n times order of 1, which is nothing but order of root n. All right. So the time complexity of this particular loop will be order of root n. Okay, cool. So I guess we will end the lecture for this today. So today was very simple concepts, the very basics of time complexity, very simple loops, very simple if else statements, right? We are going to cover a lot of things in a lot of depth, right? So when we will have the class on recursion, we will tell you how to understand, how to analyze the time complexity of recursion. When we talk about sorting, we will consider the time complexity of sorting. When we talk about graphs and trees, we will talk about the time complexity analysis for graphs and trees. All right. So do not worry about that. Cool. All right then, guys. Have a nice day. Bye-bye.
Very quickly introducing what we're going to cover today, right? So today we're going to talk about sorting. And why is sorting important? I mean, sorting is essentially nothing but arranging data that you have in a particular order, right? For example, if I have a few numbers, I could say I want to arrange them in an increasing order. Or if I have people, let's say I want to arrange them in the decreasing order of their height or increasing order of their height, etc. The ordering, because you are able to order something, helps you in a lot of things. For example, sorting might then help you do binary search on that data if you want to look for something. Or if I give you queries around, hey, tell me how many numbers are bigger than a specific number. That also, I mean, if the array is sorted, you can just look for the index of the first element bigger, and then you know how many numbers are bigger, etc. So sorting helps in those contexts if it is ordered. In fact, most NoSQL DBs, they actually try to maintain data in a sorted form. Sorted set is what it is called, because it makes searching for data, looking for data, doing a bunch of analysis on data easier and easier, right? So today, we're going to, just to elaborate, we're not going to talk about searching. I'm going to talk more about sorting. Sorting is arranging data in a particular order, right? So for example, if let's say give you 5 numbers, I give you numbers, let's say 5, 10, 3, 2, and 8. These are numbers in no particular order, right? Now, if I say arrange these numbers in an increasing order, where the smallest number comes at the front of the list and so forth. That part is called sorting. So, if you sort this, then you'll have 2, 3, 5, 8, and 10. It's an arrangement of the given numbers so that they are in some particular form or order. As I said, like, the reason why it is important is because it helps you do a bunch of different kind of operations on the data fairly quickly if what you have is sorted. And I gave the example of NoSQL databases where they maintain data in sorted sets because it lets them do a bunch of different kind of queries in a sorted form. In fact, we will talk about some form of MapReduce when we go to system design modules. There also you'll see like a lot of things are generated in sorted forms because it allows for certain more operations to happen later on. Does everybody understand like what sorting is? So maybe like the way I would explain sorting is taking just like in binary search, I took the real world example of searching in a dictionary, what we normally do in real life. I'm again going to be taking the example, a real life example of what we might have done in our lives before, right? All of us went to school, and in school we were made to stand in increasing order of our heights. Now, let's take that example, which is I have a class full of people and I want to arrange them in increasing order of their height. Right now, assume they are standing in some random order. What are the different ways in which I can actually arrange them in increasing order of their height? And I'm going to take various sort of approaches I would have taken. And then I would sort of map it to what that approach is in real life. So approach one could be that I ask everybody to come one by one. And let's say if I have a few people already standing in the line, let's say I have few people that I've already arranged in the line. And let's say there is this new guy with this height that comes. In fact, it is better to imagine, maybe I can write the height of each of those individuals. Let me just write the height. So imagine I had somebody with height 1, 5, 12, and 27 already in the line. Somebody with height 7 comes. One thing which I can do is I can find the right position for this person, which is between 5 and 12. And I insert 7 there, which means then I'll have 1, 5, 7 here. And then 12 and 27, I'll push one space back. Right? So 12 comes here, 27 comes here, right? And then as people keep coming, let's say there is a person called 32. I'll figure out where 32 should lie here. I'll figure out 32 should come here. I'll insert 32 here. Everything up after 32 would be pushed one space back to make space for 32. Here there is nothing. This is called insertion sort. This technique where I get numbers, I figure out what is the right location for them. I can do that through binary search or I can do that through a linear scan. Either is fine. Once I find out what their location should be, I shift all of the other numbers one space to their right and then insert this new number at the new location. Now, that is called insertion sort. If I have to write the approach for this or the steps for this, basically assume that I am maintaining my sorted array in, let's say, sorted array list. That's a sorted list, which is initially empty. And imagine I keep getting a few numbers, right? What I do is I start from the end of this list. For example, here, if I had 1, 5, 12, and 27, and I wanted to insert 7, I'll start from the end. Is 7 already bigger than 27? It is not. So what I would do is I'll shift 27 one space to its right. So imagine this was the array. I have one space left here, so I'll shift 27 to its right. So 27 comes here. Then I go and again check 12. Is 7 bigger than 12? No, it is not. So I'll shift 12 to one space to its right. 12 comes here. Then I check the next number, which is 5. Is 7 bigger than 5? Yes. That means this is the location of 7 and I insert it here. That is, I keep doing this with every new number that I encounter, and that makes for what is known as insertion sort. What is the best case complexity here? Best case time complexity here. And what is worst case time complexity here? Best case for sorting. Order 1 would be the time complexity of inserting a new element, best case, right? Because you start with 7, you'll find that, let's say the new element that we are inserting in this new array, let's say that is 32. Best case is I look at the first element and I find that 32 is bigger than that, and therefore 32 just gets inserted here. It is for the addition of the last, like the new element. Order 1 is the best thing that you can do, but you'll have to add n such elements. So therefore, if you do order 1 for n elements, you'll end up with order n best case complexity. So in the best case, insertion sort will take order n time. What is the worst case? When do we get the worst case? What is the worst case, and in what kind of data would we get worst case? If the array was reverse sorted, which means if, let's say, I was giving you numbers, I first give you number 5, you insert 5, then I give you 4, you insert 4 here, right? Because you'll have to shift 5 1. Then I give you 3, you'll figure out that actually 3 is smaller, so you'll shift 5 here, and you'll shift 4 here, and then 3 comes here. Then I give you 2, you'll again like shift 5 here, you'll shift 4 here, you'll shift 3 here, and then 2 will come here. And then again, you'll do one more shift and to get 1 in if 1 is the next number, right? This ends up taking, for the first number, you take 1 step. For the second number, you take 2 steps. For the third number, you take 3. And for the fourth number, 4 and 5 and 6 and so forth. So this becomes almost order of n square. So worst case, this might take order of n square when the numbers are sorted in decreasing order. A very interesting question, which is, does the time complexity affect if we take linked list? There are two parts here, right? Like one is, there are two things that we're looking for. One is, what is the right index where this new number should go? And the second is shifting greater numbers to make space. One place right. So your linked list will save you on this time. So this time will become 0. However, finding this 1 in a linked list, because you can't really jump to a random location, you'll have to do a linear scan to figure out where the number should occur. Right? So that might still end up taking order of n square, because searching for the right index, the step number 1, that might end up taking order n. You can't apply binary search in linked list because you can't just jump to a random location in the linked list. Right now, the way I explained insertion sort was that you were getting a stream of numbers and then you're sort of sorting it by putting them in the right location. Now, whatever I said, that can also be applied to an existing array as well. Let me explain. Right now, the way I detailed insertion sort is by saying that, like 5, I'm getting 5, then I'm getting 4, then I'm getting 3, then 2, then 1. Imagine I was already given an array, right? So imagine I had the array as, let's say 5, 8, 3, 2, 18, hypothetically, right? And I asked you to sort this array in place without using extra memory. I do not want to use any extra memory. Can you sort this array without using extra memory? Insertion sort. So I don't again have the flexibility of creating a new array. I am doing this in place. How do we do that in place? Even when you're doing in place, imagine I start from 5, right? So first I'll start with 5. I'll say I only have to sort this. 5 is the new number that I've gotten, right? So I have one place, 5 is the new number I've gotten. Obviously, it will go at this position. So 5 comes here. Then I go to the second number. And I say, let's put this in a temporary variable. Temp is equal to 8. Now, 8 is the new number I'm trying to insert in the first two locations, right? So first I'll compare with 5. Is 8 already bigger than 5? Yes, it is. So it will come here. Then I look at sorting the first 3 numbers. I pick 3. So I delete 3 from here, imagine. And this 3 is the new number to be inserted. So first I check with 8. Is 3 bigger than 8? No, it is not. So 8 will come here. Is 3 bigger than 5? No, it is not. So 5 will come here. And then 3 gets inserted here. So now if you look, by now I have the first 3 numbers sorted. Now I'll take this number 2, which is I'm trying to sort the first 4 numbers. I'll take the new number 2 and imagine that 2 is the new number that I was getting. So I put this in a temporary variable. I'll do the same comparison. Is 8? No. So 8 comes here. Is 2 bigger than 5? No. So 5 comes here. Is 2 bigger than 3? No. So 3 comes here. And then 2 comes here. And then finally 18 is bigger than 8. So 18 will directly come here. Does that make sense? So same approach. All I'm doing is I'm saving on the additional space if an array is given to me already. The worst case time complexity is still the same. Nothing has changed in the approach. I'm just using the same space that was there in the array instead of creating a new array. Okay, so if we apply binary search for position, it will contain more computations, right? Finding plus swapping. Yes. If you do apply binary search, you'll first take log n time to find the right location. And then in worst case, order n extra time to create the space. I mean, right shifting all of the elements to create space for this other element, right? So it will end up taking n plus log n every single step instead of just n every single step. So this log n is additional. Overall time complexity will still remain n square because you'll do this n times. So instead of n into n, you'll get n into n plus log n, which is basically n square plus n log n, which is still order of n square. But why do that? I mean, why do this additional operation? Why not just start from the end? You have to shift the bigger elements one step to the right anyway. So just start from the end, shift the elements to the right, and then like fit the element wherever you find the first place. All right, everything clear till now? So that is one way in which you would sort, let's say, your classmates, right? The second approach that I have is, let's say I have an array, right? Like let's say the same array. I had, in fact, let me go with the original 5, 10, 3, 2, 8. So 5, 10, 3, 2, 8. And I put this in an array. Now what I know is that in the sorted array, the smallest number has to come at the beginning of the array. Do we all agree with that? Smallest number has to come at the beginning of the array, right? So one thing that I can do, which is not very optimal, but still works. So it is every single time I look at what is the minimum in my given array. For example, if I run this loop, I'll figure out that 2 is the minimum. I say, okay, great. If 2 is the minimum, let me push 2 to the beginning of the array. So 2 comes here. And then I can just swap it with 5. So 5 comes at the place of 2. So when I do this, 2 comes here, 5 comes here. Now what I know is that now 2 is at the right position. I only have to sort the remaining 4 elements. And I repeat the process. For the remaining 4 elements, I again look for the minimum. Find 3. So I swap 10 with 3. And then I sort the last 3 elements. And then again, like I look for the minimum 5, I put 5 here and then so forth, right? The only downside of this approach, while this approach works, the only downside is it is order of n square no matter what the input. So in the best case, worst case, everything is order of n square. The good thing with insertion sort was that there is a case where the best case was order n. So therefore the average performance could have been better. If we do this, it is always order of n square. I mean, basically the steps were find minimum. 2 is put in start of array and then start plus plus. That was the approach. If the array is already sorted, even then, to find the minimum in the array, you'll have to look at all n elements. So every single time finding the element is taking you order n, right? So that approach is a precursor to bubble sort. So while this approach works, the question is, can we do something so that if the array is already sorted, then we don't have to go through all of the elements all over again, right? Like every single time finding the minimum takes me a lot of time. How do we decide when to break? Check whether the array is already sorted or not. Let me maybe give some other case, right? So insertion sort will still be order n if, let's say, only one element was not in its right position. Every other element was in the right position. For example, if the array was, let's say, 1, 2, 3, 4, 0. The array is just very simply some random elements. Bubble sort is a variation of exactly this. Bubble sort is, as the name suggests, it is like bubbling something to the top, right? So what you do is you compare all adjacent elements one by one. And wherever you have a pair of numbers, so what you do is, for example, let's say people are standing in some random order in the line, right? So for example, I have people standing as 5, 10, 3, 2, 8. Let me just write it like this: 5, 10, 3, 2, 8. my objective is somehow bubble the smallest number 2 to the top. So what I do is I say the last person standing in the line, hey, you compare yourself against the next person to you. You obviously know how to compare yourself against the next person. You can check your height versus the other person's height. Obviously, if you're standing behind and you're smaller, then you should swap yourself, right? So I say 8, look at 2. If you're smaller than 2, then swap yourself. 8 says, I'm not smaller. Great. Then I say 2. Look at the next person ahead of you. If you're smaller than that, then swap. And I do see that 2 is smaller than 3, so I swap. So 3 comes here, 2 comes here. Then I say 2, swap yourself against the next person if the next person is smaller. I figure out 2 is actually smaller than 10. Sure, I mean, it should get swapped. So 2 comes here, 10 comes here. And then I again say 2. Again, compare yourself against 5. If you're smaller, swap yourself. So 2 again gets compared with 5. 5 comes here, 2 comes here. So what has happened in this one order n loop? The smallest number has bubbled itself to the top of the array. This is why, I mean, because the smallest element is bubbling to the top, it is called bubble sort. Even this approach, in the worst case, will take order n square. There is one difference here, though. If there are no swaps that happen all throughout in this order n loop, then we just stop there. Which means if the array was already sorted, then we would not do the next iteration. We'll keep doing the next iteration as long as there is swap happening. So let me elaborate again. What happens is, imagine you're standing in the line. I start from the last person. I say, compare yourself against your neighbor. You compare yourself against the neighbor. If you are smaller, then you swap yourself. And then you do that till the start of the array. One thing which is guaranteed in this loop, whatever is the smallest number will bubble up to the top of the array. Then you're left with sorting only the remaining part of the array. And you also know if there is any iteration where I went from the last person to the first person, there was no swap happening between the neighbors, then I know that elements are already in the increasing order. I can just stop. I do the same process again. Now 2 I don't care about. I already know 2 is in the right position for the remaining elements. So I again start from 8. I say 8, are you bigger than 3? 8 will say, yes, I am. And I say 3, are you bigger than 10? No, I'm not. So we'll swap. 3 comes here, 10 comes here. 3, are you bigger than 5? You're not. So sure, I mean, then let's again swap. So 3 comes here, 5 comes here. Again, if you see, 3 has bubbled up to the top, which was the next smallest element. And then you're left with sorting only the last 3 elements. Any iteration where you don't have any swaps, your array is already sorted, you can just stop. Since we had 1 or more swaps in the first traversal, we'll start again from 8, but we'll not go till 2. 2 will be ignored. I mean, the first element is already sorted, so we'll stop here. Now that in the second iteration, we know that the first 2 elements are fixed, we'll start again from 8, but we will stop at after 3. I mean, we'll not look at 3 and 2 anymore because we know that they are in the right position. Every single iteration, what is happening is the smallest element is bubbling to the top. And any single iteration, I know that there is no swap that has happened. I can just break. And therefore, I do have a best case complexity, which is if the array was already sorted, I will do an order n iteration to figure out are there any swaps. But post that order n iteration, I can just break. Or if I reach a stage where, intermediary stage, where let's say I did these and then the remaining numbers were already sorted, then also I'll just break, right? So I'm not really spending time sorting if the array is already sorted. Does that make sense? Let me actually write the pseudocode for this. What I'm going to do is I'm going to start. So here is my inner loop, right? So I'm going to start from the last element. Let's say there is a j that starts from n minus 1, goes to, imagine I'm doing a loop of I from 0 to whatever. I'll tell you what 0 to whatever is. It goes to I. Imagine that like numbers till I are sorted. Right now, nothing is sorted. So n minus 1 to I. What I do is here I compare a of j with a of j minus 1. Now I know that in the right order, a of j should be bigger. So if it is smaller, if there are 2 numbers where the second number is smaller, then obviously they should be swapped. The second number, if it is smaller, if this is smaller, then they should be swapped because they are not in the right order. So I just say swap a of j, comma a of j minus 1, right? By the end of this, a of I will have the smallest element anyhow. I is starting from 0. A of I will have smallest element anyhow. I also keep track of one variable here. has there any swap that has happened? Let's say there is a flag, which is initially 0. Whenever there is a swap that happens, I make flag as 1. If at the end of it, if I see that flag is 0, then I just break, which means this element was already sorted. There is no need to look at other elements. And then I goes from 0 to n minus 1. Yeah, sorry, this is I plus 1. Correct. So again, like what is happening in the algorithm is the smallest element is bubbling to the top, and you're just taking in the process, making sure that if the remaining elements are in the right place, there was no swap, then the element is array is already sorted. So let's just break. Yeah, actually we don't need the n minus 1. When we come to n minus 1, I plus 1 would anyhow, this j loop will not run. So I can just do n minus 2. Again, let's look at what is the best and worst case complexity of this algorithm. Best case is order n, which is my array was already sorted or almost sorted. And then, I do this iteration, flag becomes 0, I break. And the worst case is when it is reverse sorted. So every single time I have to do a lot of these swaps, and it is actually order of n square. All right. So this is, by the way, called bubble sort. Find the smallest element, move it to the beginning. This is called selection sort. In selection sort as well, it's what we were discussing, where we were selecting the smallest element and moving it to the beginning of the array. That is selection sort. The reason why we are discussing this is these are intuitive ways of how we think about sorting, and the technique can come into use later on. Let's do a dry run with bubble sort just to see the best case, right? So imagine I asked you to sort this array 1, 2, 3, 4, 5. Imagine this was my input, correct? Selection sort is sort of an greedy algorithm, because what you're doing is you're saying that I know the smallest element should come at the beginning, so let's find the smallest element, you put it in the beginning, and then you sort the remaining array. Let me, however, show how the bubble sort is still best case order n. Selection sort, by the way, we can also make order n in one case. I'll also go over that. Selection sort, just slight variation, and it can become best case order n. Let's first look at how it becomes order n best case in bubble sort. Imagine this was your input, right? You start with I as 0. I is 0. J, your flag is also 0. J basically goes from, so you have your index 1, 2, 3, 4. J will start with 4 and it will go till 1. 4 till 1. And what do? Every single time you just compare A of J with A of J minus 1. So you check, is 5 less than 4? The answer will be no. So then you move on to the next J. So from 4 you will go to 3. From 4 you will go to 3. Then you compare 4 with 3. Is 4 less than 3? No. Then you will compare 3 with the previous element. Is 3 less than 2? No. Is 2 less than 1? No. So at no point this if condition gets executed. So there is no swap, and therefore flag never becomes equal to 1. So when this loop finishes, when the J loop finishes, you come to the point where flag is still 0, and therefore you break. So just after the first iteration with I0, you end up breaking, because you figured out there was no swap involved in my array. So my array is already sorted. Why look at things again? So that's why you get the best case as order n. Worst case is obviously n squared. Now let's look at what is the case, or how do we make sure that even my selection sort, which is very greedy, can I modify it somehow so that also becomes or best case order n? Let's see. Let's take some random input, right? So I had 5, 3, 8, 4, 6. Now the way selection sort works is you go from the beginning, you look at this, you try to find the minimum element in the array. This is the approach just before bubble sort that I had talked about. You try to find out the minimum element in the array. In this case, I find 3 as the minimum element. And for this, I take an order n loop, right? In order n, I find minimum of the array. Now, if in this iteration only, I would have figured out that the array is sorted in this order n, if I figured out that the array is sorted, which is all of ai is less than ai plus 1, then my work is done. However, if it is not, then the smallest number that I found, which is 3, I try to swap it with the previous element. Basically, I try to put it here and shift all of the remaining numbers one step to the right, which means the array now becomes 3 here. I have 5, 8, 4, 6. In fact, let me just change the array a little bit so that it becomes slightly better. Imagine if the array was 4, 5, 6, 8. When I do the swap, then the array becomes, or when I push it here, then it becomes 3 comes to the beginning, and then I have 4, 5, 6, 8. Now, again, I know that at this point of time, 3 is at the right position. I still need to sort the remaining array. I'll again have to do an order of n minus 1 loop, this, and this to figure out the minimum number. In this case, it is 4 as the minimum number. But by the way, in this order n minus 1 loop, I figured out the array is already sorted. So I can therefore stop my process. The key thing to do here is when you find the minimum element, you don't just swap, but you shift the prefix of the array one step to the right, create space for this new element, and then you put it in the right place. If you do that, then the selection sort also becomes best case order n. One thing is, in most cases, you will neither be using bubble sort or selection sort or insertion sort. Actually, insertion sort may be in certain cases, but most cases you will not be using these. These are algorithms that are good to think about. The approach that we utilized here, this might come into use later on in some or the other kind of context or in some or the other kind of problems. But the sorting algorithm that is currently in use in most of the libraries that you use are either merge sort or quick sort. Quick sort as being the most popular one because it has better average performance, does not use additional memory. But those are the ones because they sort of perform in order of n log n time. All of these are worst case order of n square. Average case is also order of n square almost. Java 8's array.sort also uses quick sort. But like bubble sort, insertion sort, 3 algorithms that I talked about, they're good to know from their approach standpoint because there are some problems that might utilize this approach. These are not necessarily the sorting algorithms you'll use in day-to-day. Sorting algorithms that you will use, I'll talk about that in a few moments. But just so that I, again, complete my discussion on selection sort, let me write the pseudocode for selection sort. Pseudocode is very simple. Right now, if I have to sort, imagine when I is 0, I need to sort everything from 0 to n, right? So what I do is I take, this will go to some number, I'll figure out what. I'll take the loop from I to n. I'll figure out the minimum. In fact, let me actually also track its index. I can just keep it as a of I and index is equal to I. And this loop can run from I plus 1. So if, let's say, a of j is less than min1, then minimum is equal to a of j, index is equal to j. Here, one of the other things which I also track is if a of j is greater than a of j plus 1, then there's a flag that I set to, let's say 1. Let's say there's a flag here which is also 0. And once I have found my minimum, then all I need to do is all of the other numbers, they are shifting one space to the right. So once I have found the minimum, I will take a loop of j is equal to, and then at the end you have a of I is equal to min1. That is one way of shifting. Basically what I'm doing is if I have an array, let's say I have 5, 6, 3, 2, 8. I'm going through once to figure out what is the minimum. Once I find the minimum, I bring minimum to the front, which is 2 comes here. And then 5, 6, 3, I shift one space to the right. And then I try only sorting this piece, where every single time I have a flag to check, is this piece already sorted or not? If at all at any point of time I find that there is a section of array that has already sorted, then I just break out and I'm done. Here, I could very well also have done, instead of doing all of this, I could have done swap a of I, comma, a of index. I could have done this as well. As long as I'm checking that for the remaining array, is the array sorted or not? If the array is sorted, then I just break. That is the only optimization that I put in, nothing else. Now I'm going to be covering a few other sorting algorithms, and then we'll do a few problems on these. Count sort is the easiest one. Count sort is when the elements that you are sorting, they are limited in range. Limited in range meaning, for example, I tell you, hey, you have characters A to Z. You have a lot of characters and you need to sort them. Or you only have numbers 0 and 1. Or you only have numbers from 1 to 20. Then what you do is, instead of counting or basically maintaining numbers themselves, you just count how many numbers. For example, I gave you an array of zeros and ones, right? So bunch of 0, 1, 0, 1, 1, 1, 0, etc. etc. And I told you to sort this array. One very simple way would be I calculate the frequency of 0 and frequency of 1, which is basically exactly what count sort means, right? Like you're maintaining the count of the numbers themselves. So you say I'll count how many times 0 came. let's say 0 came 10 number of times. And I'll count how many number of times 1 came. Let's say it came 5 number of times. Then I know my sorted array. My sorted array is 0, 0, 0, 0, 0, 10 times. And then 1, 1, 1, 1, 1, 5 times. So one very common application of this is if I give you two strings and I ask you, are these strings anagrams of each other? Anagrams is like two strings are anagrams if they are just some or the other permutation of the same string. For example, if I give you a string banana and I give you another string, let's say, this is not really a word, but I give you these two strings, right? And I ask you, are these anagrams of each other? Your answer will be yes, because they have the same count of n. There are two n's here, there are two n's here. They have same count of a. They have three a's here, there are three a's here. And they have same count of b. You know that you only have 26 different characters. So in a 26 array of size 26, you can maintain the counts of number of a's, number of b's, number of c's, and so forth. And you can just compare the counts, right? So count sort is very simple. If you have limited number of numbers, if your range is very limited, you maintain the count of every single number you encounter, and then like you just print those numbers, those many number of times you go from start to beginning. So we are going to maintain a new array for 0 and 1. However, 0 and 1 are just two numbers, two variables. So it is still order 1 space. If you only have, let's say, 20 numbers, then it's just order of 20 space, which is not order n, right? Like it is not dependent on the number of numbers that you have in total. Let me maybe give you an example, right? And then I'll write code for it that will make it clearer. Very simple. Imagine I give you a string of characters, and I just ask you to sort that string of characters. For example, let's say the string is congratulations. Let's say that is like a string. And then there were a bunch more characters as well. But like, let's just say that this is the thing. There could be, let's say, thousands and thousands of characters here, thousands, hundreds of thousands of characters. Now, one conventional way of sorting is like doing the bubble sort or the selection sort, etc. Right? Which is a selection sort would be you figure out which is the smallest character, which is A. You shift A to the front. However, I mean, if there are a lot of characters, that will take a lot of time. So what I say is, hey, by the way, I know that the kind of letters could only be from A to Z, correct? I have A, B, C, D, E, F till Z, correct? There are only 26 characters possible, 26 different characters possible. So if I somehow maintain the character count, right? I have only 26 characters. If I have an array which has the count of what are the number of A's here, what are the number of B's here, C here, and so forth. For example, when I encounter C, I say, let's increase the count of character C by 1. So C's count becomes 1. And I mean, this could just be an array, right? Because any character can be mapped from a number from 0 to 26. So I just maintain an array of size 26, which is all initialized to 0 to begin with. When I encounter C, I increase the count of C by 1. Then I encounter O, let's say O is somewhere here, I increase the count of O by 1. When I encounter N, I increase the count of N by 1. With R, I'll again increase the count of R by 1. A will become 1. Let's say when I encounter A again here, A's count will become 2. So that way, I mean, I'm just maintaining count of every character, right? Like, and if I have to write code for this, I would just do very simple. I would say that, you know what, like I have a array of size 26, which is initialized to 0. This is C++ format, but like Java, etc., it will be similar. And then I just say, you know what, like, let's assume that the character is CH, and I go over this string str, and I just say that ARR of CH minus A, which will now give me a number from 0 to 26 plus plus. At the end of it, I'll have frequency count of every character. And then like the sorting is very simple. I just go character by character, right? So I just go from for I is 0 to 26. I look at the count of the current character. Like for example, when I is 0, then I'm looking at the count of A. So what I do is I take a loop from 0 to ARR of I, whatever is the count. And I print A plus I, those many number of times. So what will happen is if the count of A was 2, then this will print A twice. Then let's say if the count of B was 1, then it will print B. If let's say the count of C was 3, then it will print C 3 times, and so forth. So all I'm doing is I'm just counting the numbers, frequency of the numbers, and then I'm just printing in them those many number of times, going in the order of numbers. Does that make some sense? Count sort, how is it working? As long as the range is limited. For example, let's say if you have numbers from minus 20 to 20, even then you can use the array. right? Because you can just say that every single number num corresponds to the index num plus 20. So when you encounter num, you just say, ARR of num plus 20 plus plus. And when you print, then like for ARR of i's count, you print I minus 20. In general, if you see for doing this, if you have a range of numbers, let's say the range is R, count sort takes order of R memory, right? If the range from min to max of the array, if the range max minus min, if this is R, then it takes you order of R memory, right? Because you need those many number of counts variable, right? If R is small-ish, for example, let's say if R is 1,000 or 10,000 or 100,000 or 1 million, if let's say R is up to 1 million, then you can use count sort because you can maintain the counts and therefore like it will still run. However, let's say if the numbers were not limited, if there could be any integer, then you can't use count sort. Count sort is only applicable when the numbers are limited in the range. As I showed with counting characters in a string, because characters are limited. Characters can only have 26 different values. So it is not done in place in the sense that you're still counting the number of A's, number of B's and C's, and then you can fill it in the same array. For example, if you said, tell me here instead of printing A plus I can just say, you know what? Let's have an index variable, which is 0. And I have, let's say my original string was str. I can just say, you know what? Str of index plus plus is equal to I plus A. I can fill it in the same array instead of printing, but I mean, you'll still have to maintain counts, etc. Merge sort is if imagine you had to sort a deck of cards. One possible way, which is, by the way, also called divide and conquer, could be that I break down this deck of card to half deck of card and half deck of card. So I divide into two parts, right? Like half goes, let's say, to the left, half goes to the right. I sort those individually, right? So half deck of cards, I sort them somehow by some magic. And right side also I sort somehow by some magic. So now I have two sorted deck of cards, right? I have two sorted deck of cards. Now the problem becomes, if I have two sorted deck of cards, can I merge them so that they still remain sorted? Imagine, let me give you an example, right? So let's say I have an array 2, 3, 5. Let's say I have another array 1, 6, 8. If I was given these two arrays, can I merge them into another array which is completely sorted? Is that possible or not? If that is possible, then this could become another algorithm, which is like whenever I need to sort an array, I can divide it into two parts, recursively sort them, and then I can merge them. So merge becomes the important step. The question is, I have given you a problem. You have two arrays, not necessarily of the same length. Let's say this is of size A, this is of size B. Can you create another array of size A plus B where all of the elements come from A or B and they're all sorted? Is the question clear? Like you have some A number of arrays in array A, you have B number of elements in array B. Array A and B are individually sorted. So A is a sorted array, B is also a sorted array. You have to merge them into another sorted array. How would you do that? Basically, if I have been given two numbers, let's say I have an array A, 2, 3, 5, and I have an array B, which is, let's say 1, 4, 8. And I have to create a sorted array, right? Which is of size 3 plus 3, which is 6. 1, 2, 3, 4, 5, 6, correct? This is the eventual sorted array I have to contain or create. One thing is the first element in the sorted array is going to be the completely minimum of everything in the array, right? So given array A is sorted, minimum from array A is on position number 0, correct? Minimum from array B is also on position number 0. So therefore, whichever is the minimum of these two, I don't need to look at any other element. Whichever is the minimum of these two is going to be the first element in the sorted array. Is that something you all agree with? And what is the minimum of these two? Minimum of these two is 1. So 1 comes here. Now, if I have inserted 1 here, then it is as good as saying that now I remove 1 from B. It is the same thing, right? So what I just do is, how do I remove 1 from B? I just change this pointer to now point at this number 4. This is as good as saying that I'm now merging two arrays, one array which is A and one array which is B, but B is starting from this point onwards. And I again do the same thing. What is the next number that should come here? It should be the minimum of numbers here and minimum of numbers here. What is the minimum of numbers here? Array at this pointer. What is the minimum of numbers here? The array at this pointer. Whichever is smaller, which is 2, comes here, and this pointer moves one step forward. So in short, the approach becomes that you have 2 pointers. Let's say there's a pointer 1, which is for array A. There's a pointer 2, which is for array B. And you just say the following: while pointer 1 is less than whatever is the size of A, and pointer 2 is less than size of B, you do the following. You figure out which one is smaller. You just check. If A of pointer 1 is smaller than equal to B of pointer 2, then simple. This is what goes in the sorted array. So let's say sorted of, let's keep an index, A of pointer 1. You increment the pointer 1 plus plus because now pointer 1 has been assigned here. Else you put pointer 2 element here. So sorted of, again, index plus plus is equal to B, pointer 2 plus plus. The only thing is, when I'm done with this while loop, it is possible that all of the smaller elements are in one of the array. Imagine like this array was 1, 2, 3 here, and there were, let's say, 4, 5, 6 here. My pointer 1 will end up going here, and I'll end up breaking out where I've only filled in 1, 2, 3 in the sorted array. 4, 5, 6 is yet to be filled. So I'll have to check for that, which is at the end of this while loop, if whichever pointer is not done. So I just check while pointer 1 is less than size A, I just keep adding sorted of index plus plus is equal to A of pointer 1 plus plus. And very similarly, I do the same thing with pointer 2. While pointer 2 is less than size of B, same thing, sorted B of pointer 2 plus plus. Right. That will cause the merge to happen. Does this make sense? Right. Now, if that can happen, which means now if merging can happen, and what is the time complexity of this merge? Imagine I have 2 arrays of size n and n each. M plus n plus n, right? Like, so it takes me order n time to merge. If in fact the array A was of size m, this was of size n, it takes me order of n plus n time, right? That means if I have a order n array to be sorted, if I divide it into 2 parts, I say that sort the first part separately, sort the second part separately. Once they are sorted, then merging them will take me order of n by 2 plus n by 2 time, which is order n time. So merging them will take me order n time. Now, how do I sort the first half of the array? I can do the same thing with the first half as well. I can say that even to sort the first half, again break it down into 2 parts, and then sort the first half, sort the second half, merge it. With the end condition being that once I have an array of only size 1, it is already sorted. How about I modify this and I say that I have 3 arrays that need to be merged, right? Imagine I have an array 2, 5, 10. Imagine there is another array 1, 8, 9. And imagine there's another array 3, 4, 12. Let's say there were 3 arrays, right? How would you merge these 3 arrays into one array, which has all elements are sorted? We can do 2 at a time, but we don't necessarily need to, right? Like, we look at this, right? What is the first element going to be in the merged array? It is the smallest of all. Where does the smallest come from? It is either the first element from here, or the first element from here, or the first element from here. Whichever is the minimum from here, that becomes your smallest. So I can have 3 pointers. Pointer 1 pointing to the 0th element, pointer 2 here, pointer 3 here. Whichever is the smallest of these 3, which in this case is 1 comes here. And then all I do is I move this pointer 1 step to the right. And I again repeat the same thing. Whichever is the smallest of these 3, which is 2 comes here. And then 2's pointer moves 1 step to the right. Now again, 5, 8, 3, whichever is the smallest, 3 is the smallest, 3 comes here. And 3's pointer moves to the right. 5, 8, 4, 4 is the smallest, so 4 comes here. And its pointer moves to the right. 5, 8, 12. 5 is the smallest, so 5 comes here. And 5's pointer moves to the right. And then so forth, right? In the case of merge sort, it is only 2 arrays. An extension of the previous question. Then instead of 2, if there were 3 arrays, how do you go about merging 3 arrays? I mean, you can merge 2 arrays at a time. You can merge these 2 at a time, and then you end up merging these 2. But you'll end up using more memory, because to merge these 2, you'll need an additional array of size 6. Then you'll create an array of size 9. what I'm doing is I'm just directly creating an array of size 9 so that I reduce the amount of memory required to maintain that intermediate rearray. Also, I reduce a step. Okay, all right. Coming back to the merge sort. How does merge sort work? As the name suggests, it's divide and conquer, which is basically, now that I know that I have the superpower of taking two sorted arrays and merging them, what I can do is given an array A, I sort the first half. So sort A to 0 to n by 2, sort A of n by 2 plus 1 to n, and then merge these guys. That can become my approach. And this, how do you sort the first half? This also can happen in the same way, where you again divide into two parts, 0 to n by 4, and then n by 4 to n by 2, and again, then you merge, etc., right? And if I have to write code for this, it becomes fairly simple, which is, let's say if the question was, how do you sort array A from index I to index j? If obviously like the size of the array is already 1, which means if j is equal to I, let's just put that, then your array is already sorted, so you can just directly return. If not, then what you do is you basically sort the first half, which is you say, I'll go from A of I to mid, where my mid is I plus j by 2. Then I'll sort A from mid plus 1 to j. And once these two guys are sorted, then I will need a temp array where I'll merge the array from I to mid and mid plus 1 to j. And then I'll make sure that A of I to j becomes equal to temp. I'll just do that. But basically, I'm just applying recursion here. And what I'm saying is, if you want me to solve, by the way, let's say there are four numbers, right? 5, 3, 2, 6. Let's say those were the four numbers. I say that first sort the first half. So let me call the function to solve these two numbers, 5 and 3. Somebody sort this and then give it to me. And then sort the second half separately. So somebody sort 2 and 6 and give it to me. And once I have them sorted, then I will actually merge them, right? Now to sort 5 and 3, I again do the same thing. I split it half. I say somebody sort 5 for me and somebody sort 3 for me. Here also somebody sort 2 for me and then 6 for me. Once they are sorted, then I'll merge. 5 is sorted, 3 is sorted. How do I merge? In my merge step, the same way we had seen, we have two arrays. We have to merge. When we merge, this will become 3, 5. And that is what I replace my original array with. So this array becomes 3 and 5. Very similarly, 2, 6 remains 2, 6. And then once I have 3, 5 and 2, 6, then I merge them to find 2 comes first, then comes 3, then comes 5, then comes 6. And this becomes my actual sorted array, which I replace this with. Just out of curiosity, why do we divide them into equal halves? Although in the end, we move two single elements and merge them in sorted order. Can't we take pairs in the array and do the same way of merging? Let's say I have more numbers, right? So imagine I had 5, 6, 8, 1, 2, 13, 15, 12, 3. How many do we have? We have 4. And let's imagine I remove 12 from here. Question is, if we have to sort anyway, why don't we take pairs by pairs, right? So let's just take pair 5, 6, 8, 1, 2, 13, 15, 3. And let's just first sort them. So we end up sorting them. And for example, we end up finding that this is 5, 6. This becomes 1, 8. This is 2, 13. And this becomes 3, 15. Right. Now, the problem is like we've done pair-wise sorting, but the array is still not sorted. Then we'll have to do sorting of 4 elements each, right? How do we do that? We say that, you know what, like there are first 4 elements here. The first half is sorted. The second half is also sorted. Let's merge somehow, which again, I'll take another array and then I'll merge, etc. So this will get sorted. Then I'll do again the same thing, which is I take 4 elements, half is sorted, and I'll do the same thing. And then finally, I'll look at all of the 8 elements. So you're going just in the reverse order. What I just said, you're just going in the reverse order, which is also correct. It's just harder to code because the previous approach can be coded using recursion, which I'll just show. In your approach, what you're doing is you're building bottom up, right? Like you're sort of saying that let's first sort all pair of elements. Once they are sorted, then let's look at all 4 size elements. Great. Once they are done, then let's look at all 8 size chunks. Once they are done, then look at all 16 size chunks and then 32 size and then 64 and so forth. Right? And finally, I'll have the entire array sorted, which works. It's just harder to code. What I said was the other way around, that instead of going from 1 to 2 to 4 to 8 and so forth, let's start from n. Let's divide that into n by 2 parts, then n by 4, then n by 8, and I'll finally reach the 1 part anyway. And then my recursion function will keep returning and I'll have the eventual answer. So if you look here, my recursive function, this will do the same thing. My recursive function here will also do the same thing. Let me also just write it as merge step. So what is happening is, if I have an n-sized array, I'm dividing it into two arrays of size n by 2 each, n by 2 each. I'm sorting it using the same methodology, which is this n by 2 will create arrays of size n by 4, n by 4. Here also, again, same, n by 4, n by 4. These will create arrays of size n by 8, n by 8, again, n by 8, n by 8, same thing. And this n by 16, n by 16, and so forth. How many levels will you have here? I mean, we go from n to n by 2, n by 2 to n by 4, n by 8, 4 to n by 8, n by 8 to n by 16. How many levels? Log n levels, right? So in every level, n is becoming half of what it was. As we have seen the same pattern in binary search, etc., etc. I mean, as you go, if n is becoming half of what it was, it takes you log n steps to finally come to 1. At every step, what is happening? At every step, basically, I have n by 2 sorted array. I'm merging them, which takes me order n time. This takes me order n time. N by 2 plus n by 2 and order n. What happens on this level? These two guys merge and it takes them n by 4 plus n by 4, which is n by 2 time. These two guys merge and it takes them n by 2 times. If you add them up, it will take you order n time on this level as well. Very similarly, on the other level as well, where you have n by 8, there are 8 instances of n by 8. It will again take you order n time. So the total time taken on every level, it takes you order n time. There are log n levels. The total time taken is n log n. That is an intuitive way to understand. I can also explain the mathematical way of explaining this. But the intuitive way of understanding the time complexity of merge sort is that on every level, you're doing one merge. The merge is order n. Number of levels is log n. And therefore, in fact, if you look at Arvind's approach, if you were to implement it, in every iteration, what you're doing is you're first creating pairs and you're merging the pairs. Takes you order n time. Then you're looking at all four blocks, right? Like blocks of 4 each. In one order n operation, you will have sorted blocks of 4 each. Then in again one order n operation, you would have sorted blocks of 8 each. And you'll keep doing that till you cover the entire array. So the number of steps to cover the entire array would be log n. And every single iteration is an order n iteration. So it takes you an order of n log n. I can explain the math behind it as well. Is it n log n in every case? Best case is, sure, I mean, you can probably put an optimization that if the array is already sorted, if a half is already sorted, you don't need to do all of the splitting, etc. So best case, you can still make order n. But yes, worst case is order n log n. Worst case, it takes you order n log n. And you can put a check to make sure that you're not doing the entire splitting, etc. if the array is already sorted. All right. What is the space complexity of merge sort? So if you look at the implementation here, we are allocating this additional memory temp to calculate this merged part, right? Why? Because when we are merging two sorted arrays, we need this temporary space where we put in the result, which is not a part of the original array. This is additional space. If I have to look at this tree, in this n by 2 part, I would have taken a temp array, which was of size n by 2. Here, I would have taken a temp array, which was of size n by 2. In fact, let's look at total space allocation, right? So this n by 2 will make a call to n by 4, 8, etc., etc. So this is a log n stack memory space. Plus, in each of these, so imagine I was sorting this array of size n. This will end up calling for n by 2. This will end up calling for n by 4, n by 8, and so forth. In each of this, I would have a temp array allocated, which will be freed as long as, I fill it back, right? So this temp array here is of size n by 4. As soon as I'm done, then this will be freed. Then I come back here. Here it will be of size, additional size of n by 2. As soon as I'm done, it will be freed. And then I'll come back here and I'll have a temp array additional size n. So maximum space that I end up using additional is I have log n stack of recursion, plus I have this additional order n size array that I might have used, which is my temp array. So order n extra space is what we end up using apart from the array space. So space complexity becomes order n. time complexity becomes order of n log n. There's one more way to, by the way, calculate time complexity. I mean, if you assume that the time taken for sorting an array of size n is tn, then tn is nothing but, I'm saying, first sort array, first half of the array, then sort second half of the array, which is also of size n by 2, and then merge them, which is, it takes you some n time. Let's say it takes you n time. This is basically saying 2 times t n by 2 plus n, right? If you break it down further, your n by 2 is 2 times t n by 4 plus n by 2, which is the same as 4 times t n by 4 plus 2n, which you'll see will finally come to 2 to the power I t times n by 2 to the power I plus n into I. I mean, this is just a little mathematical. Therefore, I explain the intuitive way first. Which, I mean, if you want this to become equal to 1, I becomes log n. So you have n into t times 1 plus n into log n, which is n log n. This is how Master's theorem actually works. I'm just elaborating that, expanding that equation. Even if you don't know about Master's theorem, that is fine, as long as you understand the intuition of why it is n log n. Because in the recursion tree, there are log n levels. On every level, I'm using order n time. So time complexity becomes order of n log n. Space complexity becomes order of n. Is there any way without using the extra space? So actually merging two sorted arrays without using extra space in order n is not possible. That becomes the blocker, right? So if you can merge the array in place without using extra memory, then your problem would have been sorted. But the problem is, like, merging without extra memory is the issue. All right, does this make sense? Merge, sort, space complexity, time complexity, all of that. All right. Today we'll be talking about quicksort, and today we'll be solving a lot more problems actually. By the way, I just wanted to maybe also share one news with all of you. Today was the first case when one of the fellow students at Scalar has gotten an offer as a CTO at one of the energy companies, which is a fairly big company now, right? And that the reason why I'm sharing this with all of you is to show you that, look, I mean, learning matters. I mean, and like, again, I can't disclose the exact salary of the person, but it is in a few CRs. We're not talking about lakhs, right? So the thing that matters at the end of, I mean, that is basically the North Star for all of us. He's 30 something, but like, we all should focus on the learning aspect. As long as we do that, eventually all of us will succeed. We'll go and build really, really great things in the future. He is part of Scalar Academy and not Scalar Plus. And I can't disclose the name of the company. I'm sure like that news will come out later on. It will be shared with all of the community as well. Once he joins, it's still sort of confidential. But just letting you guys know, I mean, look, it is important that all of us focus on learning. As long as we do that, I mean, obviously, like, what you find later on is going to be a function of what you know at present, plus like some bit of experience. I mean, so again, just to also elaborate, this person is not somebody who is very young. As I said, like, he's 30 plus, already has more than 7-8 years of experience, actually has more than 10 years of experience. But as long as you keep learning the right things, you'll keep moving forward, right? And that is, all of us should just aspire to become 1% better every day. That being said, back to what is the agenda for today. Today, we're going to actually talk about one sorting algorithm, which is actually used in most libraries that you use, be it in Java or Python or C++. The sort function that you use, they all use a different algorithm, which we will talk about today. But instead of talking about the algorithm, which is, I believe, not the right way to introduce a concept, what I'm going to do is I'm going to give you a problem, a real life problem that you may take an attempt at solving. And then we'll use that to maybe introduce the approach. So imagine this. Imagine you have a bunch of nuts and bolts. You have nuts and bolt, right? So nuts basically look something like this. And then you have bolt that is basically a circle that fits into the nut. The nuts and bolt, and usually like they're created in pairs, right? So you have a nut of a size and then the bolt actually clearly fits. If the nut and bolt are of the same size, then they fit. Now imagine you have a lot of nuts and lots of bolts, and you are given that every single nut is of unique size. It is every single nut and bolt are of different sizes. So none of them have the same size. And you're also given that every nut has a corresponding bolt. One fact that is given is every nut has corresponding bolt, which means they both fit each other. Two is no two nuts have same size. So they are all different sizes. However, it is very hard for you to just visually differentiate which one is bigger or which one is smaller. So what do you do? What you do is, like, if you pick a nut and you pick two bolts, if the bolt is loose, then you know that the bolt is bigger. If the bolt is not going in, then you know that the bolt is actually smaller. Now the problem is, given that info, can you sort all of the nuts and bolts in increasing order of their size with the right nut and bolt paired up? Currently, they are all just in disarray. You have a table full of nuts and bolts. You don't know which one is paired up which one, right? One is, how can you arrange that? And two is, how can you do it as fast as possible? Let me explain again, right? So imagine this. Let's say I had only two nuts. Imagine I had this nut, another nut, and I had another bolt, and then another bolt, right? Now, what I can do is, I can pick, let's say, this particular one, and I pick this one, and let's say I try to match them. There are following things that can happen. One is, these guys clearly fit. In that case, I know that this nut is to be paired with, let's just call it bolt 1, bolt 2. This is nut 1, nut 2. If they fit, then I know these guys are in the pair. They belong together. And then I can just compare the other bolt. If it is smaller than this particular nut, then it goes before this nut, right? If it is smaller, otherwise if it is bigger, it goes after. And then I definitely know that the pair for this bolt is this nut, right? So I just put these two guys together, either after or before, depending on how it compares with this current nut. So if I have to define the problem formally, you can pick a random nut, an X, and you can pick a random bolt. If you pick these two guys, you will get either of the following result. Either you will get nx is equal to by, which means both of these guys belong together, or you will get to know that, by the way, this nut is smaller than bolt, or you will get to know that nut is bigger than bolt. These are the three results you can get. You cannot compare nut with nut. So for example, I cannot get nx and ny and compare these guys. I can't. Similarly, I can't compare bolt with bolt. This I can't do. This I can't do. However, I can take a random nut and a random bolt and I can compare them. Does that make sense now? It does, right? Now, I mean, the question is, how do I sort these guys? How do I sort these guys? When I can't really compare a nut with a nut and a bolt with a bolt. The bolt size is not given to you. I mean, think of it like this, right? You have a table which is full of these nuts and bolts, and there's only minor variation in the size. What you should end up with, for example, in this case, imagine that these guys were equal. N1 and B2 was equal. So I would put N1 and B2 together and assume that B1 was smaller than N1. So I would put N2 and B1 before this. And I will return this list. N2, B1 as the first entry, N1, B2 as the second entry, right? So if you just compare with a bolt with a nut, you do get the relation, whether a nut is bigger than a bolt or not. So imagine if this nut was paired with another bolt, BZ, then you know that BZ is actually smaller than BY. So you can compare the pairs by picking nut from one pair, bolt from another pair. There is no size given. The only way is you just pick a random nut and bolt and then compare whether one is smaller than the other or not. Let's actually look at how do we do that, right? So one is, if I pick any random nut, let's say if you're given, let's say n different nuts, let's say I pick some random nut. Let's call that nut N1, right? What I can do is, now I have a bunch of bolts. I have B1, B2, B3, B4, B5 till Bn. I can compare each of those bolts with this N1. And I'll basically get three kinds of bolts. There will be one heap of bolts which are lesser, right? So there's one heap of bolts which are smaller than N1. There is one heap of bolt that we will get. Let's call this bolt bigger, which is bigger than N1. And there is exactly one bolt that I will get, which will be equal to this nut, correct? If I compare all of the bolts with this nut, I'll get three sets. One bolt which is equal, and then a set of bolts that are smaller and set of bolts that are bigger. How these guys compare amongst each other, that I don't know. But essentially, I do know which bolts are smaller than this nut, which bolts are bigger than this nut. That you guys all agree with? So if I pick any random nut, I can distribute all of these bolts this way. And very similarly, now that I know that this bolt is the same as this nut, so I can pick all of the nuts, which were N2, N3, N4, N5, N6, N7, N8 till N. And I can say, let me compare all of these nuts with this bolt, right? I'll get some nuts that are smaller. So I'll basically have some of these guys. If I compare with this bolt, I'll get some nuts here. Let me take a different color. Some nuts here, which are smaller. Some nuts, which are bigger. The equal one is already here. So you'll not find anybody who's equal. So what we have done is we first started with one nut, right? And then we use that to break all of the bolts in three parts. One bolt which is equal, a lot of bolts that are smaller, a lot of bolts that are bigger. And then once we found the equal bolt, we use that bolt to actually split the nuts, remaining nuts, into two parts, smaller nuts and bigger nuts. Now what I know is all of the bolts, smaller bolts, will have their corresponding nut somewhere here. I mean, basically now I have three sets, right? I have a set of nuts and bolt which are smaller, and they are guaranteed to be present in pairs here. Same guarantees holds here. Then I have one pair which is N1, B1. And then I have set of nuts and bolt that are bigger. Now I can actually recursively sort this set separately, and I can sort this set separately. But my problem has now reduced to sorting smaller set of nuts and bolts. And if obviously if the set only had one element, then I know that they are already sorted. I don't need to touch them. This is exactly how quicksort works. I'll introduce it very, very shortly. But let me take a few examples just to show how is this working. And that will give you a sense of or sort of some intuition behind how quicksort works. So imagine I was given some random, let's say N1, N2, N3, N4, N5 nuts. And let's say I had random 5 bolts as well. What I'm going to do is I'm going to mark, let's say hypothetically, what the process is going to be like. So what I'll do is in step 1, I'll pick this nut and I'll say, let's compare it with all of these 5 bolts. And we'll find some bolts that are bigger, some bolts that are equal. Imagine, hypothetically, let's say N1 was equal to B3. And imagine that B2 and B4 were smaller bolts. And we found out, let's say that B1 and B5 are bigger bolts. Very similarly, then what I did was that I picked B3 and I started comparing B3 with all of these guys, N2, N3, N4, and N5. And I would come to know whether they are bigger than B3 or smaller than B3. All of the bolts, again, let's say hypothetically N2 and N3 were smaller, and let's say N4 and N5 were bigger. Now the problem becomes that I know that N1, B3, whenever I sort, is going to be the third element in the set. I have 2 elements before. I don't know their order, but those 2 elements have basically B2, B4, N2, N4 as 2 pairs. And I have 2 elements after, which is B1, B5, N4, N5 that are yet to be sorted. That is after, right? However, this portion is fixed. I don't need to change this portion. It is in the right position. It is where it should be. I do not need to change this position. This is already in its correct position. So then what I do is I recursively sort the first half. And then once this is sorted, then I'll go to the second half. How do I sort the first half? I again do the same thing. I say, let's pick a random nut. Let's say I pick N2 as the random nut. And I compare B2 and B4 with it. Oh, sorry, this should be N3. So B2, B4, N2, N3, B1, B5, N4, N5. Right. Okay. So then let's say pick N2 as the one nut, right? And I compare B2 and B4 with it. I know that I don't need to compare B1 and B5. They're definitely bigger. I'll deal with them separately. I'm only concerned with sorting these 2 pairs. So I compare B2 and B4. And hypothetically, let's say I find that N2 is the same as B4. So I find these guys are equal. And hypothetically, let's say I find that B2 was bigger. I know that B2 will be paired up with N3. So I put it as it is. These guys are sorted now. Then I have N1, B3. And I do a very similar process here as well. I pick any one of these guys. Let's say I pick N4. And hypothetically, let's say N4 pairs up with B1. And I find that B5 is smaller. So therefore, B5 will come here. The pair of B5 is N5. That will come here. So this becomes your sorted array totally. Now this process where I actually picked one element and I started comparing all of the remaining elements with it is called choosing a pivot. So while this is a more complicated case, let me take an example of sorting an array of integers. And I'll show you with that. Imagine, let's say my array was 5, 2, 1, 8, 6. N1 or B3 is largest. That means this set does not exist. The set is empty. But the remaining set is still smaller set than what you began with. it has now n minus 1 bolt and n minus 1 nuts. So you still have a smaller problem to solve. So in every step, you're reducing the size of the problem. So that is actually your worst case where you will end up taking n square time. But still, I mean, that still gets you to your answer. So at each step, one of the pair comes at its right place. Let me just elaborate that with this array as well. So in the quicksort process, what you do is you pick one element, any random element, to be the pivot. For example, I say that I want to pick 5 as the pivot. So what you do is, the first part is you count how many numbers are smaller than 5, right? So you basically, let's say, have 2 is smaller, 1 is smaller, 8 and 6 are not smaller. That means the right position of 5 is the third position because there are 2 numbers smaller. So what you do is you put 5 here. 1 probably comes here. So your array is basically 1, 2, 5, 8, 6. And then once you have put 5 in the right position, then you compare all of the remaining elements. What you want is all of the smaller elements are on the left side, all of the bigger elements are on the right side, which in this case has automatically happened. But in case it wasn't, what you would do is you'll start from here and you would start another pointer from here. The first number that you find on the right side, which is actually smaller than 5, you'll stop there. You'll try to find the first number from on the left side, which is actually bigger than 5. You'll stop there and then you swap those two guys. So in order n, you'll be able to get to a place where all smaller numbers are on the left side, all bigger numbers are on the right side. And then the problem becomes that 5 is in the right position. Now, as long as I can sort the left side of the array and right side of the array separately, my entire array will be sorted. And that I can again do recursively. So in every step, when I choose a pivot, one number will come at the right position and it will divide the remaining array into two parts, two smaller subsets that need to be sorted. Do we have to take pivot as the middle to make the swap easier? I mean, so if the thing is when you're choosing the pivot, you don't know which one is the middle element. I mean, you basically start with choosing a random number as the pivot in the array that you have to sort. If you are unlucky, then it would turn out to be one of the numbers, which is either the highest number in the array or the smallest number in the array. If you are, I mean, if it is just very, very random, chances are you'll find a pivot somewhere towards the middle. I mean, let me actually go step by step. Does the nuts and bolt approach make some sense? Basically picking one nut, comparing all of the bolts with it to divide them into smaller heap, bigger heap, equal to, and using the equal to bolt to divide the remaining nuts into a smaller heap, bigger heap, equal to. And I know that the equal to part is in the right position. Now I need to sort the smaller heap of nuts and bolts separately, bigger heap of nuts and bolts separately. Let me take another example of this. Actually, here there was a swap. Let's see what kind of thing we can do where we would need a swap. Imagine I still have 5 as the first element. Let's say there is 6, 8, 1, and 2. Hypothetically, let's say this was the array. And again, we chose 5 to be the pivot. If 5 is the pivot, the first step, let's count the number of numbers smaller than 5. 1 and 2. So that means 5 should come at position number 3 in the array. So 5 should come here. So what do? The quickest way is I just swap, right? So I just bring 5 here. I bring back 8 here. So 5 comes here, 8 comes here. I remove the circle. Now I know 5 is the pivot. What I want is all smaller numbers should be on the left. All bigger numbers should be on the right. Right now it is the opposite. So what do? I say that I'll start with a pointer on the left side. Let's call it start pointer. I'll also start with a pointer on the right side. Let's call it the end pointer. Or maybe we can just call it left and right. Both are also okay. Left and right. I compare the first number and I see whether it is in the right half or not. In the correct half or not, right? So 2 is smaller than 5. It should have been in the left half. So it is not in the correct half. So I make my right pointer wait here. My right pointer is currently pointing at 2. Very similarly, I start a loop on left to find the first number which is not in the correct half. In this case, the first number that I find, which is 8, is not in the correct half because 8 is bigger than 5. It should have been on the right half. And then the first place wherever left and right is, I just swap them. So essentially 2 comes here, 8 comes here, and I now know that these two guys are in the right half. So then I again start moving my left till I find the next number which is not in the right half, which is 6. So my left will wait at 6. Very similarly, I start moving right to find the next number which is not in the right half, which would be 1, and I'll just wait at 1. And then I end up swapping 1 and 6. So 1 comes here, 6 comes here. So your right pointer will move from this position to this position, and your left pointer will move from this position to this position. If you add these guys up, you'll get total sum as n minus 1, n being the size of the array. This will help you shift all smaller elements to the left of the array, bigger elements to the right of the array. So if I have to write the steps of quicksort, one is choose any number randomly as pivot. And then once you have chosen a pivot, put pivot in the right position. For calculating the right position, you'll have to count numbers smaller than pivot. So this is one order n iteration. Third thing that you do is using left and right pointer, shift smaller numbers in left half, bigger numbers in right. So the fourth step is sort left part and right part separately. Can be optimized by choosing the correct pivot. The most optimal pivot is your median, basically a number which can divide the array into two equal parts. That is the best pivot, right? Because then you're left with smaller arrays to sort. It is obviously faster to sort smaller arrays. However, the problem is it is very hard to know what is the median of the array. Why would you want to spend a lot of time finding out the median? So what quicksort says is, as long as your pivot choice is completely random, if it is completely random, then you're still fine. Average time complexity will still become n log n. All right. What is the approach behind quicksort? Quicksort is essentially choose a pivot, divide the array into smaller numbers, bigger numbers, sort the smaller number separately, sort the bigger number separately. Your array will automatically be sorted. Divide and conquer. Most of the library functions that you use, they use quicksort and they choose pivot randomly. I'll explain why randomly still works here. The one thing which you will notice is in this entire process, we have not used any additional memory. We did the swapping, etc. in place. So we have not created a duplicate array. All of this is happening inside the same array. That is important because while merge sort also is order of n log n, which we will see with quicksort, merge sort uses additional space, or it requires this separate array where you merge the two arrays, which is additional memory required. So one of the reasons why merge sort is not used extensively, but quicksort is used extensively, is because quicksort does not use additional space. The worst case of quicksort is still really bad. Collections, you also use quicksort. Now, since we don't have random access, how does it work? For example, if you use what you're saying is, let's say if you have implemented the list with a linked list, then how would the quicksort sort of work there? Because here, if you see in the quicksort, you're not really doing random access. All of your access is still sequential, right? For example, let us go step by step. We say let's choose any number randomly as pivot. I can take a loop till the number because I'll still anyhow have to take an order n loop throughout the entire list to count the number of numbers smaller so that I know what is the right position. I'll have to do that anyway. So I take a linear loop to get to the number. That's fine. I take a linear loop to find out the right position. And again, I do the same thing. I anyhow have to split the numbers into left and right pointer. I can take a linear loop for that. So in all of this case, if you see, I'm not doing any random access. I'm actually going step by step in a linear loop. Let's do what is the time complexity analysis. Let's do what is best case, what is worst case, and what is average case. What is the best case with quicksort? What is the best pivot you can choose? Assuming that the array is not already sorted, what is the best pivot you can choose? Median. Let's say you were very lucky and you were choosing the middle element all of the time. What would happen is if you were given an array of size n, you would put the median in the right place. So median would be in the right place. And then you'll have an n by 2 size array here, n by 2 size array here. You'll need to sort these separately. So what happens is exactly like merge sort. You start with an array of size n. This reduces to sorting array of size n by 2 twice. One on the left side, one on the right side. That becomes, basically time to sort an array of size n is the same as 2 times tn by 2 plus order of n for merging. And this basically comes to order of n log n. So if you are choosing the median as the pivot all of the time, then you end up sorting it in order of n log n. If you are choosing the median as the pivot every time. And by the way, this is probably not the best case. Best case is in the array is already sorted. Best case meaning that if you're given an array and then your median is the best, right? So you end up sorting in order of n log n. What is the worst case? What is the worst kind of pivot you can choose? One end. When your pivot is actually on one of the ends. So what happens is in one step, in order of n, what you would do is you'll end up choosing a pivot that is on one end. So your pivot is here and you'll find all of the other remaining n minus 1 elements are on one side, which means that in one order n loop, you have only fixed the position of one element and you still have n minus 1 numbers to be sorted. And if you keep doing that again and again, if you're extremely unlucky, your time to sort will become n plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4, which is order of n square. So your worst case becomes order of n square. If you are very, very unlucky that you're choosing the extremes as your median all of the time. Does this make sense? Why is the best case order of n log n? Why is the worst case order of n square? Just in terms of how we choose the pivot. If we are really, really good with choosing the pivot, then we end up choosing the median as the pivot. That means it divides the array into two equal halves, which is exactly the kind of thing that we did in merge sort, right? Like you start with an array of size n, you end up with two equal halves of size n by 2 each, which you have to sort, which again will split further into n by 4 if you again choose median. This tree will have log n number of levels. On every level, you're doing order n operation. So your becomes the best case. If you're choosing the best pivot, then it becomes n into log n. If you are choosing the median as the pivot, then you'll have order of n log n complexity. That is clear to everybody, right? Okay. What is the worst case? Worst case is when you're choosing one of the pivot. Your time to solve or sort n sized array is in order n, you were able to fix the position of one element. The other n minus 1 still need to be sorted. And if I just expand on what Tn minus 1 would look like, it would be n minus 1 plus Tn minus 2, which is what? N plus n minus 1 plus, what is Tn minus 2? N minus 2 plus Tn minus 3, which if you keep adding up will become n square. I was not talking about the best case really. I was talking about given an array. If let's say I had flexibility on what I choose as the median. So what kind of pivot? What kind of pivot will give me the best complexity? What kind of pivot will give me the worst complexity? That was what I was looking at. Right. So what is the average case complexity? One algorithm that I wanted to address, which is called bucket sort. If you guys remember, we did something called a count sort, right? Which is when the elements were in limited range. We would just count the frequency of elements and that would help us sort. Bucket sort is a slight variant of that. Variant being that if I can categorize numbers into buckets where I know that the buckets are sorted in some fashion, then the sorting problem becomes easier for me. Radix sort is exactly bucket sort. For example, hypothetically, let's say you had a lot of numbers. So let's say I had 456, 923, let's say I had 150, let's say I had 268, and let's say I had 12. And maybe I also have 950. Now imagine I was to create 10 buckets. 10 buckets. Bucket 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Which is for the most significant digit of the number. Let's say the 100th place of the number, assuming that all of the numbers are smaller than 1000. They can be 1 million, 10 million as well. So then we'll choose the most significant bit and we'll keep it the same position for all numbers. If I do that, then I know that 423 will go in the fourth bucket. Most significant digit is 4. Most significant digit here. Assuming for all of them, the most significant digit that we're looking at is the third digit from the back. So 923 will go in the 9 bucket. 150 will go in the 1 bucket. 268 will go in the 2 bucket. 012 will go in 0 bucket. 950 will go in the 9 bucket. What I know is now if I start going bucket by bucket and I have sorted the numbers within a bucket, if I have sorted the numbers within a bucket, and if I just start picking numbers from here and appending them, then I end up getting the entire array sorted. Why? Because I definitely know that any number that is starting with 0 is definitely going to be smaller than any number starting with 1. So dividing them into buckets and then sorting the buckets within themselves, sorting the numbers within a single bucket, that helps me reduce the complexity to some extent. And I'll show you an example of that to a major degree, which is what is called as radix sort. But the idea is if I can break them into buckets where buckets already have some ordering defined, then my job becomes just simply appending the numbers in the buckets, and that might give me a sorted array. And I'll give you a few examples to sort of talk about what bucket sorting is. And we'll do one problem on bucket sorting as well, which is a hard problem, but we'll do that. What kind of data structure can I use for buckets? Think of them as, for example, vector of int. So for example, your v of 0 is a vector of numbers. V of 1 is also a vector of numbers, and then so forth. So the concept of bucket sort is very simple. If you can split numbers into buckets, where buckets themselves are ordered in some fashion, then I can sort numbers within the buckets, and then I merge them. That gives me a sorted answer. If numbers are not on the same order, how do we put them in bucket? So even here, if you see like 12 was not of the same order, I just added another 0 to get it to the same order. So imagine I have numbers as 950, 1, 12, 923, 256. I'll just add 0 to make sure they're all of same length. How do we keep the value sorted in one bucket? Within the bucket, just use quick sort or whatever kind of sorting you want to use there. Insertion sort, quick sort, whatever you want to use. Let's take an example. Bucket sort alone isn't enough. Bucket sort paired up with a few observations is actually very powerful. So one observation that leads to sorting algorithm is called radix sort. The way radix sort works, imagine again you have a bunch of numbers to sort, right? Again, I'll pick the same thing, which is, let's say I have 923, 950. Let's say I have 12. Let's say I have the number 1. Let's say I have number 100. Let's say I have 150. Let's say I have 650 and 688. Hypothetically, let's say I have a bunch of these numbers. So what radix sort says is, look, at the end, if I was at the end, let's make all of these guys equal length. So add zeros wherever applicable. If all of these numbers are of equal length, then at the end, most significant bit, this bit, is the most important bit. Obviously, if the most significant bit of one number is smaller than the other number, then the overall number is definitely smaller. It is only a problem when they both are equal. Then I will look at other digits. So I know that. So what I want to do is I want to start sorting digit by digit, with most significant digit being the last place where I sort, because I know this is the final step. So what radix sort does is it says, let's start with the least significant digit. Let's first sort based on this. And what do? I basically create, again, 10 buckets corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I will first look at the last digit. Based on that, 923 goes here, 950 goes to 0, 012 goes to 2, 001 goes here, 100 goes to 0, 150 goes to 0, 650 also goes to 0, 688 goes here. And then I append these guys, right? What will happen once I have done this step? All of the numbers will be sorted by their last digit. So I get 950, 100, 150, 650, 001, 012, 923, and 688. I sorted numbers based on their last digit. Now let's look at the next digit. I repeat the same process again, but with the next digit now. I'm going to erase all of these guys from here. We are now going to look at the second digit. I say that now let's look at these numbers again, one by one. But the second digit is what we are looking at. So 950 goes at 5. 100 goes at 0. 150 goes again at 5. 650 also goes at 5. 001 goes at 0. 012 goes at 1. 923 goes to 2. And 688 goes to 8. I'll again append these guys. What this would make sure is now everything is sorted based on the last two digits. So I append, and when I append, I basically get 100, 001, 012, 923, 950, 150, 650, and 688. And now the last step is the magic step, which is where I look at the most significant bit. So I erase all of this again. I look at the most significant bit and I bucketize these guys based on the most significant bit. So 100 comes here, 001 comes here, 012 comes here, 923, 950, 150, 650, and 688. Now, once I append them, all of the numbers should be sorted, which you would see 001, 012, 100, 150, 650, 688, 923, 950. Now this final array that we've gotten, this is sorted. What has happened? We can take MSB directly. The only problem is then within the bucket, if you have multiple numbers, and think of like when you have a million numbers, right? You only have 10 buckets based on MSB. That means every bucket on average will have 100,000 numbers. And if you go to solve or sort of sort each of those buckets separately, it will take you a lot of time. But here, I can sort the entire array by doing this function, the number of digits, number of time. So imagine all of the numbers had 5 digits. I'll do this operation 5 number of times and my entire array would be sorted. For every single digit, I am putting them in buckets, 10 buckets, and then I'm appending them, which is an order n operation, right? So my total amount of time taken is order n into max number of digits. Space is assuming that we are taking a vector of vector. The total space taken by vector of vector combined across all of this is order of n. So I'm using an order on n extra space. Actually, order of 10 plus n, which is order n. Do we need to compare an element with the existing elements present in the bracket? No. Right now, because the moment you start doing that, then your complexity increases. Currently, it is just very dumb way of appending to existing numbers in the bucket. Why can't we take MSB to LSB? I mean, when we start with MSB, in the first step, we would definitely have put the bigger numbers to the first half of the array, the smaller numbers to the second half of the array. That I completely agree with. In fact, numbers would be sorted based on their first digit. But as you go to the second digit, within these numbers, if the sorting is happening in the right way or not, because you'll have, let's say you look at second digit as 0, right? Now, some of those 0 numbers will come from the numbers that had the first digit as 9. Some of those 0 numbers will come with some numbers where the first digit was 6. For example, let's look at this example itself, right? If I started from MSB, then what would have happened? Let me erase this. My first 2 numbers will go in the 9 bucket, 923, 950, 012, 001, 100, 150, 650, and 688, which is great. Now, if I append them, then I get this, which is almost sorted. The problem is when I move to the next digit, it's then that it becomes a problem, because 012 will come here, 001 will come here. Now 100 will also come here. However, I know that 100 should only come after 012. When I'll merge, then I wouldn't know how to maintain this ordering. I mean, I'm using digits here. You can do the same thing for bits. There you will only have 2 buckets, 0 and 1. Here I have 10 buckets. You'll only have 2 buckets when you're dealing with bits. When you go from LSB to MSB, that means MSB takes higher priority because it is the last deciding factor. When you go from MSB to LSB, then LSB starts taking higher priority. So time complexity is n into number of digits. If d is the number of digits, that is your time complexity. Usually, the number of digits is the same order as log n. It's actually log n to the base 10. N being the maximum number in the array. Number in array. So, I mean, usually radix sort is good number to know and good approach to know because this can be applied at multiple places. That being said, again, like not very commonly used because n log n, you can just directly use your sort function. Why would you go and take the pain of implementing radix sort when it has very similar time complexity? If all of what we have discussed till now, if that makes sense, I'll give you one problem which will actually make the bucket sort even clearer. The reason why we have bucket sort. Explain the time complexity again. So if you look here, what are we doing? We are taking digit by digit, right? So first we look at the last digit. And for that digit, what do? We put them in these 10 buckets, right? So basically what happens is, what is the last digit of any number? Let's say I do this, right? I say I goes from 0 to n and we calculate the last digit. Digit is equal to array of I mod 10. That is your last digit. And then you put it in the same bucket. So for example, let's say if you have bucket array, you say bucket of digit dot add AI, right? You do that. All of this is order n process for the last digit, correct? And then eventually I'll basically look at numbers in every bucket and I'll keep appending them in another array. All of this is order n process. I'll have to do this for every digit, correct? So if all numbers have, let's say 5 digits, then my complexity would be n into 5 because for every digit, I'll do an order n operation. If every number has d digit, then it becomes order of n into d. How n log n is similar to n into d. So n into d makes sense, right? Order of the algorithm is n into d. That makes sense. Correct. Okay. Now what is d? What is given a number x, what is the number of digits that x would have? How do you find that? Basically, how do you find number of digits? You basically divide x by 10. You check if it is 0 yet. Then you again divide it by 10 further, which is 10 power 2. Then you divide x by 10 power 3, x by 10 power 4, 10 power 5, and so forth, right? When x by 10 to the power I is 0, which is like now 10 power I has become bigger, then that is where you have the number of digits, okay? If I just put it like this, I mean, basically, if x has I digits, then x is approximately equal to 10 raised per I. Approximately, which means if I take log 10 on both sides, then I basically get I is equal to log of x. That you agree? So if there is a number x, then x has basically log base 10 x number of digits. So therefore I'd say like whatever is the highest number in the array, then d is basically log of that highest number. So your D is almost the same as n log x, x being the highest number. So bucket sort is more generic, right? Like bucket sort just says, hey, look, my fundamental is you can create any sort of bucket you want. You can create a bucket of all numbers from 1 to 100, all numbers from 100 to 1000, all numbers from 2000 to 3000. You could create any bucket that you want as long as it covers all range. You put numbers in the bucket where you know that every number in bucket 1 is going to be smaller than every number in bucket 2. So you just bucketize these numbers, you sort them separately, and then you append. That becomes bucket sort. It is very generic. Radix sort is using bucket sort in one way. Why this type of bucketing works? Going for all positions instead of just MSB or LSB. Let's say if you just go for MSB, there wherever two numbers have different MSB, most significant digit, there, I mean, you probably can only do with most significant digit. The problem is there will be a few numbers that will have the same most significant digit. In fact, there are only 10 possible most significant digit, right? So if you have, let's say, 1000 numbers, then on average, you will have 100 numbers in every bucket, right? For example, here as well, I had 950 and 923. They'll all go to the 9 bucket. Now, how to actually decide the ordering between these? In fact, if you have a lot of numbers in the bucket, then how do you figure out the ordering between those? That is not clear. So therefore, you can't decide only based on most significant digit. You'll need to somehow sort these guys within the who have the most significant bit as 9 as well, right? Internally, you'll need to sort them. So there are two ways. One is like you just say, I'll bucketize based on the most significant digit and I will sort each bucket, right? So what happens is if I had n numbers, then on average, each of the buckets will have n by 10 numbers. To sort them, I'll take n by 10 log n by 10 and I'll have 10 such buckets. So I'll finally multiply by 10. This will give me n log n by 10, which is the same as n log n. So I end up reaching the same algorithm which I have anyhow done before. This does not seem to be an improvement. So therefore I said, like, can I improve further on it? And there we said, maybe if instead of saying that we'll sort the numbers in the same bucket, if we could do bucket sort multiple times in a way where at the end of it, all of them would have been sorted, then that would be nice. So I say, you know what, like for the sorting based on the most significant bit, one thing is if I can somehow reach a state where numbers with the same most significant bit, they are already sorted in some way, that would be awesome. But to sort the numbers with the same most significant bit, for example, if you remove the most significant bit, you'll need to sort them by the remaining bits. There also, if you just again break it down recursively, you'll reach the same state. Like you'll first have to sort based on the least significant bit, then the least significant and most significant together, and then the last 3 together, last 4 together, and so forth. In radix, you have log base 10 of not the number of elements. I mean, so in n log n is number of elements. This is log base 10 x, which is the highest element in the array. This is not the number of elements. This is highest element in array. Two different things. But yeah, I mean, in cases of log n, if you have, let's say, 1 million entries, 10 power 6 entries or 10 power 7 entries, the log n is typically 20, 22, 24. In the case of numbers, the number of digit is probably still 8 or 9. So it can perform twice as faster. If max is less than n, go for radix sort. That I wouldn't say. If your log of 10 max is less than, in fact, significantly less than log n, then go for radix sort. Okay. In case of integer, we could use radix. That's why I said, like, if your log of max is less than log of n, you could use radix. That might run just slightly faster. Even if you go with bits, yes, you will eventually end up sorting. Just that the number of iterations will be more. All right, let's move to the next problem. Imagine you're given a bunch of numbers, which are not sorted, by the way. So let's say you have 5, 8, 3, 1, 6, some numbers, right? And you've been given this array that you cannot modify. So this is a constant array. Cannot be modified. Now what you need is that if this array was sorted, let's say if this array was sorted, the numbers would be 1, 3, 5, 6, 8. Actually, let me change the numbers a little bit. Let's say this number was 7, right? If this number was 7, then the numbers would be 1, 3, 6, 7, 8. And then in the sorted array, if you were to look at adjacent difference, the difference here is 2, difference here is 3, difference here is 1, and difference here is 1. There you have to find out what is the maximum gap between the numbers when the array is sorted. In this case, the maximum gap is 3. So you say the answer is 3. So given an array, how do you find this maximum gap if the given array is constant? And obviously, like, one answer is you make a copy of this array, you sort the array and you look at the adjacent differences and you take the maximum of that, which becomes time complexity order of n log n, space complexity order of n. Can you do something better than this? I'll repeat the question once more. You're given an unsorted array. The array is not sorted. What you have to find is if the array was sorted and if you looked at the adjacent numbers differences, what is the maximum difference you can find? What is the max gap you can find?
Hello everyone. If you want to learn binary search from the scratch, this is the perfect video for you. In this 3-hour Snyder cut, we will explain you what is binary search, intuition behind binary search, the code and the time complexity. After that, we'll jump into problems. First set of problems, given a sorted array, apply binary search. Second set of problems, array is not sorted, but you still have to apply binary search. Third set of problems, nothing is given. You have to build your own search space and then apply binary search. Finally, under which scenarios we can apply binary search. All these things will be covered in this 3-hour Snyder cut. So watch, learn, have fun. Thank you.
So hello everyone. So the topic for today is going to be searching, right? So we are going to look at different searching algorithms. We will start with linear search. And then we will move on to binary search, we will look at ternary search, and we will solve some problems related to binary search. Okay. Now, as always, after the class, we will have an assignment for you guys. So after every class, you are given an assignment so that you can actually apply what you have learned in the class and solve problems so that you can solidify the concepts. The link for the problem set will be in the video description. Apart from that, there will also be a link for a chat forum so that you can talk to your peers and discuss any issues that you face while solving problems. So that is for today. There is one more announcement that I would like to make, which is that a lot of students come to us and they say that, hey, I need help with interviewing, right? So they tell us that they somehow get nervous during interviews. And a lot of students say that when I'm doing competitive coding online, I am able to solve problems. But when I'm in a face-to-face interview, I somehow get nervous, or I'm not sure what the correct approach or what correct approach should I take while solving the problem in an interview. So to handle that, we have organized a mock interview for you guys today, right? So suppose that you wanted to see how an ICPC World finalist, right, someone who is very strong at data structures and algorithms, how such a person would behave, would approach a problem in a Google interview. All right, without further ado, let us dive into today's lecture. So let me just share my screen. All right, I hope that this is visible to everyone. Can someone just confirm please? Perfect. All right, let's begin. So I assume that most of you would be familiar with some sort of searching, right? Suppose that you have a collection. Suppose that you have a haystack. And you are looking for something in this haystack, right? Suppose a needle. Then how do you usually search? Well, the way we usually search is we pick each item one by one. Pick each item one by one. One by one. And we inspect it. Right? We see if this is the correct item, if this is the item that we are looking for. Now, this can be very, very time consuming, right? So just to prove this point, let us play a very simple game. Okay. So I want you all to play this game. So I have a number in my mind, right? And I'm telling you that the number is between 0 to 1000. Okay. Now, what you're supposed to do is you're supposed to guess what the number in my mind is. I'm not telling you the number right away. So you're supposed to make guesses between 0 and 1000. So if you could please start spamming in the chat, just tell me your guesses in the chat. And whenever I see the number that I'm guessing, that is in my mind, I'll let you guys know. All right, so can you guys please start? I have a number between 0 to 1000 in my mind, and you have to guess that number. So start pasting in the chat. What do you think the number is? You have no other information. 786, not really. That is not what I had in my mind. Okay, I got 52, 30, 91, 900, 100, 99. No, none of those. A lot of zeros, some 500, some 304, 300, 666, 120, 76, 2. None of these. 50, no, 3, 404, 545. None of these. None of these. Please give some hint. So Tushar has a very important thing over here. Tushar says, if you could give us something, then we will be able to approach that particular solution much faster, perhaps. Right? So we see that if you have no information, right? If you have no information about how to search, then your best chance is to randomly check, randomly guess, right? Or if you don't want to randomly guess, your best chance is to basically check each possibility, right? So it could happen that first you say that, okay, you are guessing the number 1, then you move on to number 2, then you move on to number 3, and you keep doing that. You keep making guesses till I say that, yes, your guess is correct, right? So this is an example of something called linear search. Why linear? Why linear? Because you are going over each item linearly, right? Basically, you're going over each item once. So this is called linear search. And let us suppose that you have n elements, and you're looking for some value, right? You're looking for some key in this set of n elements. Then how much time will linear search take us? So what is the time complexity of linear search? It is order of n time, right? And while we are at it, let us also quickly discuss the space complexity. So how much space does it take to do a linear search? Well, this is just order of 1, right? Because we don't really have to store a lot of memory. We can just use a couple of temporary variables and perform the linear search. All right. So I assume that everyone is familiar with this linear search. So linear search is very inefficient. Now the question comes, can we search faster? Can we search faster? Right? What do you think the answer to this is? So this is the question. Now I'm asking you, what do you think the answer will be? Now, as most things in life, the answer is it depends, right? It depends. Well, it depends on what? It depends on, is there some pattern in the data that we can exploit, right? If we have some pattern in the data that we can exploit, then perhaps we could search faster. Does that make sense? For example, let us play this game once again. Right? Let us play this game once again. I am going to have a number from 0 to 1000 in my mind, and you are supposed to guess that number once again. However, this time, whenever you make a guess, I'm going to tell you if your guess is too high or if your guess is too low. All right? Cool. So let us begin once again. I have a number in my mind, and could you start guessing, please? So Mudasir says 2. Well, 2 is too low. Then Mudasir has guessed 34. 34 is too low, once again. Then the next guess is 123. It is too low. The next guess is 233. That is too high. Sahil says 500. That is too high. All right. Keep them coming. Keep the guesses coming. The next guess is 150. This is too high. Then What is your next case going to be? So 188, no, 188 is still too high. 200 is still too high. 10 is way too low. Yes. So 130 is too low. And then what do we have? All right, so 130 is too low. Can you make more cases now? 143, right? Someone guessed 143, and that is exactly the value that I was thinking of, right? This was my guess. This is correct. All right. So we see it took us some time, right? It took us some time. It was not that we were able to guess the answer immediately. However, we were able to hone in on the answer, right? So you know of homing missiles, right? The homing missile doesn't really know where the target is, but as it moves forward, it will get closer and closer to the target. Right? That is what we were able to. We were able to home in, right? Home in on the answer. Why were we able to do that? Because there was some pattern in the data that we could exploit. The pattern was that we were able to figure out whether our guess was too low or whether our guess was too high. Right? Now, a lot of students think they have this misconception that some sort of a binary search, right? Binary search can only be applied when the data is sorted. And that is not the case. The data need not be perfectly sorted for you to be able to apply binary search, right? So what we are looking for in the data is we are looking for some pattern or some sort of ordering. Okay. So let us define some nomenclature over here. Let us define some theoretical nomenclature over here so that we can make concrete progress over what binary search is. All right. So suppose that you have some search space. And let us represent the search space like this. In the search space, this search space is basically a set of possibilities, of possible answers. Right? So there's one answer possible over here. So this is another possible answer, this is another possible answer perhaps, another possible answer, and so on. What binary search says is that when you make a guess, let us suppose that you made this as the guess. When you make a guess, if you are able to eliminate a large fraction of your search space, then you can search efficiently. If this is the case, then you can search efficiently. Right? Let's see how. So let us look at the previous game that we played. In the previous game, whenever you came up with an answer, right? Let us say that you came up with an answer that, hey, the guess is 200. Then all I told you was whether the guess was correct or not. Right? All I told you was whether the guess was correct or not. And that basically allowed you to eliminate this possibility itself. Right? So you made a guess 200. I told you it is not correct. So you can eliminate this possibility. Can you eliminate any other number? Did you get information about any other number? You did not. Right? On the other hand, in the second version of the game, suppose you guessed 200 and I told you that it was too high, then you could have eliminated every number. You could have eliminated all these numbers that were greater than 200. And your search space would only remain with the numbers that are less than 200. Right? Does that make sense? Yes. So this is something that we will try to exploit in binary search. So basically, binary search can be applied whenever you can remove, right? Remove or prune a large chunk of your data, of your search space with every guess. All right. Cool. So let us look at a more concrete example of this. So mostly when we are talking about searches, the first thing that would come to our mind is that we have an array. Right? We have an array. Suppose we have an array of integers. right? This array has multiple values. Let us say that the size of this array of size n, right? The size of this array is n, and we are supposed to search for a particular value in there. So given an array, what type of things are we able to binary search over? What type of things are we able to binary search over? So whenever we try to binary search, we try to come up with a proposition. Does everyone understand what a proposition is? Yes, a proposition is something that takes two values, any of two values, right? A proposition can either be true or it can be false. Right? A proposition can either be true or it can be false. Now, if you can come up with a proposition, such that your array starts looking something like this, that for this particular element, the proposition is true, for this element, the proposition is true, for this element, the proposition is true, and so on. At some point, the proposition starts becoming false, right? If you are able to come up with a proposition that can make your array look like this, then you are able to perform binary search on this array. And what will that binary search give you? That binary search will give you this boundary point. That binary search will give you this point where the proposition flips. All right, is that clear? So we will look at a little more concrete examples of these. Cool. So let us once again go back to this game of guessing the number. Right? Let us suppose that I gave you an array from 0, 1, 2, all the way till 1000. Right? All the way till 1000. And I had a guess. Let us say my guess was this number G. The correct answer was this number G. Now, what is my proposition over here? What is my proposition over here? So what is the proposition that makes sure that everything to the left of G is true and everything to the right of G is false? Can someone tell me that? So what proposition should I make so that every number to the left of G should result in false, while every number to the right of G should return in true? Exactly. So the proposition can be as simple as, is A of I less than G? Right? Is A of I less than equal to G? Right? What happens in that case? So if G is my guess over here, then every value to the left of it, yes, it is less than equal to G. So all these values will be true. On the other hand, on the right hand side, all these values will be false, because they will be, if the array is sorted, all these values will be false because they will be larger than G. So if I'm able to come up with this proposition, then binary search will allow me to find this junction. It will allow me to find this point where the true flips from true to false. Is that clear? All right. And now we have basically come up with the final definition of binary search. Right? Binary search does not require you to have a sorted array. Right? That is a misconception, that you need to have a sorted array to perform binary search. What you really need is you need this proposition. If for any search space you can come up with such a proposition, then you can apply binary search on that search space, right? Irrespective of whether that search space is sorted or not. All right. Perfect. So let us dive into some more concrete things, and let us try to look at the implementation of binary search. Right. So once again, suppose that we have been given an array, right, of size n, and this array is of integers. Right? And we are also given a key, suppose k, that we are looking for. And for now, let us suppose that the array is sorted in ascending order. Right? Then what we have to do is we have to search the element. We have to find the index of k in this array, if it exists. Right? If it exists in the array, then we are supposed to find the index and return the index Otherwise, what we're supposed to do is we're supposed to return the index where k should be inserted. K should be inserted in the array. Is that clear? Yes, is that clear? So once again, suppose that we have an array that looks like this: 0, 3, 7, 12, 15, 16, 20, right? And I give you the key, let us suppose 12. Right? So in this case, what are you supposed to return? So let me give the index as well. This is 0, 1, 2, 3, 4, 5, 6. So in this case, what are we supposed to return? If this is the array and this is the key, then what value will we return over here? The answer we are supposed to return over here is the index 3, right? Because 12 is at the index 3, right? On the other hand, if I ask you to find the value, let us say k equals to 17, right? If I ask you to find the value k equals to 17, then what are you supposed to return? So there are multiple variants, right? In some cases, I might ask you to return -1 because 17 is not present in this array. I might ask you to return -1, but that is not what we are looking for over here. We are saying that if the value is not present in the array, then tell me the index where that value should be inserted. Right? So if 17 was inserted in this array, then what value, what index should it be inserted at? Should it be inserted at this location? Should it be inserted at this location? No, it should not be, right? Because 16 is less than 17. It should be inserted at 20's position, and 20 should be shifted to the right. Yes, 17. If 17 was inserted, 17 would come in the 6th position, and 20 will be moved to the right. Right? So if the search key is 70, then you are supposed to give me back the answer index equals to 6. Is that clear? Right? So this is the classic problem of binary search. We have been given an array. We have been given an array which is sorted, and we have been given a key, and we have to search this key within the array. Right? Now let us first look at the implementation of how we would do this binary search, and then we will discuss the time complexity, right, and the corresponding analysis. All right. So let us start with this thing. So suppose that we have this function int binary search, right? And in this we are receiving a vector, right? We are receiving a vector. So we can say that, okay, we have an vector AR, vector of int AR, right? Apart from that, we also have the key. So we have an int. So this is not a semicolon, this is a comma. We have an int key. All right. This is the function that we are going to write. Yes, Shubrata, yes, in this case, we are accepting a sorted array. All right. We will come to binary searching over non-sorted arrays in some time. We are starting with the most simple thing, that the array is sorted. All right. Cool. So how would we write this particular piece of code? So when binary searching, there are certain things that we would like to identify. There are certain things that we would like to identify. If we are going to search, then the first thing that we need to identify is our search space, right? Is our search space. Now, if we have an array, then what do you think the search space is going to be? If we have an array, then what is the search space? Well, the search space is all the possible different indexes in the array, right? The value could be at index 0, the value could be at index 1, and so on till the last index. So the search space is the indices of the array. Well, what is the minimum value of that search space and what is the maximum value of that search space? So can we somehow draw a boundary? Can we draw a boundary around that search space? Yes, right? So in this case, the boundary is from 0 all the way till n minus 1, where n is the length of my array. Is that clear? All right. So when I'm defining the boundary, I will encapsulate. I will basically wrap my search space around this within this boundary. So I will say that, okay, let us suppose that we have some low, right, and that is the minimum possible value in my search space, and I also have some high, and that is the maximum possible value in my search space. And I can write over here that n is perhaps n equals to ar.size. All right. Cool. Now that we have the boundary, we are supposed to perform the binary search. Okay. So this was the first step of binary search. The first step of binary search was to bound or to establish the boundary of the search space. Right? The second thing, once you have established the boundary, the second thing is to make a guess. So how do we make a guess? Let us suppose that we have some search space and we want to make a guess. What guess do you think we should make? What guess do you think we should make? So we can make any guess, right? We can make any guess. However, we should try to make a guess that allows us to eliminate a very, very large chunk of the search space. Right? Does that make sense? So if I have this array, and this is sorted, right? And this is my low, and this is my high. Right? If I make this guess, if I make a guess over here, then what will I be able to eliminate? What will I be able to eliminate? I will either be able to eliminate this part or I will be able to eliminate this part. Yes, I will either be able to eliminate this left half if my guess was too high, right? Or I will be able to eliminate this right half entirely if my guess was too low. Now, what is these values? What are these values over here? What are these values over here? Let us say that this is x, then this will be n minus x, right? Now the question is, in the worst case, right? If I'm very, very unlucky, then my guess will be on this side, right? I will be able to eliminate a smaller value. I will not be lucky. I will not be able to eliminate a very large value, right? So I should try to make it so that x is as large as possible, right? Both x and n minus x are as large as possible, right? So that no matter whether I'm lucky or not, I'm able to eliminate a large chunk of my search space, right? So what guess should we make over here? We should perhaps guess the middle element. We should perhaps be guessing the middle element. Is that clear? Right? So this is the second thing. Once we have decided the search space, once we have the low and the high, now we are supposed to find a mid. Right? So we will guess a mid. So we will say int mid equals to low plus high by 2. Right? And notice that this is integer division. Right? This is integer division. All right, cool. So is this part clear? Is this part clear? That we calculate the mid. All right. Once we have the mid, then what do we do? Once we have the mid, then what do we do? The third step is to check the proposition. Check the proposition and prune, right? And prune our search space. Right? We have to check the proposition and prune our search space. Now, the proposition can be either true or false. Right? The proposition can be either true or false. However, in most of the cases, we can have 3 values. Right? We can have 3 values. Either my guess is too high, or my guess is too low, or my guess is exactly correct. Right? So let us look in this case. Let us look at that in this case. So what possibilities can I have over here? Right? What possibilities can I have over here? If AR of mid is less than the value I'm looking for, is less than the key. If AR of mid is less than the key, then what does that mean? Is my guess too high or is my guess too low? If the location that I'm looking at the location mid. If the element at that location was less than the key, then is my guess guess too high or is my guess too low? Well, the element was less than the element I was looking for. So I am sure that since the array is sorted, any value that is at AR of, let's say, 0 or AR of mid minus 1, right? Mid minus 1, all these different values are going to be less than the key as well because the array is sorted. So my guess was too low, right? My guess was too low. So what should we do? We should adjust something, right? We should adjust the search space. How should we adjust the search space? We can say that low equals to mid plus 1, right? Mid plus 1. Right? So basically, earlier, this was the search space, this was low, and this was high. Right? I made the guess at mid. And I found out that this guess was too low. Right? This guess was too low. So what should I do? I should shift this low. I should shift this low to the element just right of it. Right? So this element should now be low. And basically by doing that, I am eliminating all these different possibilities. Right? I am eliminating all these different possibilities. Is that clear? So we should move up the low. Is that clear? We should increase the low. All right, so that is one case. So what other cases can we have? Else if AR of mid was greater than key, right? If AR of mid was greater than the value I'm looking for, then what happens? Then my guess is too high. And by the same argument, now I need to decrease the high. Right? And now I need to say high equals to mid minus 1. Right? Otherwise, if even that is not the case, then what possibility remains? If it is neither too high, if it is neither too high nor too low, then what possibility remains? Then it must be exactly correct. Right? Else my guess was exactly right. Right? I guessed the perfect answer. So in that case, I can just return the index. Right? Because I looked at this particular index, AR of mid, I looked at this particular index and I found a value that was exactly equal to the key. Right? It was neither greater than key, it was not less than key, so it must be exactly equal to the key. So I can just return this index because this is the index that I am looking for. Is that clear? Yes? Perfect. Now let us look at the code that we have and let us see if there is something missing over here. Right? Let us see if there is something missing over here. So once again, in the code, what we are doing is we are saying let us initialize a search space. Initialize space, right? Then we make a guess. So this is our guess. And based on the guess, we adjust the search space. So will we be able to, after one adjustment, will we be able to reach the answer? Will we be able to reach the answer after just one adjustment? No. Right? We have to continuously adjust our guess. Right? So we have to do this entire thing again and again. We have to repeat this. Right? We have to repeat this entire thing. So how should we repeat this entire thing? Let us put it inside a loop. So let me add some space over here. And let me say, I will loop. Let us say I loop forever, right? While some condition. So I don't really know what this condition is, but as long as this condition is true, I will keep looping. Right? I will keep looping till this condition is true. Is that clear? Right? So we could have done several things over here. We could have called this function recursively as well. Right? Based on the adjusted guess, we could have called this function recursively as well. But recursion will have a lot of different issues with itself. So it will use a lot of memory because it will use the recursion stack. So let us not do that. Let us go with the iterative approach. Right? So once we have made a guess, and we check the guess, after we check the guess, we will adjust our search space. Right? Now once we have adjusted the search space, what do we have to do again? We have to make the guess again. Right? We have to make the guess again and again. But till what time should we continue this? Till what time should we continue this? Should we continue this forever and ever? Should we continue this forever and ever? No, we should only continue this as long as our search space has elements in it. Right? If our search space has elements in it. So basically, if our search space is empty, then it does not make sense to keep looking inside that search space. Right? If our search space is empty already, then it does not make sense to keep looking inside that search space. So when will our search space be empty? Right? When will our search space be empty? Let us suppose that this is my array. This is the low and this is the high. At what point would I say, for what values of low and high would I say that my search space, that this particular area, this particular range over here, this is empty? When will I say that? What happens when low equals to high? When low and high are the same. What happens when low and high are the same? Well, then my search space is not empty. Then my search space has one element, which is A of low. Right? If low equals to high, then my search space has one element, which is A of low. So when will my search space be empty? When low will be greater than high. Yes. As soon as this happens, as soon as this is my low and this is my high, right? Then I'm saying that the search space is everything that starts from low and goes till high. Well, it cannot go till high, right? My search space is empty now. Is that clear? So I am supposed to continue this loop till my search space is not empty, right? So what will be the opposite condition over here? What will be the opposite condition over here? So if this tells me that the search space is empty, then how do I check if the search space is not empty? I will check it by saying while low is less than or equal to high. Is that clear? Yes? Right? And this is very important. Right? If you miss this equal to, you might get an incorrect answer. Right? Or if you do something else, you might run into an infinite loop. So it is very crucial that we have this condition right, because this condition tells us when to terminate. It tells us when our search space is empty. Okay? And I mean, a lot of the times people are worried that, okay, I don't really know how to determine what condition should go over here. So here's the trick once again. To determine what condition should go over here, you have to ask yourself, when will my search space be empty? When will my space be empty? Right? And based on that, you will be able to come up with a condition. All right? Cool. So this is basically the code of binary search. We started with a search space. Repeatedly, while the search space was not empty, we made a guess and we adjusted that guess. Right? If our guess was perfect, we simply returned that guess. But what if we did not find that element? What will happen then? What if we did not find that element at all? What will happen then? Well, then we will keep on looping. Till the point our search space becomes empty. Right? Till the point our search space becomes empty. So what will happen is we will not be able to return over here. However, we will come out of this while loop. Right? So we will come out of this while loop. We will be over here at this point. And what values of low and high will we have? We will have a value such that low will be equal to high plus 1. Right? That is when our search ends. Right? And what is this location? Can you tell me what this location is? This location is exactly the location where I should insert this element. If I were to insert this element, this is exactly the location where I should insert this element. So when I am at this point, just give me a second. When I am at this point, I know two things. The first thing I know is that low is the index. Is the index where I should insert it. Where I should insert key. If I was going to insert it, then low is the location where I should insert it. Second thing I know is key was not found in my array. Key was not present in my array. Right? Is that clear? Now, once again, if we were to simply find the index of the, if we were supposed to find the index of the key and return -1, if the key was not present, then over here we will return -1. Right? Then over here we will return -1. Right? On the other hand, more practically, whenever you see a library implementation, we don't usually return -1. Instead, we return the index where I should have inserted the key. Right? So over here we can also return the low. Return the low value, right? Because this is the location where I should have inserted the key. Is that clear, guys? Yes? Now, one common question is, if you are returning -1, then your caller knows that the element was not present, right? Because hey, index cannot be -1. Index of a particular value in an array cannot be -1. Indexes start from 0, right? So in this case, my caller knows that the element was not present. But what if I return low? What if I, instead of returning -1, what if I return low? How will the caller find out if the element was present or not? Yes, the caller has to be able to make that distinction, whether the element was present or not. So how will the caller get to do that? Well, the caller can check. The caller can simply check. So it will say that, okay, index equals to binary search, the array and the key, right? And the person can check, the caller can check if AR of index equals to key, right? If AR of index equals to key, then we found the key, right? Then we found key at index, right? Otherwise, it means that we did not find the key, but this index is the location at which we are going to insert it, if we were to insert it. So we can say did not find the key, but if we were to insert it, it should be inserted at index. Is that clear? So the caller will have to make this additional check. Is that clear, guys? Yes? Okay. So Rohit has a question over here. Rohit says, what should we return? What should we return if key is less than AR of 0? Right? That's a very good question. So suppose that we have this array. This is the index 0, this is the index 1, and so on. Right? Let us say this value is 10, this value is 11, this value is 12. And let us say my key was 9. Right? Or let us say my key was 5. So first of all, is my key in the array? No, it is not in the array, right? Not present. If I were to insert this value, where should this key go? If I were to insert this value in the array, where should this key go? Can the key go at location -1? No, right? There is no index -1 in the array. So where should this key go? This key should go at index 0. The 5 should be inserted over here, and everything in the array should be shifted to the right. It's shifted 1 to the right. Does that make sense? So over here, a binary search, when I search for key equals to 5, my binary search should return the value 0, right? It should return the index 0. And that is exactly what our code will do. All right, that is exactly what our code will do. Is that clear? Okay. So let us move on. So I hope that the code and the implementation of binary search is clear to everyone. Now let us look at some improvements that we can make on our code. So one of the most important improvements is that we never try to calculate. The mid like this, right? And you might have seen this a lot of times. People do the following. People instead of saying int mid equals to low plus high by 2, right? They do something else. They say int mid equals to low plus high minus low plus high minus low by 2, right? So can someone tell me the difference between these two? Why do some people do it this way? Well, let us try to look at the mathematics, right? Let us try to look at it mathematically. So if I have low plus high by 2, right? This is one thing. On the other hand, I can have low plus high minus low by 2. And let us see that if there is a difference between these two. So what I can do is I can take the denominator 2 common over here. So what will happen? The numerator, this will become 2l plus h minus l. Right? This will become 2l plus h minus l. What is that? That is simply, so one L will cancel out. This will simply be low plus H. Right? This will simply be low plus H. So we see that the left hand side and the right hand side are equivalent. Right? From a mathematical point of view, they are equivalent. So what really gives? Why do people do this? This is more complicated, right? The reason why people do this is, even though they are mathematically equivalent, when we are dealing with computers, we can run into an overflow. Right? When we are doing addition, we can run into an overflow. For example, let us suppose that our integer can only store. So let's suppose that the largest value our integer can store is, let us say, 10 to the power 9. Right? Let's say 1 billion. Okay. Let us say that our low is 5 into 10 to the power 8. Okay. So our low is 500,000. Let us say that our high is 8 into 10 to the power 8, right, which is 800,000. Right? If I have something like this, what will happen when I try to calculate the mid? I will be doing 5 into 10 to the power 8 plus 8 into 10 to the power 8. Right? This will be low plus high, and then I will divide it by 2. Yes, then I will divide it by 2. But what will happen over here? When I try to add these values, this will be 13 times 10 to the power 8. Right? And we just saw that 13 into 10 to the power 8, this cannot fit in my integer. My integer can only be up till 10 to the power 9. This is greater than 10 to the power 9. Right? This is what? This is 1.3 times 10 to the power 9. Right? So this value over here, this will overflow. And the value that I will get over here will be garbage. Right? It will give me a wrong answer. And then I divide the wrong answer by 2, I will eventually get a wrong value of mid. Is that clear? Yes. On the other hand, if I do it the other way, if I say low plus high minus low by 2, right? If I do it this way, then what happens? Then this will be 5 into 10 to the power 8 plus 8 into 10 to the power 8 minus 5 into 10 to the power 8 by 2. Right? And is this operation going to overflow? No, I'm subtracting things. Right? I'm subtracting things. So the answer over here will be less. Right? The answer over here will be less than this value. Yes. So what do I get over here? I get 5 into 10 to the power 8 plus 3 into 10 to the power 8 by 2. Right? And then then this will give me the correct answer, 6.5 into 10 to the power 8. Is that clear? This will not overflow. Whereas this approach will overflow. Is that clear? This approach will overflow. All right. So Amit over here says that, hey, we can just use a different data type. Right? If we are dealing with an integer, maybe we can switch to a long data type. Right? But I mean, what if you were using a long? Right? Amit, the problem is, what if you were using a long? What would you do then? So in general, it is a good idea to implement the mid calculation via this particular approach. Okay. All right. So that is the improvement we are going to make over here very quickly. We are going to go to a code of binary search. We are going to remove this and we are going to improve it. We are going to say int mid equals to low plus high minus low by 2. All right. Perfect. Okay. I hope that everything is clear till now. Now let us try to analyze the time complexity of binary search. All right. Let us try to analyze the time complexity of binary search. Time complexity. All right. So how do we talk about the time complexity of binary search? So what is really happening is, initially I have the search space of size n. Right? Initially I have the search space of size n, and I guess the midpoint. Right, as my guess. Right? If my guess is too low, then I'm able to remove these elements. Right? I'm able to remove these elements. How many elements was I able to remove? So if this is 0, this is mid, and this is n, then after one guess, if my guess was too low, then how many elements was I able to remove? I was able to remove n plus 1 by 2 elements. Right? Yes or no? On the other hand, if my guess was too small, then I would be able to remove all these different elements. Right? Everything from mid all the way till n minus 1. Right? Even then, I was able to remove n plus 1 by 2 elements. Right? I was able to remove n plus 1 by 2 elements. So what really happens is, every time I make a guess, I'm reducing the search space by half. Right? I'm halving the search space with every guess. Right? So suppose we started with this guess n. Right? We started the search space of n. After one guess, I will have a search space of n by 2. After one more guess, I will have a search space of n by 4. One more guess, I will have a search space of n by 8. Right? And when will I end? So finally, this search space will reduce down. This search space will reduce down to just one element. Right? This search space will reduce down to just one element. Is that clear? So the question is, how many guesses did it take? So it took me one guess over here, it took me one guess over here, one guess over here, one guess over here, and so on and so forth. So how many guesses did it take? Right? How many guesses did it take? So no, guys, it did not take me n plus n by 2 plus n by 4 all the way till 1. No, this is not how many guesses I got. Right? This is incorrect. So remember that when we are moving from this search space to this search space, I am making one guess. I am not making n guesses over here. Right? I made just one guess, and I was able to reduce my search space from n to n by 2. Right? So basically, at the 0th guess, when I have not made any guess, my search space is of size n. After first guess, right? After first guess, my search space is of size n by 2 to the power 1. After second guess, my search space is of size n by 2 to the power 2. After the ith guess, my search space will be of the size n by 2 to the power I. Right? Now the question is, at what value of k? At what value of k will this thing become equal to 1? At what value of k will my search space reduce to one single element? Right? That is the question that we are asking ourselves. So this is the equation that we get, right? So at the kth guess, our search space will be this, and we want the search space to have just one element. So can we find the value of k from here? Can we find the value of k from here? So what can we say? This implies that n equals to 2 to the power k, which implies that I can take log on both sides. Right? I can take log base 2 on both sides, log base 2 of 2 to the power k, right? Which implies that k equals to log base 2 of n. Is that clear? Yes. So I am taking order of log n guesses. I am making order of log n guesses, right? And that is the complexity. That is the time complexity of binary search. Is that clear? Yes. Is that clear, guys? So basically, we started with an array of size n. Then after first guess, we were able to reduce it to half the size. Then after the second guess, we were able to reduce it to 1/4 the size, and so on and so forth. So how many guesses will we take to reduce it to size 1? Well, it will take us log base 2 of n guesses. Right? The depth of this tree, the depth of this is log base 2 of n. Is that clear? Right? Okay. What about the space complexity? What about the space complexity? So let us go to the code to analyze the space complexity. Let us go back to our code and let us see what variables we are using. Okay? So this is our code. Let us see what variables we are using. So we are declaring a variable over here, n. We are declaring a low, we are declaring a high, and we are declaring a mid. Right? All of these take constant space. They are just integers. So overall, our space is just constant. Right? We are not allocating any space that is dependent on the input. We are just allocating a constant space. Right? Notice that this vector, we are not allocating this. This is given to us already. Given to us. Since we are not changing this array at all, so we don't have to allocate the space for the array. All right? The array is given to us. So the space complexity of binary search is going to be simply order of 1. All right? Constant space. Is that clear, guys? Perfect. Now let me ask you a question. Let me ask you a fun question over here. So this is called binary search. Right? This is called binary search. Binary search. Why is it called binary search? Because we are splitting into two parts. Two parts with every guess. Right? And we saw that when we do binary search, our complexity turns out to be log base 2 of n. Right? Our complexity turns out to be log base 2 of n. What if instead of binary search, what if I try to come up with something like ternary search? So first of all, how would ternary search even work? Right? If I have this particular array, then now I have to guess two values. I have to get mid 1 and I have to get mid 2. Right? This is my low. This is my high. In ternary search, what I can do is I can make two guesses. Right? I can say mid 1 equals to low plus high minus low by 3. Right? And I can say mid 2 equals to low plus 2 times high minus low by 3. Yes or no? Can I do that? And then I can compare. Right? So I can compare AR of mid 1 with my key. Right? I can compare AR of mid 2 with my key. Right? And what will I get? Either my key will lie in this area, or my key will lie in this area, or my key will lie in this area. Yes, that is all the possibilities, right? My key cannot lie in both these areas at the same time. Right? My key cannot lie in both these areas at the same time. Does that make sense? So after one guess, we were able to reduce our search space by 1 to 1/3. Right? From n, we could go to n by 3. Right? We could eliminate a larger chunk of our search space. Does that make sense? This is called ternary search. And in general, you can extend this idea. You can define something called a k-ary search. And in k-ary search, what you will do is you will calculate mid 1, mid 2, all the way till mid k minus 1. Right? And then we'll compare with all of them. That will allow us to, in one guess, it will allow us to go from n all the way till n by k. Right? Does that make sense? Yes, ternary means 3 divisions. Binary means 2 divisions. K-ary means k divisions. All right? Is that clear? Example of ternary search? Well, the example is very simple, right? We given an array, what I'm going to do is I'm going to make 2 guesses. Right? Instead of making one guess at any point, I'm going to make 2 guesses. And based on these 2 guesses, I'm going to decide whether I should be looking over here, or I should be looking over here, or I should be looking over here. Right? Going back to our original question, when we were supposed to guess between 0 and 1000. Right? Instead of you giving me a guess like 500, you could have given me 2 guesses at the same time. You could have given me 333 and 666. Right? And then I could have told you that, okay, it is less than 333, or it is between this, or it is above this. Does that make sense? Yes? Does that make sense? Right? So the time complexity of ternary search, it seems that the time complexity of ternary search will be order of log base 3 of n. Right? Because we are dividing by 3 every time. Similarly, the time complexity of k-ary search would be order of log base k of n. Yes? Now, which is greater? Which do you think is greater? Is log base 2 of n more, or is log base 3 of n more, or is log base k of n more? Right? For some large value of k, which value is more? Which value is smaller? Right? So which value is larger, which value is smaller? Well, if we divide by 2, then it takes us certain number of steps to reach 1. If we divide by 3, then it will take us lesser steps to reach 1. Right? If we divide by 3, then it will take us lesser steps to reach 1. So log base 2 is greater than log base 3n, which is greater than log base kn. Right? So it seems like k research should be the fastest. Right? So why do people still use binary search? Why don't we always have k research? K research seems to be very fast. Right? And it seems that I can make it as fast as I want. Right? I can just increase the value of k to make it as fast as I want. Yes or no? Yes? Well, let us see what is the fastest value I can have. So maybe when k equals to n, I will get log base n of n, right, which is simply 1. So I will be able to find the answer in just one guess. That is amazing. Right? I will be able to find the answer in just one guess. That's very, very weird, right? I was able to find the answer. I was able to search the element in the array in just one guess if k equals to n. Is that correct? Yes, but there's a catch over here. Right? Now what really happened was we had this array and we made every element as a guess. Right? We made every single element as a guess. And then we checked if our guess is between over here or 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 over here, right? In one guess itself, we made we chose n different values and different midpoints. Right? N minus 1 different midpoints. So are we really doing an efficient search over here? No, this has reduced to the linear search. Right? This has reduced to linear search. So it turns out that when k equals to n, we were expecting it to take just one guess. It did take just one guess, but inside that single guess, we were doing a linear search. Right? So this is the worst thing that we can do. Does that make sense? K equals to n is the worst thing that we can do. So what really gives? We see that our intuition does not equal our math over here. Right? Math says that this should be faster, but intuition says that this should be slower. So what really gives over here? Right? What really gives over here? Well, there's a catch, right? There's a catch in the fact that this is big O complexity. Right? There's a hidden constant factor. Let us look at the exact complexity of searching. Right? Let us look at the exact complexity of k research. If I'm doing binary search, then I have one guess, right? I have one midpoint. Yes, I have one midpoint. Do you agree? And what check am I making? I'm comparing A of mid with k. Right? How many comparisons is this? This is one comparison. Right? So my actual complexity is 1 times log base 2 of n. Right? This is in the case of binary search. On the other hand, when I have ternary search, I will guess 2 midpoints. Right? I will be guessing 2 midpoints. And then what comparisons do I have to make? I have to compare A of mid 1 with k. I have to compare A of mid 2 with k. Do you agree? Yes, I have to compare A of mid 1 with k, and I have to compare A of mid 2 with k. So how many comparisons is that? This is in fact 2 comparisons. Right? Now you see the hidden cost. As we increase the value of k, the number of comparisons for each guess increase. Does that make sense? Yes, guys. So for ternary search, our complexity is 2 times log base 3 of n. Right? This is for ternary search. And in general, for k research, our complexity will be log base k of n. But for every guess, we will have to make k minus 1 comparisons. Right? We'll have to make k minus 1 comparisons. Now let us ask this question again. What do you think is larger? Right? What do you think is larger? Is log base 2 of n times 1 larger? Or is 2 times log base 3 of n larger? Or is k minus 1 times log base k of n larger? Right? Which one of these is larger? Well, now we know that actually this is the reverse, the other way around. This is the slowest. This is the largest value, so this is the slowest. And in fact, binary search is the fastest. Is that clear? So we can totally do k research. We can totally do a ternary search. We can totally do a k research. But practically, binary search will work much, much faster. Is that clear, guys? Is that clear? Binary search will work much, much faster. Right? Cool. Now, there's this question. Now you might be thinking that, okay, you told us about ternary search, you told us about k research, and then you said that, okay, those don't really matter, right? Why did you even tell us in the first place? Right? Why did you tell this to us in the first place? The reason is that in certain situations, k research can become faster. Right? K research can become faster. Let us look at how. Right? Let us look at how. Suppose that we are dealing with some sort of a disk, right? Hard disk. Right? Suppose that we are dealing with some sort of a hard disk. Do you know that hard disk is split into blocks and sectors and tracks? Yes. So basically, we are talking about a spinning hard disk over here. Right? We are not talking about that the new SSDs over here. We're talking about that spinning hard disk over here, the magnetic hard disk. So what really happens is, in a magnetic hard disk, you have several platters. Right? You have several platters, and for each platter, you have a read head. Right? You have a read head that is at a particular platter that is tracking a particular track. Right? That is tracking a particular track on this platter. Right? Now, what you have to do is this one track information across this one track is let's say called a track. Right? And let us say this is one block. So usually this can be something like 32 kilobytes. This could be 32 kilobytes. All right. Now what happens is, if you have to read any value within this, then that is very fast. Right? Then that is very fast because your disk is spinning. Right? Your magnetic disk is spinning at 1000 RPM. Right? So within 0.001 second, you can read this entire 32 kilobyte. You can read this entire 32 kilobyte block. Right? But if you have to change blocks, if you have to move from this sector, if you have to move from this track to perhaps this outer track, right? If you have to do that, then what you have to do is you have to move this head. You have to move this read head. So you have to unplug this read head. You have to run the motor to move it back. Then you have to plug it back, right? And that takes some time. So that moving the read head can take a lot of time. It can take, say, that is 0.1 seconds of time. Right? So that is very, very slow. Is that clear? So it turns out that what really happens, is, it could be the case that due to this thing, it could be the case that making comparisons is fast. All right, you read 32 kilobytes of data in the memory, and then once the data is in your RAM, you are making comparisons in the RAM, right? And RAM is very, very fast, very, very fast. On the other hand, making a guess is slow. Making a guess is slow, right? Why? Because for every guess, for making a new guess, you have to change the block. You have to change the hard disk block, right? And you have to move that. You have to move that read head manually, right? Because this is happening at the hard disk level. This is not happening at the RAM level. Okay. So what really happens in this case is making a guess. I want to reduce the guesses. I want to reduce the number of guesses I make. I don't really care about the number of comparisons I make, because the comparisons are happening in the RAM very, very fast, right? So in this sort of scenario, I would prefer to use some sort of a K research, right? I would prefer to use some sort of a K research, because in a K research, this is the number of comparisons, right? and this is the number of guesses. This is the number of guesses. The larger the value of k is, the lesser my guesses will be. Right? The larger the value of k is, the lesser my guesses will be. So basically, to maximize my efficiency, I choose a k which is equal to the block size. I choose a k which is equal to the block size. Right? And this thing, right? This thing is used all the time in databases. Whenever you are using a database, the database internally is storing the data in a thing called a B plus tree. Right? In something called a B plus tree. And a B plus tree is simply a binary tree that has been extended from. So binary tree works in a binary search manner. Right? On a binary tree, you can have a binary search tree and you can binary search on it. On a B plus tree, you can do a k research. You can do a k research on a B plus tree. All right. How did you come up with this formula? So this formula is what we just saw, right? This formula is what we saw for binary. For binary search, we have one comparison and log base 2n guesses. For ternary search, we have two comparisons and log base 3n guesses. For k research, we have k minus 1 comparisons and log base kn guesses. All right. Is that clear? This is multiplication. Is that clear, guys? All right. So I think we are going to leave it at this, right? We are already above the time. So today we basically discussed binary search. Binary search. We saw how to implement it, right? We saw how to implement it, and we saw that this idea can be extended into a k research, into a ternary search or a generic k research. K research is generally slower, right? Generally, we would like to do binary search, but there are cases, like for example, databases in which k research is very, very valuable. Okay, cool. Now, I would want each of you to, once this lecture is over, to find the link in the video description, or there's a link to the assignment, right? Today's assignment. So please go over there and try to solve those problems. So those problems will be on basic binary search. There are some things that we were not able to discuss, like binary search on a rotated array, and finding the peak element. We can discuss it in the next class. All right. All right, guys. Cool. Will we cover interview bit problems from your website? Yes, Reshma. So all these problems. So that is why we give you the assignments, right? We are discussing the problems that are part of those assignments. Okay. I mean, of course, when we are actually doing a scalar class, when someone joins our academy, we usually have 3-hour classes, right? And we have classes every single day for 3 hours. So that gives us a lot of time to work with the student, right? So they are able to solve many more problems. We won't be able to do that on YouTube, right? So I understand that you won't be able to get the exact same experience as scalar, but that's to be expected, right? Because this is on YouTube. All right then. So please make sure that you solve the assignment. Please make sure that you are taking notes while you're studying the lecture. And see you in next class. In the next class, I will continue. We will continue with binary search, and we will be looking at more advanced problems on binary search. Okay. Perfect. If you want to join Scalar, well, we don't really announce the dates during lectures. So whenever, if you're trying to join Scalar, just go to scalar.com. Right? And any announcement about a new batch, will be made over there. Right? So please monitor the scalar.com website, and any announcement about any new upcoming batches will be made over there. Right? So let us end the lecture then. All right. Bye-bye, guys. Have a nice day. We are back with another lecture. Today, we are going to continue binary search. We are going to look at some questions that have been asked in companies, in some of the top companies, right, regarding binary search. Now, without further ado, let us start the class. So let me just share my screen. All right. I hope that everyone can see the screen and whatever I'm writing over here. Cool. So Let us start with a question directly. So yesterday we had looked at what binary search was and how to implement binary search. Let us dive into one question today. Okay. So suppose that you have been given an array, right? And this array has n integers. All right. Now it has also been told to you that in this array, all elements but one come twice. Come twice. All right. Also, it has been said that the array is sorted. Array is sorted. So let us first take an example of such an array. Let's look at such an example. Let's say that we have 0, 0, we have 4, 4, minus, we have, let's say, 5. All right, we have 5 over here, suppose. Right. Then we have, let's say, something like 7, 7, and we have 8, 8. Right. So in this array, we see that every element has been repeated twice. There are 2 zeros, there are 2 4s, there are 2 7, there are 2 8s, except for one element. Right. Except for one element, every element is repeated twice. Also, this array is sorted. Right. So it is sorted in ascending order. I hope my voice is clear. All right. Cool. Now the question says you have to find this singlet element. Right? You have to find this element which occurs only one time. So if this was the array that was given to you as input, then you are supposed to return 5. Is the question clear? Yes. So we have been given an array. It is sorted. Every element in the array occurs twice, except for one element. And we have to find that one element that occurs only once. All right. So let us see some approaches. Let us see some approaches. So Piyush has a very nice idea over here. Piyush says, let's try XOR. Right now, we all know the property of XOR. We have seen that in the bit manipulation class. That XOR acts like a lock and key. Lock and key. Right? Basically, if I XOR the entire array, that is supposed to give me that element that occurs only once. Right? That element. I'm supposed to get the correct answer because all these things will cancel. Right? 0 XOR 0 will cancel. 4 XOR 4 will cancel. 7 XOR 7 will cancel. 8 XOR 8 will cancel. And I will be left with 5. So yes, that's a valid approach. That is totally a valid approach. What is the time complexity of this? How much time will this take? How much time will this take? This will take order of n time, right? Because we have to go over each element and check, right? We have to XOR each element, all right? Cool enough. Can we do better? In this, using this XOR thing, are we first of all making use of this property? We know that the array is sorted, right? We know that the array is sorted. So either if we use XOR or if we use a map to keep a count, then we are not really using this sorted property, right? They are going over each element. So let us try to make use of this sorted property and see if we can reduce the time complexity. So this is a valid brute force approach. This is a valid brute force approach. But let us come up with an optimized solution that exploits the property that the array is sorted. Yes, let us see if we have some other approaches. All right. So yes, binary search would be the answer here. But what exactly are you going to do with the binary search? How exactly are you going to search it? All right. So Anurag over here says that let us check the middle element. Let us check the middle element. All right. Let us suppose we have some middle element. And what Anurag is saying is let us compare it with the previous or next element. Right. And then return. Well, let us suppose that this array was a little longer. Right. Let us say that we had 10 over here as well. So when you find the middle element, let me just add the indices. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So what will be the middle element? This will be the middle element. Right. Cool. Now, if this is the middle element, then we compare it with the left and right element, and what exactly do we do? What exactly do we do? So we look at both neighbors. We look at both the neighbors. All right. This is 5 and this is 7. So how does that help us? How does that help us? It doesn't really help us, right? Okay. So what can we do then? Yes. So Dipanshu has a nice idea over here. Let me just show Dipanshu's comment. So Dipanshu says that let us observe one thing. Let us observe one thing, that whenever a new element comes, it always comes at an even position. Right? Whenever a new element comes, it always comes at an even position. Yes? Is that correct? Until and unless that middle element comes. After that, every new element comes at an odd position. Do you all agree? Yes, the first occurrence of any element is on an even position on the left side of this mid and is on an odd position on the right side of this mid. Do you guys observe that? So we are going to use this property. We are going to use this observation to find out what the single occurrence element is. Right? So suppose that we do something like this. We pick, so we have a high and we have a low. Right? So this is 5 and this is 8. We have a low and we have a high. Right? Let us calculate some mid. Right? What we will do is, this mid will be, let us say, A of mid. Right? This A of mid, it might be the first occurrence of this value or it might be the second occurrence of this value. Right? We don't really know. This 7 that we landed on, this could be the first occurrence of 7 or this could be the last occurrence of 7. Right? We don't really know. So what we can do is we can find the first occurrence of 7. Suppose that we landed on this bit. Suppose that we had landed on this bit. Then we can compare it with the previous element and always find the first occurrence. First occurrence of A of mid. Can we do that? Yes. Given a mid number, can we find A of mid and then can we find the first occurrence of A of mid? It will either be that element itself or it will be just the previous element. Right? Cool. Now once we have that, we can check if the index of first occurrence of A of mid, right? If this is even, then what does that mean? That the singlet element lies to the right of me. Right? Whenever I find the first occurrence at an even position, that means that the singlet element lies to the right of me. So I will move right in this case. Right? On the other hand, if this is not the case, if it is odd, then I will move left. Yes? And I will also have to stop at some point. Right? So I can check if A of mid is the first occurrence, and there's only one occurrence, right? So A of mid plus 1 is not equal to A of mid. Then I know that I have found my singlet element because it occurs only once. Does that make sense? Yes. So what will be the very quick pseudocode for this? So we will start with low equals to 0. We will start with high equals to length of, so AR dot length minus 1, right? Then we will loop while low is less than equal to high, right? What will we do? So we will calculate the mid first. So we will say mid equals to low plus high minus low by 2. Yes, we just calculated the mid. Remove the extra string comment, surely. Yes, cool. All right, so we calculate the mid, then we can check. So we will first check. So we know that we have to find the first occurrence of A of mid. Right? How do we find the first occurrence of A of mid? Well, we can check over here. We can check if A of mid minus 1 equals to A of mid. Right? If this is the case, then A of mid is the second occurrence and not the first occurrence. Do you agree? Yes, if A of mid minus 1 is equal to A of mid, then A of mid must be the second occurrence because the previous element is also equal to. In this case, what is the first occurrence? The first occurrence is mid minus 1. Right? In this case, the first occurrence is mid minus 1. Otherwise, the first occurrence is mid itself. Right? All right. So what I can do is over here is I can do mid minus minus. Mid minus minus. And then over here, my mid contains the index of the first occurrence. Now I can check. Now I can check if mid is even or odd. So if mid is even, mod 2 equals to 0, then I have to move towards my right. Yes, I have to move towards my right. How do I move towards the right? I say low equals to mid plus 1. Right? Otherwise, else I move towards the left. I say low equals to, high equals to mid minus 1. I simply say high equals to mid minus 1. Right? Perfect. But that does not really tell me when to stop. Right? That does not really tell me when to stop. So I have to make some other checks as well. Also, there is one more problem over here, that what if this mid turned out to be 0? What if this mid turned out to be 0? Then this a of mid minus 1 will give me an index error. Right? I will be trying to index at a negative value. That is not good. Right? So I have to take care of these things. So first of all, what I can do very quickly over here is I can first confirm this. Right? I can first fix this thing. I can say if mid is greater than 0, right, and a of mid minus 1 is equal to a of mid, right, then do mid minus minus. Then do mid minus minus. So after this point over here at this line, mid will be the first occurrence of a of mid. Right? Mid will be the first occurrence of a of mid. Now if mid is even, we do low plus, we increment the low, else we increment the high. But once again, when do we stop? Once again, when do we stop? So we can check over here. If a of mid plus 1, right? If a of mid plus 1 is actually equal to a of mid, is not equal to a of mid, my bad. So we have the first occurrence of this element, right? We have the first occurrence of this element. And if the next element is not the same, then we have found the correct location, right? Then we have found the correct location. So what I can do over here is, let me just erase this and write it properly. And also we will have to make sure that we check the boundary condition, right? So we will check if mid is less than n minus 1 and a of mid plus 1 is not equal to a of mid, then what do we have? We can just return. We can just return the mid because this is the correct answer. Is that clear? Yes, is the approach clear? So the approach is very simple. The approach is just saying that once you have these elements, all the elements come in pairs, right? All the elements come in pairs. So 0, 1 will come in one pair, then 2, 3, this will be the second pair, then 4, 5, this will be the second pair, until and unless this singlet element comes. Right? This singlet element comes. After that, we will once again have the numbers in pairs. We will once again have the numbers in pairs. So 7, 8 will be there, then 9, 10 will be there, then 11, 12 will be there, 11, 12 will be there, right? Now notice that before this singlet element, every new element occurred at an even index. Right? Every new element occurred at an even index. But after this, every new element occurs at an odd index. Right? So that is just what we are exploiting. All right. Cool. So what will be the time complexity of this approach? What will be the time complexity of this approach? So Abhay says, what if a of mid minus 1 equals to a of mid, then what are we doing with this? Right? So basically what I'm saying is, suppose we landed at this element. Right? Suppose we landed at this element was 7. Right? This and its previous element was 7. So if this is mid, then we are checking if a of mid minus 1, right? Mid minus 1, if that is also the same as 7, if that is also the same as the same element, then move mid to the left, right? Then do mid minus minus. Right? That will make sure that we are always looking at the first occurrence of an element. Right? Cool. So the complexity of this is just order of log n. Right? Why? Because this is a binary search, and at every time we are splitting the array into half. We are reducing the search space by half. Right? Is that clear? Cool. So this was a fairly easy question. Let us move on to a slightly more difficult question. Okay. But before that, let me just give you a brief thing. So when you are finding a number in an array, right? You usually return some index. Right? You usually return some index. Now, what occurrence is this? Which occurrence is this? Which occurrence is this? Basically, what I'm saying is, suppose that I have a sorted array 0, 1, 2, 2, 2, 2, 2, 3, 4, 5, 6. Right? Suppose that I have this sorted array. Right? So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, suppose I want to find the value 2. Right? I want to find the value 2 in this array. Right? So when I'm searching for the value 2, the value 2 occurs at more than one indices. Right? It occurs at all these different indices. So what index should my binary search really return? That is the question. Right? So yesterday we saw that okay, we were returning an arbitrary index. Right? As long as we found the index, it didn't really matter what occurrence we were looking for. Right? So I mean that is perfectly fine. But usually what you will do is you will try to return either the lower bound. You will try to return either the lower bound, right, which is basically the first occurrence, right, or you will return the upper bound, right, which is the last occurrence. Does that make sense? Yes. What if the array is not present? So lower bound is the first occurrence, right? Or if the element is not present, it is the location. It is the location at which I can insert the element. I should insert the element. Insert the element to keep the array sorted. Yes. Similarly, the upper bound is the last occurrence. Right? Is that clear? Yes or no? All right. Cool. So basically, the question now is that if you have been given this, if you have been given an array like this, and I ask you that given a value 2, you have to return both the first occurrence and the last occurrence of this element, then how will you do that? Right? How will you do that? What if lower bound equals to upper bound? Well, that simply means that the element occurs only once. Right, Reshma? That simply means that the element occurs only once. So suppose that the question is that given this array and this value 2, you have to find both the first occurrence and the last occurrence of this array. So basically, if I give you 2, you have to return 2 and you have to return 6. So if the input is this array into, you have to return 2, 6. Right? So how will we do that? Yes, so this is very simple, right? This is very simple. We just have to make sure that we tweak a little bit of those -1s and +1s. Right? We just have to make sure that we tweak a little bit on those -1s and +1s. Right? So usually what we do is we write the loop like this. So while low is less than equal to high, right? And then what do? We say if array of mid, so we have mid calculation over here, we have something over here. We say if array of mid is less than key, right? If array of mid is less than key, then what do? We do lower bound. We do low equals to mid +1. We do low equals to mid +1, right? Otherwise, else if a of mid is greater than key, then we do high equals to mid -1. Mid -1, right? Otherwise, if it is exactly equal, in the last class we saw that we can just return the mid. Right? We can just return the mid because we have found the location. But now we can't just return the mid. Right? Now, if we are looking for the first occurrence, suppose, if we are looking for the first occurrence, can we return the mid arbitrarily? No, because what could happen is when we calculated the mid, suppose we landed at this particular location. Right? We found the two, but we cannot return it, but because this is not the first occurrence. Right? This is not the first occurrence. So how do I ensure that this is the first occurrence? I will have to check over here that first of all, else if mid should either be 0, right? If the mid is equal to 0, then it is my first occurrence, or a of mid -1 should not be equal to a of mid. Should not be equal to a of mid, right? Because if the previous element is equal to the same element, then this mid is not the first occurrence. Does that make sense? Yes or no? All right, that is fair enough. But then what does really happen then? If I write this code, there is a condition remaining, right? There is some condition remaining over here. Yes, there's some else condition remaining over here, right? So what do I really do in that else condition? Well, I have to absorb that else condition. It will have to absorb that else condition somehow. So basically what I need to do is I need to make this thing. I need to make this thing less than or equal to key. Oh, sorry, I have to make this thing greater than or equal to key. Right? Basically, if I have found the element, but it is not the first occurrence, then I will still decrease my height. Right? Suppose I found the element over here, but it is not the first occurrence. The first occurrence occurs over here. Then what should I do? I should move left. I should decrease my height. Is that clear? But once again, the moment I do this, something else happens. Right? Another issue arises. What is that issue? That issue is that if I have this condition in my else if, I will never come into the else. Right? I will never come into the else. So what I will have to do is I will have to move this particular condition on the top. Yes, do you guys agree? Do you guys see the problem? Because if I have less than here and if I have greater than equal to here, then I will never go into that else condition, right? These conditions are exhaustive. Yes? So I will have to move this up. So what will my actual code look like now? What will the correct code look like now? For finding the first occurrence, what I have to do is I have to check first of all. If mid is 0, right? If mid is 0, sorry, if a of mid equals to key, right? If I have found the value and either mid is 0 or a of mid minus 1 is not equal to a of mid, right? Only then, if I found the element and it is the first occurrence, only then can I return the mid. Right? Only then can I return the mid. Otherwise, so let me just put it over here. Right? Otherwise, if a of mid is less than the key, then I have to move up. Right? So I can say low equals to mid plus 1. Right? Otherwise, else, I can simply say high equals to mid minus 1. Right? And this is what my correct code looks like now. This is what my correct while loop looks like now. And this is for the first occurrence. Right? This is for the first occurrence. So this code is incorrect, this code is incorrect. Right? And this is the final correct code for the first occurrence. Can you similarly find the last occurrence? Can you similarly find the last occurrence? Yes or no? Yes, you just have to do it the other way around. Right? You just have to do it the other way around. Basically, you have to make sure that a of mid equals to key and mid is equal to either mid is equal to n minus 1 or a of mid plus 1 is not equal to a of mid. Right? That way we find the last occurrence. And when we are finding the last occurrence, this will be less than equal to, and this will not be, this will be less than equal to, right? This will come in less than equal to over here. So that is very simple. It is very simple to find the first and last occurrence of an element in an array. All right. Now suppose that I have an array which is sorted and has size n, and I tell you that given a value x, you have to count the number of occurrences of x in this array. Then what will we do? If we have to count the number of occurrences in this array, then what will we do? Yes? Jay says instead of two binary searches, can we take a while loop both sides and find first and last occurrence? Yes, totally, Jay. We can totally do that. So let us we are going to explore that via this question. Right? We are going to explore that via this question. Suppose that we have this array. Right? Suppose that we have this array. This element is x, 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 and all the way till this location, it's x. Right? Then this is something else. This is y, this is a. So if I am supposed to find the count of x's, this is a sorted array. If I'm supposed to find the count of x's, then I have two options. Either I can find the first occurrence, then write a while loop, then write a for loop, right? Till the last location of x. Yes or no? I can find the first occurrence and then I can increment the count one by one. I can go one by one and till I reach the last occurrence of s. And I can do a count plus plus. Right? I can do a count plus plus. If I do it this way, then what will be the time complexity? What will be the time complexity of this way? Well, to find the first occurrence, it will take me order of log n time. But after that, to count each of these values, I will have to count one by one again and again. Right? I will have to count one by one again and again. So it will take me order of n time for the counting. In the worst case, right? What if the entire array was full of the same values? Does that make sense? So in this case, this approach will be linear. This approach will be linear. On the other hand, can I do something better? Can I do something better? Let me just clear the banner. Just give me a second. Yes, can we do something better? Right? So what we can do is we can simply find the last occurrence. We can simply run a binary search to find the last occurrence. Right? This is one binary search. And we can also use another binary search, one more binary search, right, to find the first occurrence. Right? And then we can simply return last occurrence minus the first occurrence. Yes? Is that correct? Plus 1. Exactly. Right? Last occurrence minus first occurrence plus 1. All right? And that will basically give us the count of that element. Is that clear? Yes? All right, perfect. Cool. So I hope this is clear, because this is very important. First of all, because whenever you do binary search, you have to understand that you're either going to be finding the last occurrence or the first occurrence. You're not going to be returning any arbitrary occurrence. Also, because in all of the further questions, whenever you are doing binary search, this is going to be very important for us. It is going to be very important for us. So let us look at another question. So suppose that we have been given two sorted arrays. Right? This is a very, very famous question. This question has been asked in all sorts of companies, right? Be it Google, be it Amazon, be it Facebook, be it DirectTime. All the companies have at some point asked these questions, this particular question, and this question is very, very, very frequent, right? And even if you try to search on YouTube, you will find hundreds of videos about this question. So this question is very important. The question is that you have been given two sorted arrays of length n and m respectively, right? So you have been given two sorted arrays. One is of length n, one might be of length m. Right? We don't really know which is larger, which is smaller, and both are sorted. Right? Both are sorted. The question is, we have to find the median of both the arrays combined. Right? We have to find the overall median. Yes. Right. So first of all, let us look at what median is. Right? First of all, let us quickly look at what the median is. So suppose that I give you this particular thing. Suppose that I give you this array 1, 2, 3, 5, 5, 6, 8, 10. Right. Suppose that this is my array, and let me put the indices as well. Right. So 0, 1, 2, 3, 4, 5, 6, 7, 8. Right. So what is the median defined as? What really is the median? So median basically is another term for the middle element. Right? This is a loose definition. This is not the exact definition, but median, you can think of median as the middle element, right, of a particular collection. Now, what do we mean by middle element? If you're talking about a middle element, we should have some sort of order. We should have some sort of ordering, right? Yes. So that is why we are talking about a sorted array. So we are saying if we sort a particular array and then we look at the middle element, So in this case, do I have a middle element? In this case, do I have a middle element? How many elements do I have? I have 9 elements in total, right? I have 9 elements in total from 0 all the way till 8. So what will be my middle element? This will be my middle element. Yes, this will be my middle element. Okay, so basically this is what a median is. Now some of you might ask, all right, well, what if the number of elements is even? Right? What if the number of elements is even? So let us say that I add up 20 over here. Right? Now I have 10 elements. Now I have 10 elements, right? This is no longer 9, this is 10 elements now. Now there's no middle element, right? The middle element does not exist now. There are two middle elements. Both this and this are middle elements. Yes. Then what is the median? Well, in that case, median is the average of both of these. So in this case, this is both 5 and 5. So the median is just 5. On the other hand, let us try to change the values. So let us say this is 9, this is 9, and let us say this was 8. Right? If this was 8, then what will the median be? It will be 5 plus 8 by 2, right? Which is 13 by 2, which is 6.5. All right? Is that clear? Cool. So this is what the median is. Now the question says that you have two arrays. You have two arrays. Let us suppose 0, 0, 1, 3, 5, 8. Right? And you have another array. Let us suppose 4, 5, 6, 7, 8, 9, 20, 30. Right? Let us suppose that we have these two arrays. So let me put the indices very quickly. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7. Right? Now the question is not asking you to find the median of each of these arrays. That is not what is being asked. What is being asked is the median of the overall array, right? Of the overall collection. So basically, if I were to take all these elements, consider all these elements and sort them, right? Consider all these elements and sort them, then what will be the median? So what will be the median in this case? What will be the median in this case? If I write both the arrays in sorted form, I have 0, 0, 1, 3, 4, 5, 5, 6, 7, 8, 8, 9, 20, 30. Right? Yes or no? And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? That's an even number of elements. So the elements, what? The elements 6 and 7. So the median will over here be, the median will be 5.5. Is that clear? Yes or no? Is the question clear? We have been given two arrays and we have to find the overall median of the two arrays. Is the given array sorted? Yes. Both the arrays are individually sorted in ascending order. Right? Both the arrays are individually sorted in ascending order. Right? But I mean, relatively they are not sorted. So it is totally possible that this element is greater than this element. Right? That's totally fine. Okay. There's no relation between the two arrays. It is just that they are individually sorted. Yes. So yes, Shivani has a nice approach over here. Shivani says that let us very quickly merge the two arrays. So where did our comment go? Yes. So Shivani says over here that what we can do is we can merge the two arrays. So when you were doing the merge sort class, you read this merge algorithm, right? Merge algorithm. What did this merge algorithm do? Given two sorted arrays, it created a sorted array. Yes. And how much time did it take? How much time did this merge algorithm take? So if I have total of n plus m elements, if I have n plus m elements, then usually if I just do sorting, right? If I just do sorting in a naive way, then how much time will sorting take me? It will take me n plus m log of n plus m, right? This is how much time sorting will take me. However, if I use the merge algorithm, given that both the arrays are sorted, then I can do it in order of n plus m time. Yes, I can merge the arrays in order of n plus m time. Once I have merged both the arrays, then I can very quickly find the median. Yes, I can very quickly find the median. Right? Find the median. How much time will it take me? If I have merged both these arrays, how much time will it take me to find the median? So suppose that I have merged both the arrays. After that, how much time is it going to take me to find the median? So is it going to take us order of log n time? No, right? So finding a median is just order of 1. You just have to look at A of mid. Right? You just have to look at A of mid. If the number of elements is even, you just have to look at A of mid and A of mid plus 1. Right? So finding the median takes just order of 1 time, provided that I already have a sorted array. Overall, if I do this merge thing, my overall complexity will be order of n plus m to merge the two arrays plus 1 to find the median. Right? To find the median, which is just order of n plus m. Is that clear? Order of n plus m. Well, that is fine. That is good. That is certainly better than the naive approach. Right? So this was the naive approach. So this is certainly better. But we can still do better. So this is not the best approach that we can use. So can we still optimize? Can we come up with an optimized approach now? What other approaches we have? So Ratnesh has a very, very nice question over here. Ratnesh says, can't we just use the median of medians? Median of medians, right? What does Ratnesh mean over here? Let us suppose that we consider these two arrays, right? Let us consider these two arrays separately. What is the median of the first element or of the first array? So this is the first array. What is the median of the first array only? So this array has 6 elements. So the median will be what? So 0, 1, 2, 3, 4, 5, right? It has 6 elements. So the median will be at what index? No. So what Ratnesh is telling us is that let us try to find the median of medians. Right? Let us try to find the median of medians. So first of all, let us consider this particular array, A1. Right? This particular array has how many elements? It has 6 elements from this location to this location. So what will be the median of this particular array? It will be the sum of these two. It will be the average of these two, right? It will be 1 plus 3 by 2, which will just be 2. Right? Similarly, let us calculate the median of this array. Well, how many elements does this array have? This has 8 elements, right? And what is the median of this element or this array? That will be this 3 plus 4, right? This element at 3 and element at 4. So that is 7 plus 8 by 2, which is 7.5, right? Now, Ratnesh is saying, once we have these two medians, can't the final answer simply be the average? Can't the final answer simply be the average of these two? 2 plus 7.5 by 2? Well, no, that is not going to be always true. Right? That is not going to always be true. Is that clear, Ratnesh? Over here, we see that this does not really work. This is 9.5 by 2, which is 4.75. Right? And that is not the answer. The correct answer is 5.5 over here. So it doesn't really work. All right. So let me just remove Ratnesh's comment. So median of medians will not work over here. So we have to do something else. Yes. So what approach can we use? What approach can we use? So now we have to do some sort of a binary search. Right? We can use some sort of a binary search to optimize this solution. Right? So what we are going to basically do is we are going to binary search. There are multiple ways of doing this. Right? We are going to binary search on the index only of. We are going to binary search over the smaller array. Right? So first of all, suppose that this is A1. Suppose that this is A2. Right? So can I assume without loss of generality that A1 is smaller than A2? Can I assume that the length of A1 is smaller than length of A2? Yes. If that is not the case, then I can just swap those arrays. Right? I can call this A1 and this A2 if that is not the case. Right? So let us assume that A1 is the smaller array. So what we are going to do is we are going to binary search in this smaller array. All right. So we will have some low, we will have some high, and we will calculate a mid. All right. Now, once we have this mid, the question is, when will A1 of mid be the correct median, be the answer? What has to be true? What has to be true for A1 of mid to be the correct median? What has to be true? If A of mid is the correct median, then how many elements in A1, how many elements in A1 are less than mid A of mid? How many elements in A1 are less than A1 of mid? When all these elements are less than A1 of mid? Yes or no? Do you agree? And how many elements are greater than this? Well, all these elements are greater than it. Yes. If A1 of mid is actually the median, right? Then what must be true? What must be true? Then half of the elements, right, across both the arrays, half of the elements must be less than it and half of the elements must be greater than it. Yes, half of the elements must be less than it and half of the elements must be greater than it. Cool. So let us check. Let us quickly check. So if A1 of mid is actually the median, then how many elements in A2 should be, or if this is the case, if this is actually the median, then how many elements in A2 should be less than A1 of mid? Right, that is the question. Right, so we know that in A1 there are mid minus 1 elements. Oh, there are mid elements, mid number of elements. So the count of elements in A1 that are less than mid is mid. Right? So the total number of elements that have to be less than A of mid. The total number of elements that has to be less than A of mid should be n plus m by 2. Yes or no? Should be n plus m or plus 1 by 2 actually. Do you guys agree? If I have this total sorted array, and this is actually the median, then half the elements will be less than it and half the elements must be greater than it. So if this many elements are less than it overall, right? And out of these, this many elements were already present in A1. This many elements were already present in A1. Then what is the number of elements that are present in A2 which are smaller than this A of mid? So this many elements were already present in A1. So this must be the number of elements. This must be the number of elements in A2. Number of elements in A2 that are less than mid. A of mid. Yes? Does that make sense? How can you say that length of A1 is equal to mid? No. We are not saying that the length of A1 equals to mid. We are not saying that. We are saying that assume that mid is the correct median. Assume that mid is the correct median. For that to be true, if there are these many elements that are less than it in A1, then how many elements should be less than it in A2? And this is the answer. This is the answer. These many elements should be less than mid in A2. So what we can actually do is, we can start with some low over here. We can start with some high over here, and we can calculate a mid. Now what we can do is, we can put a marker at n plus m plus 1 by 2 minus mid. Right? We can look at this particular index. Right? We will have 4 elements now. We will have 4 elements. We will have one over here, one over here, one element over here, one element over here. Right? So let us call these elements A, B, C, D. Let us call these elements A, B, C, D. A, B, C, D. Right? Now, when is this A of mid? When am I at the correct position? I am at the correct position when A is less than D and B and C is less than B. Right? If this is the case, then this marker, these two markers, they point to my median. Do they not? Yes. Do they not point to the median? Why do they point to the median? Because the number of elements over here and the number of elements over here is equal. Do you guys agree? The number of blue elements is equal to the number of green elements. Yes, and how are they equal? Because I have chosen to be. Right? Because I have used this formula to make sure that I land at the correct spot over here. Does that make sense? Cool. So guys, if this is not clear to you at the moment, we will make sure to basically explain this with an example. Okay, so we will look at a concrete example, but let me first explain the idea. Right? So basically what we have to do is, we have to binary search for a mid such that this property of the median becomes valid. Right? Now look at a concrete example. Let us look at a concrete example to further establish this. Suppose that we have this array 0, 1, 1, 3, 5, 7. All right, and we have another array. Suppose 4, 5, 6, 8, 8, 12, 20, 30. All right, and let us mark the indices 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7. All right. Now, which one is A1 and which one is A2? Which one is the smaller array? This is the smaller array and this is the larger array. Yes, this is the smaller array and this is the larger array. So let us have 2 pointers. Let us have the low pointer and let us have the high pointer. Yes, let us have the low pointer. Let us have the high pointer. Also, what is the value of n? The value of n over here is 6. And what is the value of m? The value of m is 8. Yes, there are 6 elements in the A1 array and there are 8 elements in the A2 array. Yes or no? Cool. So now we have this low and high. What will be the mid? What will be the mid? Mid will be 5 by 2, which will be 2. Yes, mid will be 5 by 2, which will be 2. So this is the midpoint. This is the midpoint. All right. And A1 of mid equals to what? It is 1. Right? Now the question is, how many elements in A1 are less than or equal to A1 of mid? How many elements in A1 are less than or equal to A1 of mid? Well, these many elements, right? This element and this element. Yes, there are 2 elements that are less than or equal to A1 of mid. What is the count of that? Well, the count is simply mid. Right? Mid is the count. Do you agree? Right. Now, if this one was actually the median, then how many elements in this array should be less than 1? Right? In this array, how many elements should be less than 1? Well, total there are 14 elements. Right? Total there are 14 elements. So if there is my median, then half of the elements must be less than it, half of the elements must be greater than it. Right? So basically what I'm saying is 7 elements should be less than or equal to it, 7 elements should be greater than or equal to it. Right? That is the property of my median. Right? Yes or no? Cool. So basically, if this is the case, and 2 of these 7 elements come from A1, right? 2 of the lesser elements come from A1, then how many lesser elements should come from A2? How many of the lesser elements should come from A2? Well, 2 are from A1, so 5 must be from A2. Right? 5 must be from A2. So all these elements should be less than 1. It should be less than this 1. If 1 was the median, then all these elements should be less than 1. Are they less than 1? Are they really less than 1? Yes or no? They are not less than 1, right? So 1 cannot be the median. Does that make sense? Because all these elements, they are not less than 1. So 1 cannot be the median. So my median is too small. In that case, I have to increase my load. Right? I will try to find the median on the right hand side. Is that clear? Is that clear, guys? Yes. So basically what we are saying is that let us say that we are going to have a low and we are going to have a high and we are going to calculate the mid as low plus high by 2. Right? Now, how many elements are less than mid, A of mid in the first array? Well, that is just mid. So how many elements should be less than it in the second array? How many elements should be less than it in the second array? That should be what? That should be n plus m plus 1 by 2 minus mid. Yes, that should be n plus m plus 1 by 2 minus mid. Right? So what we can now do is, so this is the partition. This is basically the partition of A2. Right? Now we can simply check. Now we have 4 elements. We have A1 of mid. We have A1 of mid plus 1. Right? And we have A2 of partition. And we have A2 of partition plus 1. Right? Is that clear? And we can check if this element is less than this element and this element is less than this element, then our partition is valid and we have the correct midpoint. Right? Then our partition is valid and we have the correct midpoint. All right. Why n plus m? Why this plus 1 thing? Well, this is just to make sure that the number of elements number of elements that are on the left are greater than or equal to the number of elements on the right. Right? That is just to make sure that the number of elements on the left are either equal to the number of elements on the right, or they are one more than the number of elements on the right. Okay. So if the number of elements is even, then there will be a mismatch, right? You can't have both the same number of elements on both left and right. So we will have one extra element on the left. Is that clear, guys? Just give me a second. Let us look at some code for this. Okay? Let us look at some code for this. So what will really happen is, let us suppose that we have two arrays. So we have find median, and we have two arrays. We have A1 and we have A2. Right? Let us call this A and B. Let us call this the array A and the array B. All right, for simplicity. Now what we are going to do is, we are going to make sure that array A is smaller. We are going to make sure that array A is smaller. How can we make sure that array A is smaller? How can we make sure that array A is smaller? Well, we can declare it over here, right? So we can say, if the length of A dot length is greater than B dot length, right? If it is in fact larger, then simply swap the values of A and B. Right? So this will ensure that that this particular array is smaller. Right? And notice that this swap is just swapping the pointers. This is just swapping the pointers. This is not actually moving the arrays. This is just swapping the pointers. All right. So now that we have ensured that A is the smaller element, so now what we can do is, we can have a low and we can have a high. Right? So we can say that, all right, low, we can initialize low equals to 0, and we can initialize high equals to what? So what array are we searching over? We are searching over the smaller array. So we will say high equals to A dot length. Right? A dot length, right? And basically, let me also do one thing. Let me also save two values over here, n and m. So let me say, for simplicity, let me say that n equals to A dot length and m equals to B dot length. Right? So we have saved the length or the length in nm. So now my low will be 0 and my high will simply be n. All right. Now I can loop while my low is less than or equal to the high. Right. Now what is the first thing that I should do? The first thing that I should do is I should calculate the mid. Right? I should calculate the mid. And what is the mid? The mid is simply low plus high minus low by 2. Right? Cool. Now this mid is a marker in the first array. This mid is a marker in the first array. What will be my corresponding marker in the second array? As we just saw, that corresponding marker, that is called this partition. Right? This is called this partition. This is going to be n plus m plus 1 by 2 minus mid. Right? Is this clear to everyone? That this will be the partition? Cool. Now what we are going to do is, we are simply going to compare values. Right? We are going to say that if, if A of mid, right? If A of mid is less than or equal to B of partition plus 1. Right? If A of mid is less than or equal to B of partition plus 1, and A of mid plus 1, or basically I can write it the other way. I can write B of partition is less than A of mid plus 1. Right? If this is the case, then what do we have? We have two arrays. Such that this element is smaller than this element, right? And this element is smaller than this element, right? So A is less than B and C is less than D, right? And we know that the number of elements over here is equal to the number of elements over here, right? If this is the case, then I have found my median. Right? So I have found my median over here. So I have found the correct midpoint, right? And I will actually return the median over here. So we will have two cases over there as well. We will look at that. But if that is not the case, then some other case will arise. Right? What case can arise? So either it can be that A is actually greater than B. Right? It can be that A is greater than B, or it could be that C is greater than D. Yes or no? If A is in fact greater than B, let us suppose that I have something like 5 over here and 7 over here, right? And I have something like or let's say 12 over here, and sorry, not 12. Let us say 1 over here and 3 over here, right? So if this element is greater than this 3, then what does that mean? If this element happens to be greater than this 3, then what does that mean? It means that my midpoint is too high. This midpoint is too high, right? I have to move left. Is that clear? Similarly, if that's the opposite thing, right? If I have 5 and 7 over here, right? If I have, let's say, 12 and 15 over here, right? So if this element is greater than this element, right, then my mid should be on the right. Right? This value 7 over here, this is too low. So I should move to the right. Right? So that is what we are going to do over here. We are going to say else if A of mid is greater than B of partition plus 1, then I have to increase my mid. Right? So I have to decrease my mid. Right? So I will say high equals to mid minus 1. Right? Otherwise, I will say low equals to mid plus 1. All right. So this is the main while loop. Now there are some more conditions that arise. Those conditions are basically, let us take one more example. Let us suppose that we have this particular array and we have this particular array. Right? All right. Now we have two conditions. Either the combined length n plus m, either this is even, or n plus m, this is odd. Right? Either this is even or this is odd. If the length is odd, then what will be my median? If the length is odd, then what will be my median? This is A, B, C, D, right? We know the number of elements over here. So the number of blue elements is either equal to number of green elements, or it is equal to green elements plus 1. Right? It is either equal to it or one more than it. Right? So if I found the correct midpoint over here, then what can I say about the median? The median has to be one of these two things. Right? The median has to be one of these two things. Yes or no? Yes or no, guys? And which one of these is the median going to be? Is it going to be A or C? Well, it is going to be the maximum of A comma C. Yes, the median over here is going to be the maximum of A comma C. On the other hand, if the number of elements are even, then what do I have? Well, in that case, what do I have? I have the max of, I want to find the maximum value on the left, right? I want to find the maximum value on the left. So max of A comma C, and I want to find the minimum value on the right. Right? So a min of B comma D, and I want to take the average of those, because the median will be average of two different values over here. Right? I want to take the average of those. Is that clear? Cool. So basically, what do I have to write over here? I have to check if n plus m mod 2, right? If n plus m mod 2 equals to 0, if it is even, then I have to return basically A of max. So basically I have to return max of A of mid comma B of partition, right? The max of these two plus the minimum of A of mid plus 1 comma B of partition minus 1, right? And I have to take the average of these two. So I will add these two up and I will divide by 2. Right? That's a very long line, but I hope that it makes sense. Right? That is the case when my number of elements is even. On the other hand, if the number of elements is odd, then this is very simple. right? Then this is very simple. I simply return. So I can simply return over here the max of A of mid and B of partition. All right. We can simply return the max of A of mid or B of partition. So this will basically be the code for finding the median of two arrays. Now there's one bug over here. Can someone catch that bug? This code is not entirely correct. There is one very, very crucial bug over here. And that bug is basically, let us suppose that I was searching in this array and I was searching in this array. Right? Suppose that while searching this array, either my midpoint became n minus 1, or if my midpoint became 0. Right? Then what do I compare? I don't have anything to compare, right? If my midpoint is this thing, n minus 1, then I can't compare A of mid plus 1 with anything, right? I can't really compare A of mid plus 1 with anything. Yes or no? So for that, to handle that, we can virtually append infinity and minus infinity to the left and right of both the arrays. All right? Yes, exactly. So Jay, even in that case, if the first array is only of size 1, so we will very quickly exhaust the mid. So to handle that situation, to handle that boundary case, we need to add infinity and minus infinity on the right and left side of both the arrays. All right? You don't have to actually append it. You can treat it virtually. Right? You can treat it virtually. Is that clear? Yes, आज कुछ ज़्यादा हो गया. Well, I mean, I would recommend that you actually try and code this up. When you try and code this up, this will. So I understand that you won't be able to. I mean, you will have to get practice on this. You will have to actually try and code this up to properly understand this, right? But I hope that the intuition was clear. The code might not be clear to you, but I hope that the intuition was clear, right? Cool. So now, what will be the time complexity of this overall algorithm? What will be the time complexity of this overall algorithm? Yes. So we are doing a binary search, right? We are doing a binary search over what? We are doing a binary search over the smaller array. Right? We are doing a binary search over the smaller array. So what will be the time complexity? It will be order of min. So it will be order of log of min of n comma n. All right. It will be order of log of min of n comma n. Is that clear? Yes, Himadari, there are a lot of edge cases over here. So we always have to take care of the edge cases. I mean, the solution is very elegant, but the code only becomes difficult because of all the edge cases that you have to handle. All right. Tushar says, how are the corner cases rectified? The corner cases can be rectified by just adding a minus infinity to the left of both the arrays and a plus infinity to the right of both the arrays. All right. Basically, you can say that you have 4 values over here, right? You have 4 values over here. You have A, B, and you have C, D. You have these 4 values over here. Well, what if this midpoint was equal to n minus 1? In that case, if that is the case, then there is no A of mid plus 1, right? There is no A of mid plus 1. So what value should you consider instead of B? There is no B. B does not exist, right? So what value should you consider instead of B? You should consider infinity. Similarly, this value over here, if this is partition and this is partition plus 1, right? If there is no D element over here, then you should consider infinity in its place. Similarly, on the left hand side, if mid is 0, then on the left hand side you should consider minus infinity, and same for partition. Is that clear? So once you actually try to code this, things will start making sense. I don't want to give you the exact code right now, because then it will defeat the purpose of us trying to solve these questions. All right, you actually have to code this yourself, struggle a little with the edge cases, and once you figure this out, things will become clear. All right, cool. So let us move on then to the next question. Right. So the question goes something like this. That we have an unsorted array. that we have an unsorted array, right, of size n, all right, and this array only has positive integers, right? We have an unsorted array of size n, and this array only has positive integers. Now we have been given a value. We have been given a value x, right? And we have to find the largest value of k. The largest value of k such that no subarray of length k has sum greater than or equal to x, or let us say just sum greater than x. Right? So that's a mouthful. Basically, what we are saying is, suppose that we have some array with some elements. Right? We have some array with some elements, and we have been given a number x equals to 10. Right? Let me also give this array. So this is a 1, 5, 6, 2, 0, 1, 3, 5. All right. Let us say this is my array, and I have been given some x equals to, let us make this a little smaller, perhaps x equals to 6. Right? Now we have to find the largest window size. Right? K is the window size. We have to find the largest window size such that in that window there is no window that sums up to greater than 6. Right? There is no window that sums up to greater than 6. So in this case, what will be the answer? Is the question clear? So if I make a window of size 1, this or this or this or this or this or this, then is the sum ever going to be greater than 6? Is the sum ever going to be greater than 6 if I have a window of size 1? No, right? So window of size 1 is valid. Right? Window of size 1 is valid. Size 1 is valid. Right? On the other hand, if I have windows of size 2, let us say this window, right? What is the sum of this window? The sum of this window is 6. Right? So 6 is okay. What is the sum of the next window? 5 plus 6. The sum of this is 11. Well, 11 is greater than 6. Right? 11 is greater than 6. So this window is not okay. And because this window is not okay, the window of size 2 is not valid. Right? Windows of size 2 are not valid. Is that clear? Okay. So we know that a window of size 2 will give me a sum greater than 6. So should I try a window of size 3 or above? Should I try a window of size 3, size 4, size 5? Yes or no? I should not try them, right? There is no point in trying them. Does everyone agree? Yes, because we have to find the largest window such that the sum of any subarray of that size must be less than or equal to this summation value over here. Right? Let us take another example, perhaps. So let us take one more array. So suppose this array is 1, 0, 3, 6, 4, 2, 7, 0. Right? And let us say that x equals to 13. Right? Let us say that x equals to 13. Okay. Now, what is the largest window? What is the largest value of k such that no window of size k has sum greater than 13? Right? So does k equals to 1 work? If I have windows of size 1, then is the sum going to be greater than 13? No, right? So windows of size 1, they all have sum less than 13. Right? So windows of size 1 are valid. Right? Every window of size 1 is valid. So size 1 is valid. This is valid. All right. What about windows of size 2? Well, this has a sum of 1. This has a sum of 3. This has a sum of 9. This has a sum of 10. This is 6. This is 9. This is 7. Right? All the sums were less than or equal to 13. So windows of size 2 are also valid. All right. Let us try increasing the window size further. K equals to 3. All right. Now, what do my windows look like now? My windows are, so this is my window, first window. Right? What is the sum of this? It is 4. Then this is the second window with sum 9. This is the third window. Right? This has sum 13. This is the fourth window. This has sum 12. This is the fifth window. What is the sum of this fifth window? This is still 13. This is the last window. This has sum 9. Right? So still we see that window of size 3 is also valid. Is that clear? Window of size 3 is also valid. All right. Let us try to increase it further. So let us try k equals to 4. All right. Now what is the size of what is the sum of this? That is 10. What is the sum of this? That is 15. Right. The sum of this particular window is 15, and 15 is already greater than 13. 15 is already greater than 13. So windows of size 4 are not valid. Is that clear? And because windows of size 4 are not valid, windows of size 5, windows of size 6 will also not be valid. Right? All these will not be valid. Is that clear? Yes, is that clear? So if this is my array, if this is the input array, and this is the value of x that has been given to you, then what value of k should you return? What value of k should be returned? We should return k equals to 3. Right? We should return k equals to 3 because we have to return the largest size of window, so that no window of that size has sum greater than x. Is the question now clear? Yes, is the question now clear? All right. So how can we approach this particular question? How can we approach this particular question? So guys, whenever you come across a new question, don't try to come up with the optimized approach right away. Right? Come up with the most brute force approach. Right? First, try to solve the question. Once you have solved the question, then you can try to optimize it. Right? Because some solution that works but is slow, some solution is always better than a fast solution that you never find. Right? So having some solution at least is better. Right? So let's think of a brute force approach first. Yes, so what can we do? All right. So let us look at two questions. Suppose I have a guess. Right? Suppose I have a guess for k. All right. Suppose I say that k equals to, let's say, 5. Right? Suppose I have this array and I have been given a value of x, let's say 20, and I am guessing that k equals to 5. Then how can I verify? How can I check it? How can I check it? I have to consider every possible window of size 5. I have to consider every possible window of size 5. So how can I do that? How can I do that? I can either do two nested loops. So I can either say for I equals to 0 all the way till n minus 5 minus 1, right? For j equals to 0 till 5 minus 1, right? And then I can say sum plus equals to a of j, a of I plus j, a of I plus j, right? And initially sum equals to 0, right? So doing this, what will this do? This will give me, so only, sorry, over here. I will have to say sum equals to 0 over here. Sum equals to 0 over here. So basically, after this inner loop, in each iteration of this inner loop, I will have the sum of one window. Right? I will have the sum of one window again and again. So I will have to check if sum is greater than x, then return that window size is invalid, right? K is invalid. Right? After this entire thing is complete, I can say that k is valid. Right? So given a window size k, this is how I can check it. Yes or no? That seems like a very, very difficult approach to do, right? So can we simplify this a little bit? Can we simplify this a little bit? How can we do that? So are you guys aware of prefix sum? Are you guys aware of prefix sum? Suppose that this is my array. Suppose that this is my array, and I want to find the sum from some start location to some end location. Right? If I want to do many queries of such form that find the sum of all these different elements, then how can I do that efficiently? I can calculate the prefix sum. The prefix sum of the array. Right? Let us say that this is the array A, then the prefix sum of array A will be P of A. Yes? Now, if I were to tell you to calculate a of I plus a of I plus 1 or plus a of I plus 2 plus all the way till a of j, then how can you express this in the form of prefix sum? How can you express this in the form of prefix sum? Well, this is simply equal to what? P of j minus P of I minus 1. Yes or no? Is that clear? Yes or no, guys? Alternatively, you can also rewrite this as P of j minus P of I plus A of I. Right? You can also rewrite this as this. They are the same thing. All right. So once I have this prefix sum, if I tell you that find me the size of window of size 5 starting from this location I. Right? If I ask you to find the sum of this window, then how can you do that? How can you do that? You can very simply do what? You can simply do prefix sum of I plus k minus prefix sum of I minus 1. Yes or no? This will give you the sum of this window. Right? And to go over all possible windows, you can just write a loop for I equals to 0 all the way till n. Right? N minus k basically. Yes? So that is the first thing that we can do to make our sliding window calculation a little simpler. Right? We can store the prefix sum. But the thing still comes that, all right, given a value of k, I can check if it is correct or not. But how do I find the value of k? Currently, the approach that I have is start from k equals to 1 and try increasing it. Right? Try increasing it one by one. Right? If I do that, then what will be my time complexity? I will have a loop for k. This will run for order of n time. Right? Then I will have a loop for checking k. This will also run order of n time. So my total time complexity will be order of n squared. Yes. Of course, I also have to consider the complexity of the prefix sum. But calculating the prefix sum is just order of n pre-computation. Right? Pre-computation. So this is actually order of n squared plus n, which is just order of n squared. Right? This is my naive. This is my brute force algorithm. All right. Can we improve this? So Teju says that we can use binary search, right? But what should we binary search over? Teju, what should we really binary search over? Yes, so Prakash says that we can binary search for the value of k. So we are going to binary search for the value of k itself, right? So what is the minimum possible value of k? What is the minimum possible value of k? What is that? What is the minimum possible value of k, guys? It is 0, right? It is 0. Basically, if some a of I itself is greater than x, then I can't have a window even of size 1. Right? In that case, the value of k will be 0. On the other hand, what is the maximum possible value of k? That is n. Right? If I take if the sum of the entire array is still less than x, then that is the maximum possible value of k. So what I have to do is I have to binary search in this search space. So I can say low equals to 0, high equals to n, while low is less than or equal to high, right? I will say mid equals to low plus high by 2, right? All right. Now, once I have the mid, what should I do? I should check window of size mid. All right. I should check window of size mid, and I will have another function over here. Check window. Right? That takes a value of k and returns true or false. Right? This check window is going to do exactly this. So it is going to loop. It is going to say for I equals to 0 all the way till n minus k. Right? If the prefix sum of I plus k minus prefix sum of I minus 1, right? If this is greater than x, if any of this sums is greater than x, then return false. return false. Right? Otherwise, return true. Right? If all these windows are valid, then return true. Right? This is the check window functionality. Is that clear, guys? Cool. So we have a function for check window now. So what can we see over here? What can we see over here? So if I check window of mid and this comes out to be true, if check window of mid comes out to be true, then what can I say? If a window of size k works, then can I return this? If a window of size k works, then can I return that window size as the final answer? Yes or no? No, I cannot. Because yes, this works, but this might not be the largest value that works. I have to find the largest value that works. Right? So if this is the case, then I have to increase my low. So I will say low equals to mid plus 1. Right? Mid plus 1. On the other hand, if this does not work, then I have to decrease my value of k. Right? So else, I will say high equals to mid minus 1. Right? High equals to mid minus 1. Well, when do we stop? When do we stop? So we can either stop when this loop exits, or we can explicitly check. We can explicitly check that k works, but k plus 1 does not work. Right? If that is the case, then we can simply return. Is that clear? Even if you don't do that, that is fine, because this loop will automatically take care of it. Is that clear? So we will return when we find a position of k which works, but the immediate higher position, right? K works, but k plus 1 does not work. That will be our correct answer. Is that clear, guys? So after this loop, after this while loop is over, I can simply return what? What can I return? So this will exit when low will become greater than high. Right? Low will become greater than high. How will it become greater than high? When I would just do low equals to mid plus 1. Okay, so I can just return low over here. Right? I can just return low over here, and that will be my size of the window. All right, cool. So what will be the overall time complexity of this algorithm? What will be the overall time complexity of this algorithm? So let us take this step by step. How much time does check window take? How much time does one function call to check window take? This is simply a for loop. Right? This takes order of n time per call. Right? This takes order of n time per call. Well, what about this thing? This is log n search. Right? This is log n search. But inside this log n search, we are doing this order of n call every time. Right? Inside this log n search, we are doing this order of n call every time. So basically, the time complexity will be order of n times log of n. Yes, order of n times log of n. Well, we also have to consider the prefix something. So this is for the prefix sum. This is for the binary search. Oh, sorry. This is for the binary search, this log n thing. This is for the binary search. And this is for check window. Right? So the overall time complexity is just order of n log n. Is that clear? All right. So let us end the class at this point. Bye-bye. Have a good day. Hello, everyone. So we are back again with another class. All right. So today's topic is once again binary search. So we have been studying binary search in the past 2 lectures. Right. So if you have not watched those past 2 lectures, please go and watch them. So let us continue with some more advanced problems on binary search today. All right. Let me just share my screen. I hope that everyone can see the screen. All right. So let us start with a question that you might have seen earlier. Right. It is a pretty famous question. And you might have seen this in the arrays, 2D arrays class that we already had. Right. But this question is relevant to binary search, so let us quickly see it here once again. Question goes something like this. You have been given a matrix. I mean, this is not that matrix movie thing. This is a matrix. It's a 2D array, right? Now, this matrix can have a certain size. Let us say that the size is n cross m, right? Now, this one property in this matrix that each row and each column is sorted, right? So let us quickly take an example of what one such matrix would look like. So suppose we have 10 over here, 20, 30, 40, 50, right? All right. What other numbers can we choose? So let us suppose that we have 15, 25 perhaps, right? 35, 45, 55. Something else, maybe 27, right? 29, 29, 37, let us say 48, and let us say 60, right? So let us just add quickly one more row. So suppose this is 32, and suppose this is 40, suppose this is 51, suppose this is 60, and suppose this is also 60, right? So we see that in this matrix, every row individually is sorted, right? Every row individually is sorted, and so is every column. So is every column, right? Cool. All right. Now, what is the size of this particular matrix? Well, over here we have 4 rows, so n equals to 4, and m equals to, we have 5 columns, so m equals to 5. So this is a 4 cross 5 matrix, right? Now we have been given an integer. We have also been given an integer k. Right? So k stands for key. We have been given a key, and we have to search this key. We have to search this key within the matrix, and we have to return. We have to basically tell whether the key exists or not. Key exists or not. Fair enough? Yes. All right. So Rahul has a question over here. Rahul, I guess, is talking about the assignments that were given in the last class. Rahul says that 5 questions in 24 hours is kind of aggressive. Right? So Rahul, you do not have to attempt those questions in 24 hours. Right? So unlike when you are enrolled in Skiller Academy, you will have a lot of guidance. You will have mentors. You will have TAs that will be helping you while you're working through the assignments. Right? We will have remedial classes a lot. When we are on YouTube, we just want to give you as many assignments as we can so that you can practice on your own time. Right? So it could be the case that yesterday, after taking the class, you were able to solve 2 of the problems. Now, maybe 5 days later or 10 days later, you want to come back and try it again. Right? So we just want to make sure that you have some new problems that you can still attempt. All right? So do not worry about the time constraint. This assignment is not timed. Right? So feel free to take this assignment whenever you want, how many times you want. So it doesn't really matter. Okay. Just the assignment is just to make sure that you can practice a lot. Perfect. So yes, Shazia is saying that this question has been done in the previous class. So we are going to very quickly move through this question. All right. But this is kind of important for binary search as well. So as you guys already know that this is binary search question. So let us just quickly recap this. All right. Perfect. So this is the question. You have been given a matrix of size n cross n. Each row and each column is individually sorted. Given a key, we have to find whether this key exists in this matrix or not. Yes. Perfect. So what approach do we have? Well, one of the brute force approaches. So whenever we have a new problem, we try to come up with a brute force approach. Brute force approach, right? In a brute force approach, we will not be using any extra information that we are given, right? So what will be the brute force approach? We simply try to linearly, so linear search. If we search through the entire matrix in a linear manner, then how much time is it going to take? What will be the time complexity? Well, how many elements are there? There are total n cross m elements. We are doing a linear search, so it will be the complexity, the amount of time it will take us for linear search will be order of n cross m. All right, but we can optimize, right? We know that each row and each column is individually sorted. Interesting. Well, let us just worry about the rows for now. So we know that because each row is sorted, we can binary search. Inside each row. Is that correct? So if we binary search, let us call this binary search 1. If we binary search inside each row, then how much time is it going to take us for every row? Well, there are m elements. In a row, right? There are n rows and there are m columns. So every row has m different elements. So if we want to binary search among m elements, it will take us log of m time. Right? This is for one row. Now we have to do this for all the rows. How many rows are there? N different rows. So it will take us order of n times log m time. Yes, do you guys agree? On the other hand, if we basically, so this is on the rows. If we binary search number 2 on the columns, right? Then it will be very simple. So it will be m times log of n, because now we are searching within each row, right? We are searching within each column. And how many elements are there in a column? Well, equal to the number of rows. So we can search through a column in log n time, and we have m columns to search through, right? So if we search through just the rows, we will get this complexity. If we search through just the columns, we will get this complexity. The question is, can we do better, right? Now, this might not be obvious from the question itself. We have already tried binary searches, right? We have already tried binary searches, but binary search is not always about this binary property. So just because you are saying binary, that does not mean you always have to split the array into half, right? That is originally what binary search means. But binary search has a more important concept, more important underlying concept. And the concept, as we discussed in the previous classes, is what? The concept is that given a search space, when you make a guess, you are able to eliminate a large part of that search space, right? So every guess allows you to eliminate a large chunk of the search space. Perfect. All right. So that's fair enough. So how can we basically do that? How can we basically do that for this particular question? Well, we can observe. Let us suppose that we are looking at this particular element. Let us just pick any random element, and let us say that we are looking at this particular element, right? Then, if we determine that given our key, right? Let's say that we compare this key with 45. Suppose that the key is less than 45. Right? Suppose that we are looking for an element like 29. 29 is less than 45. Right? Then what can we know from here? This key was less than 45. So can this key be over here? Can this key be in this area? No, right? This key cannot be in this area. Why? Why can it not be in this area? In fact, this particular area, because this key is less than 45, and everything in this area, everything over here in this area is already greater than 45, right? So the key cannot be over here. Similarly, so I can reduce my search space, right? I can reduce my search space by a large chunk. This might be a large chunk. Now, there's one more property that we get. If we move in a particular order, right? Suppose that we are starting from the top right, then we can also eliminate some more rows or some more columns. Right? So we will see that we will be able to eliminate this top row as well. Right? So over here, there's nothing binary over here. Right? We are not really splitting the search space into half. However, what we are able to do is we are still able to eliminate a large chunk of the search space with every guess. Yes, so Dev has a nice name over here. Dev is saying that we can call this staircase search, right? And yes, Tushar also points out one thing. So Tushar says that this has already been discussed in a previous class. So yes, it has been discussed in the array class. However, it is important enough to bring up again in the binary search class, right? Just to stress the point that binary search is not just always about binary search, right? You can still do sort of a binary search on even though you're not splitting the data into half, right? So very quickly, how can we do the search now? Suppose that we start from the top right. So once again, let us assume that the key we are looking for is 29. We are looking for the value 29, and 29 happens to be over here, right? So we better reach this point. But for now, we don't know where the key is. So let us start from the top right. And we will compare 29 with 50. 29 happens to be less than 50. Since 29 is less than 50, what can I eliminate? What part of my matrix can I eliminate? So where can 29 definitely not lie because of this comparison that I have just made? I know that in this particular column is sorted, right? So over here, in all this column, every element is greater than 50, is greater than equal to 50. And we already know that 29 is less than 50. So my key cannot be in this column, right? My key cannot be in this column. So I can eliminate this column. Do you agree? Yes. All right. Once I have eliminated the column, now I have a different matrix, right? I have a different matrix. The matrix exists only up till this column, right? So what is the top right part now? What is the top right part of the matrix? It is this particular cell. All right. Let us compare once again. So we know that 29 is again less than 40. So once again, by the same argument, since this column is sorted, then 29 cannot be in any of these elements because we know that 29 is less than 40. So let us very quickly eliminate this column as well. Perfect. Let us move on to the next top right element. So this is 30. 29 is still less than 30. By the same argument, we will be able to eliminate this particular column. Does that make sense? Yes. Let us continue. So now the top right element is 20. Right? 29 versus 20. What is it? So 29 is greater than 20. Well, now a different argument appears. Let us look at the different argument. So we know that 29 is greater than 20. Right? So if we look at this particular column, if you look at this particular row, we know that everything to the left of 20, everything to the left of 20 over here, in that same row, right, that has to be less than 20. Everything to the left of 20 has to be less than 20 because the row is sorted. So 29 cannot be over here. So what we can now do is we can eliminate this particular row. We can eliminate this particular row. And notice that these columns have already been eliminated. Right? We move on to the next top right element. So 25 is the next top right element. We compare once again. 29 happens to be greater than 25. So by the same argument, we can eliminate this row. Then we move to the next top right element, which is 29. And now we can return yes, we have found 29 and 29 exists in our matrix. Is that clear? Yes. So we are not doing binary search. We are kind of doing a staircase search, right? We are zigzagging around. So in this particular case, we moved along this path. We moved along this path. There's nothing binary about this, but this is still an example of binary search. Is that clear? Cool. Now very quickly, what will be the time complexity? Time complexity of this approach. So we have already seen that linear search takes this much time. Binary search will take either n log n time or m log n time. What about this particular approach? Well, for this approach, we have to go from the top right corner, in the worst case, to the bottom left corner. Right? From the top right corner to the bottom left corner. And the path does not matter. The path does not really matter because in both the cases, we will be covering n different rows and m different columns. Right? So our total path length is equal to n plus m, irrespective of what paths we take. Right? Either we go this way, or we directly go over here, or we maybe take this weird way. Right? All these cases have the same path length of n cross m, m plus n. So the time complexity will be order of n plus m. Is that clear? So this was a repeated question, but this was still very simple and very relevant to binary search. Let us move on now. So we very quickly saw this question. Let us move on to the next question. So Animesh over here says, can we rewrite this? So Animesh says that, okay, perhaps we can also rewrite this as order of max of n comma m. And that is true. That is true. So as we saw in the very first class on time complexity analysis, we saw that we can rewrite this part as max of n comma m, right? Because asymptotically, these complexities will turn out to be the same. They are related by a constant factor of each other. All right. Perfect. Moving on, let us see a more challenging question. So this question is very famously called aggressive curves. Aggressive curves. I think this question was originally from the platform Spodge, right? And this question is very, very common. I mean, this question happens to be one of the favorites for all the companies. So this question has been asked numerous times at Google. This question is still asked very frequently at places like Directile and Amazon. And this is a very, very nice question. Right? The special thing about this question, as you will see, is that it has a very nice solution using dynamic programming as well. But it can also be solved using binary search. Right? So a lot of the times when a student goes to an interview, they are expecting a difficult interview question. Right? A lot of the students are afraid of dynamic programming, even though dynamic programming is pretty easy. Right? So whenever they see this question, the natural approach, the natural idea that comes to their mind is, okay, I can try dynamic programming on this particular question. I mean, of course, dynamic programming solves this question, but binary search solves this, faster now. Okay, so let us quickly see the question. The question goes something like this: that you have n different stalls. You have n different stalls, right? And the stalls. So let us say n is greater than 2. You have n different stalls. So you have more than 2 stalls, and you have C cows. Right? Once again, C is going to be greater than 2. There's one constraint over here that C is less than or equal to n. All right? We have n different stalls and we have C different cows. Now, you have been given the location of these stalls. The location of these stalls has been given to you. So let us say that we have 4 stalls, right? N equals to 4. And the location of these stalls are 1, 2, 5, and 8. All right? Or let us make this n equals to 5. Let us just add one more. And 1 to 5, 7, and 8. What that means is that the first stall, the 0th stall, is at location 1. The first stall is at location 2. The second stall is at location 5. Third stall at location 7. And fourth stall at location 8. Right? So you can try to imagine this, that this is one stall, this is the other stall, this is the third stall, this is the fourth stall, and this is the fifth stall. And if this is at 0 meters, then perhaps this stall is at 2 meters, then this stall is at 5 meters. Right? This stall happens to be at 7 meters, and this stall happens to be at 8 meters. So they are unevenly spaced. Right? These stalls are unevenly spaced. Now we also have C cows. Right? Suppose for this example, we have 3 cows. Right? C equals to 3. So now our task is to place these cows. Our task is to place these cows into the stalls. And one cow can only go in one stall. So I'll just draw the cow as a circle. Right? Cows are not sphericals. So, I mean, if you were a physicist, then you would say that, okay, cow is you would consider a spherical cow in vacuum. Right? But we are not physicists over here. So let us just consider this cow in this particular stall. Right? So I can put this cow installed in many different ways. If I have 3 cows and I have 5 stalls, if I have 5 stalls and I have 3 cows, then very quickly, can someone tell me what is the total number of ways I can put them? What is the total number of ways I can take 3 cows and put them in 5 stalls? Well, that will simply be 5 choose 3. Right? I have to choose 3 stalls out of 5 stalls to put the cows in. And oops. So let us go back. Sorry about that. Right? And if the cows are distinguishable, then I will also have a 3 factorial factor coming. Right? That depends on whether the cows are distinguishable or not. Right? Perfect. So suppose I put the first cow over here in this stall. I put the second cow over here in this stall, and I put the third cow over here in this stall. Right? Now, the cows are aggressive. They want to fight with each other. Right? So we want to maximize the distance between the cows. Right? Now, but there are multiple differences, right? So there's one distance between this cow and this cow. And there's one distance between this cow and this cow. So which distance are we trying to minimize? We are trying to maximize the minimum distance. The minimum distance between any 2 cows. Right? So let us suppose that this distance is 6 and this, so let us not suppose that this is 6. Let us just calculate. So this is at 2 meters and this is at 7 meters. So this distance will be 5 meters. Right? Similarly, this is at 7 meters, this is at 8 meters. So this distance is 1 meter. Right? Now the minimum distance among these two is 1 meter out of 5, and 1 is minimum. So we are saying that this is the minimum distance between 2 cows in this particular arrangement. We want to maximize this distance. We want to place the cows as far apart as possible. All right. And this distance, mind you, this distance is not in terms of the stall number. This distance is in terms of the location of the stall. Right? So we have two things over here. We have the 0th, first, second, third, fourth stall. We have the stall number. That is not what we're talking about. We're talking about the distance in terms of the location of the stall. Is the question clear? Yes. So very quickly, what do you think should the answer for this particular case be? What do you think should the answer for this particular case be? Suppose that this is the arrangement. Suppose that this is the arrangement. I have stalls at 0 meters, 2 meters, 5 meters, 7 meters, and 8 meters. And I have 3 cows. Then where should I put these cows? Where should I ideally put these cows to maximize the distance? Yes, the first cow should go in this particular stall. The first cow should go in this particular stall. All right. Then I can put the second cow in this stall, and I can put the third cow in this stall. Is that clear? Yes. So this will be the ideal case. And what will be the final distance? The distance will be, so the distance between these 2 cows happens to be 5 meters. The distance between these 2 cows happens to be 3 meters. Right? And the minimum of those distances is 3 meters. So we are making sure that the cows are 3 meters apart from each other. Any pair of cows is 3 meters apart from each other. All right. Perfect. So now the question is that given you have been given N, you have been given C, and you have been given the location of these N stalls, right? And you have to tell me what minimum distance can you achieve? Can you achieve by placing the cows as far apart as possible in the different stalls? I hope the question is clear. So basically, if this is the input, you have to give me the output 3 meters, right? You have to give me the output 3. All right. Now, how will we do this? How can we do this? So once again, let us start with a very, very brute force approach. The brute force approach would be to try all possible arrangements of the cows. Right? Try all possible arrangements. So as we just saw, so are the cows distinguishable in this particular case? Does it really matter what the first cow, second cow, and third cow is? No, it does not, right? All that matters is what stalls they are in. So over here, how many possibilities do we have? We have 5 C3 possibilities, right? Or basically, we have N choose C possibilities, where N is the number of stalls and C is the number of cows. So if we do this brute force, we will check each of the possibilities, and then for each possibility, we will find the minimum distance. Right? We will find the minimum distance. So what will be the overall time complexity of this brute force approach? It will be order of N choose C times. So once we have chosen an arrangement, we still have to calculate. So let us say that we have several stalls, and we have chosen to put 1 cow here, 1 cow here, and 1 cow here. That is not done, right? We still have to measure these distances and find the minimum distance between any pair of cows. So that will take us an additional of order of N time, because we have to go through every pair of cows, right? The total of time complexity will be N choose C times N. Well, how big is N choose C? Can someone tell me how big N choose C is in terms of ON complexity? So what polynomial, N to the power what will it approximately be? This is the same as N to the power C, right? N choose C is the same order as N to the power C. Yes, no? Yes, no? Well, not really. Not really, because binomials flip. From the midpoint, the binomials flip. Right? So we are assuming, so this is if C is less than N by 2. Right? C is less than N by 2. So we can rewrite this as, so let us not write this complex expression. Let us just keep this as N choose C times N. And this is in the worst case. In the worst case, this is equal to order of N to the power C times N. Right? Now, if C is very big, if the number of cows is very big, this complexity is perhaps not that big. Right? If there are 10 cows, then you will have to spend N to the power 10 times. That is very, very bad. Right? So let us try to optimize this approach further. Let us try to optimize this. Okay. So those of you who are familiar with dynamic programming, who are familiar with dynamic programming, what would you try to do over here? What would you try to do over here? So anyone who is familiar with dynamic programming would say this, that, all right, I have several stalls and I have some cows. Right? I have several stalls and I have some cows. That is simple, right? For every stall, I have to make a yes, no decision. I have to make a yes, no decision whether to put this cow in there or whether to not put this cow in there. Right? So people would try to apply DP over here and say that, okay, for the first stall, I can choose whether I'm going to put the cow in or I'm not going to put the cow in. Again, for the second stall, I'm going to choose whether to put the cow in or to not put the cow in. Right? And so on and so forth. I will build my choices. And by DP, I can finally find the answer. Well, that is perfectly valid. Right? That is perfectly valid. And if you do that, your complexity will turn out to be order of n squared, which is not bad, right? Which is definitely better than order of n to the power c times n, right? But we can do better. But we can do better. So the moral of this story is that even if you have come up with a solution, it is still worth checking if the solution can be optimized or not. All right. Now let us dive into the most optimized approach, which will be using binary search. Binary search. Perfect. So if we are supposed to use binary search, we have to have a search space. We have to have a search space. We basically have to decide what we are searching for. What are we really searching for over here? Can we search for the location of stalls? Can we search for the location of stalls? That doesn't really make sense, right? Because we have to consider multiple stalls and there are multiple cows. So how it doesn't really make sense to search for the location of a particular stall. What we can search for is the answer itself. We can search for the answer itself, right? So what is the answer over here? The answer is the minimum distance. The answer is the minimum distance. And we are trying to maximize this particular answer. Minimum distance between any two cows. Between two cows. All right. So now that we have figured out what we have to search over, let us quickly discuss the bounds. Let us quickly discuss how large this search space is. So what is the minimum value for this minimum distance? What is the least possible distance that we can achieve? What is the least possible distance when we can achieve? Well, if every stall, if we are forced to put one cow in every stall, and every stall is 1 meter apart, right? So they're just next to each other. They're just next to each other. Then the minimum distance will be just 1. Do you agree? Can the minimum distance be 0? Can the minimum distance be 0? Not really, right? Not really. What is the maximum possible distance that we can achieve? What is the maximum possible distance that we can achieve? Well, this is my first stall. Right? This is my 0th stall is at location 0. All right? And let us say my nth stall, my n minus 1th stall, right? Let us say it is at location, let us say L. All right? And I have to place C cows. I have to place C different cows within this distance. So in the worst case, I mean, even in the best case, doesn't matter how the stalls are arranged, can I achieve, what is the best distance that I can achieve? If all the stalls are equidistant from each other, then I can simply place the cows one in each of them, right? And then basically my distance will be L by C, right? This is the maximum possible distance I can achieve. Can I achieve more than that? Can I possibly get more than that? No, because once I have placed the cows at equidistant locations, if I try to move any cow to the left or right, then the distance between the previous cow or the next cow, this decreases. Right? And we are supposed to consider the minimum distance between any pair of cows. Right? Minimum distance between any pair of cows. So the maximum possible distance that we can achieve possibly is L by C. Right? And what is L over here? L is simply the maximum of the array. Right? So let us consider that these distances are given to us in the array. Right? So this location of the stalls, this has been given to us in array of size n. Right? So this is simply max of A, right? Max of AL for all n. So we now have the bound. We now know that we are supposed to look for a value in this search space. This search space goes from 1 all the way till max of a of I. All right. Now, what else is required for a binary search? What else is required for a binary search? So now that I have a low and a high, I have a low and a high, I will calculate a mid. And this mid is going to be my guess. Okay? This mid is going to be my guess. Now I have to check. Now I have to check several things. I have to check, is the guess perfect? Is the guess valid? And is this the correct answer? That's one thing I have to check. Or I have to check, is the guess too low? Or I have to check, is the guess too high? Because only if I know all these three things, only if I know the answer to these three things, only then can I adjust my search space. Do we agree? Yes, exactly. We need a proposition. Right? If I don't have these three values, I will not be able to figure out in which direction should I move in the search space. All right. So let us quickly look at how we will do that. So suppose that I tell you, suppose that you have been given this array A of n, size n, and this is the location of stalls. Location of stalls. And I am telling you that, okay, you can achieve a distance. You can achieve a distance of, let us say, 5 meters. Right? We have to verify whether this is true or not. So how will we verify that? How can we verify that? Well, this is very simple. Right? This is very simple. What we can do is, so let us suppose that these are the stalls. Right? And let us suppose that this is at location 0, this is at location 5, this is at location 7, location 11, location 16, location 23. Let us suppose this is how the stalls look. So what we can do is, we can place the first cow in here. Right? We can always place the first cow in the first stall. Then we can move on to the next stall and we can check what is the current distance. What is the current distance? Is that distance greater than or equal to 5? Yes, it is, right? So we can safely place the next cow over here because we are trying to achieve a distance of at least 5. We're trying to achieve a distance of at least 5. All right, then we can move on. So when we want to put the third cow, we will come to the next stall and check. Is the distance from the previous cow greater than or equal to 5? So is 7 minus 5 greater than or equal to 5? No, it is not. Right? So we cannot, if we have placed the cow in this stall and we are trying to achieve a distance of 5 meters, then we cannot put the next cow in this stall. All right. What about the next stall? Well, the distance from 5 till 11 is 6. So we can safely place the next cow over here. Does that make sense? Moving on. So we can definitely place the next cow over here. And we can also place the next cow over here. Right? So we can place the cows in this particular manner. Now, if we are able to place all the cows, successfully, right? So remember that we have C cows. Right? If we are able to place all the C cows successfully, then what can we say about this particular guess? What can we say about this particular guess? Is this the correct guess? Not necessarily. Right? This is a valid guess. This is a valid guess. But we are supposed to maximize this guess. Right? So this is a valid guess, but this might not be the maximum value. So we have to continue searching. We have to continue searching with larger values. Right? We have to continue searching with larger values. Suppose that we were not, so if we were able to place it, then we have a valid distance, but the distance can be higher. All right. What is the other possibility? The other possibility is we were not able to place all the cows. Right. For example, suppose over here, let us suppose that my guess distance was, so let me just erase this. So let us say that my guess was that, okay, I can achieve a distance of 10 meters, right? And let us suppose that I had 3 cows to put. So I will try to put the first cow in this first stall. Then I cannot put the second cow in the second stall or in the third stall. I will have to put the second cow over here. Right? I will have to, in this case it will work. So let us just say that we had 4 cows. Let us say that we had 4 cows. So I will put the second cow in this stall. Then I can't put the third cow here. I can put the third cow here. So I will put the third cow over here. Now where do I put this fourth cow? Fourth cow. I cannot possibly put the fourth cow because I have exhausted all my stalls. Right? So in this case, we see that we had a guess of 10 meters distance and we tried to place the 4 cows, but we were not able to place all the 4 cows. We were only able to place 3 cows. So that means that my guess is incorrect. Right? That means that my guess is incorrect. Is there anything else that I know? Is there anything else that I know? I know that my guess is too high. Right? If 10 meters did not work, then 12 meters or 20 meters or 50 meters will also not work. Right? My guess is too high. I have to reduce my guess. Does that make sense, guys? Yes? So what we are essentially doing is, we are saying that let us initialize the low as 1, the high as L by C. So this is maximum of A of I. Right? So maximum of A of A is just the last location. The location of the last term, A of A dot length or n minus 1, A of n minus 1 by the number of cows, C. Then while our low is less than equal to high, right, what we will do is we will calculate a mid. So our guess is the mid, which is simply low plus high minus low by 2. Do you agree? Now we have to verify the guess. Right? So if works, right, if this array for this number of cows, for this value, for this guess, if this works, so we will write this function works. But if this works, then what can we say? If this particular thing works, then what can we say? We can say that, hey, this guess is valid, but it might be too low. Right? This guess is valid, but we could do better. Right? So we have to increase. We have to increase our guess. Right? How will we increase our guess? We will say low equals to mid plus 1. Right? But this guess worked. Right? This guess worked, so we must also save it. This was the largest guess that worked. So let me also save a variable over here, largest working guess. Right? Let me save a variable over here, largest working guess. And this was initialized with, let's say, 0 or minus infinity, whatever you want. And I can say over here that largest working guess equals to maximum of my guess, my mid. So it is maximum of mid, the current guess, comma the largest working guess. All right, I can make sure that whenever I have a valid guess, I save the largest of those valid guesses. Is that clear? On the other hand, if this does not work, then I have to adjust my high. High equals to mid minus 1. Right? And at the end of this loop, when this loop is through, I can simply return whatever maximum guess I have found so far. So largest working guess. Does that make sense, guys? Does this binary search make sense? Yes? We still have to write this function, right? We still have to write this works function. Well, this function is very simple, as we saw. How will this function work? So we have to write works. This will take an array. This will take the number of cows. This will take the number of cows, and it will take a guess. So what will we do? We will start from the location first, right? We will say that the previous stall equals to 0, right? We will place the first cow at location 0. Now, how many cows do we have to place now? So for I goes from 1 till C minus 1. Right? We have already placed the 0th cow. Now we have C minus 1 cows remaining to place. Right? So we will go over each cow, and then what will we do? Right? We will try to place the cow in the next stall. So we will also, let me also save a stall number over here. Right? So stall number is 1. Right? I've already used up the stall number 0. So the current stall number is 1. Okay. So now what can I do is I can try to put the cow in over there. So I can say while the location of the current stall, right? While A of stall minus A of previous stall. Right? If this distance while this distance is less than my guess, while this distance is less than my guess, I cannot really put this cow in the current stall, right? So I must move on to the next stall, stall plus plus. Do you guys agree? While this is true, I will do stall plus plus, right? And finally, I will say that, all right, once I have this, I will say previous stall equals to stall, right? So I will put the cow in there. I will put the cow in there. So this is my loop. Now, of course, this loop might not always work, right? This loop might not always work. Basically, when will it fail? When will it fail? When my stall number has become equal to the size of the array. When I have reached the last stall, but my cows have still not been finished. Right? My cows have still not been finished. So I can put a condition over here. I can very quickly check over here. So instead of directly doing this stall plus plus, let me do a stall plus plus. And now I can check if stall equals to n. If I have already reached the last stall, then I can return false. Return false. Because this guess did not work. I still have some cows to place, but I have exhausted my stalls, right? So I will return false that, hey, this guess does not work. If I can complete this for loop, that means that I was able to place all the C different cows. I was able to successfully place all the C different cows at a minimum distance of guess. So over here, I can return true. Return true. Does that make sense? Does this function, this works function make sense? Yes? Do you guys agree? Perfect. So what will be the time complexity of this? What will be the time complexity of this entire code? Well, let us take it step by step. Right? How much time does the works function take? Given a particular guess, how much time does it take to verify that guess? Well, we have to linearly search through the array of stalls. We have to linearly check the array of stalls. So this works takes order of n time, right? Where n is the number of stalls. Do you agree? Do you guys agree? So, okay, some people will over here say that, okay, you have a while loop. You have a while loop over here, and you have a loop that goes c times over here. So isn't the complexity going to be c times n? Shouldn't the complexity be c times n? Well, no, right? The complexity of this entire for loop is not c times n, because as we see, this variable stall is strictly increasing. Right? This variable stall is never reset. So it can only increase. And the maximum possible value of stall can be up to n. Right? So it is the complexity of this entire nested loop. It is not c times n. It is simply order of n. Is that clear? Yes? Perfect. What about this? What about this binary search? So I think I deleted something from here. Right? What about this binary search? So this binary search takes us how much time? It takes us log of the size of search space. What is the size of search space over here? Is the size of search space n? No. The size of search space is this value over here. Right? This is the size of search space. A of n minus 1 by c. Right? This is the size of search space. So this will be the number of times we will have to do the binary search. And each binary search will take us order of n time. So we can say that the complexity of this is order of log of max of ai, max of ai, so the maximum stall location divided by the number of cows, right? The log of that times n. Is that clear? Yes? Yes or no? Well, C over here. Is that clear, guys? So C is not a constant, so we can't really ignore it. So this will be the final value. This will be the final value. And is this better than n square? So do you guys think that this is better than n square? Well, that will depend. That will depend on how large this A of I is. Right? How large this A of I is. Is that clear? So it might be the case that A of I is 1 trillion. If A of I is a very, very large number, then it might make sense. It might make sense to do this n square solution. But that is going to be extremely, extremely rare. Right? So if n is large, if n is large, then definitely this log value will be much, much small, right? So in general, this approach will work faster. Is it clear? So we saw the brute force approach for this. We saw the brute force approach for this, right? That was order of n to the power c plus 1. Right? Then we saw the DP approach for this. We did not discuss this in detail. We will discuss this maybe later. So this was order of n square. And then we discussed the binary search approach. Binary search approach. And this turned out to be order of log of max of A by C times n. Is that clear? Yes? Any doubts on this particular question? I hope that you will be able to code it. So this is part of the assignments. So please try and code it. You will actually learn a lot when you implement these solutions. Right? And one more thing, please try to make sure that you make the code modular. Right? So just like we have discussed in the class, please define a separate function, right, that will check the guess. You can also write this. You can also write this code over here as well. Right? You can also write this code over here as well. But please do not do that, right? Because then your logic will not be clear. You will be mixing the logic of your binary search with the logic of your checking a guess. Let us keep those two logics separate. Binary search is separate. Checking if a particular guess works or not, that is separate. So please let us do the separation of concerns thing and then keep them in different functions. All right. So let us move on to another question. So this is again fairly challenging question, and this is also a very, very interesting question. Okay. So the question goes something like this: that you have been given an n, you have been given a number n, and this n is a 64-bit number, 64-bit integer, and let us say it is also positive. All right. Let us say it is also positive. Let us also say that n is greater than 2. All right. Let us also say that n is greater than 2. So basically, what values can n take? So n can take a value from, let us say, suppose 3 all the way to 10 to the power 18, perhaps. Right? N can take all these different values. Cool. So now what we are saying is, let us suppose that n written in some base k. N written in some base k. So k can be either 2, in which case we are writing n as a binary number, right? Or k can be ternary, or k can be 3, or k can be 8, in which case we are writing n as an octal number, right? But if we write k in, if we have n in some base k, and if this equals to 1, 1, 1, 1, 1, dot, 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 right? If this is just a string of ones, right? Then we will say that, okay, this k is a good base. Good base. All right? Is that clear? For example, let us say that n equals to 7. All right? N equals to 7. Then what different bases will work? What all different bases can work? So first of all, this k equals to 1 will always work. Right? Yes or no? I can always write something in base 1. Right? A number n in base 1 is just 1, 1, 1, 1, 1 n times. Do you guys agree? Yes? Let us not do that. Let us not do that. Let us ignore this k equals to 1 thing. All right? Let us ignore this k equals to 1 thing. So we are also considering that k is greater than 1. That k is greater than 1. Okay. Now let us try some other base. So 7 written in base 2. What does this look like? What does 7 in base 2 look like? 7 in base 2 is, so this is base 10, my bad. This is base 10. In base 2, if I write it, then it will be 1, 1, 1. Right? So 2 is a good base. 2 is a good base for 7. All right? Are there any other good bases? Are there any other good bases? Yes, no? Well, what happens if we write 7 in base? What happens if we write 7 in base 3? What do we get? So we get 1, then 4 remains, right? Then we will get, so just give me a second. So the last, so 7 is basically equal to 3 to the power 0 plus 3 to the power 1 plus 3 to the power 2. So this is going to be 3 to the power 3. Yes, so this is going to be 2 times 3 to the power 1 plus 1 times 3 to the power 0. Yes, so this is 7. This is 7. So what will 7 look like in base 3? What will 7 look like in base 3? 7 will look like 2, 1 in base 3. Right? 7 is 2, 1 in base 3. So is this a string of ones? Is this a string of ones? No, this is not a string of ones. So 3 is not a good base. 3 is not a good base. All right, let us continue. Let us continue. So we can check the base 4, we can check the base 5. That is also not going to work. There is some other base that is going to work. Right? 7 in base 7 is also equal to, in base 6, this is going to be equal to 1, 1. Right? In base 6, this is also going to be equal to 1, 1. Do you guys agree? Yes. In fact, if I have any n in base 10, then this is equal to 1, 1 in base n minus 1. Yes or no? 1, 1 in base n minus 1, that is simply n. Why is that? Because see, 1, 1 in base n minus 1, this is equal to n minus 1 to the power 0 times 1 plus n minus 1 to the power 1 times 1. Right? And that is equal to what? N minus 1 plus 1, which is just n. Right? So any number n that I have, I can always write in one less base and get a string of ones. So 7 equals to 1, 1 in base 6. Right? 13 equals to 1, 1 in base 12, and so on. Do you guys agree? So n minus 1 is always a good base. Right? N minus 1 is always a valid base. So this is also a good base. Right? Good. Now the question once again is that you have been given a value of n, right, such that n is greater than equal to 3 and n is less than or equal to 10 to the power 18, suppose. So it is a 64-bit integer, positive integer. We have to find the smallest base, smallest good base. All right, so we found several different good bases, right? For 7, we found that 2 works. So we found that 2 works, 3 does not work, 4 does not work, 5 does not work, 6 works. Right? That is what we found for 7. So what will be the smallest good base for 7? What will be the smallest good base for 7? It will be 2. Right? It will be 2. So smallest good base. So for example, if n equals to 7, then the answer will be 2. And why 2? Why not 1? Because 1 works for everything. Right? If we allow 1, then for every number the answer will just be 1. Because base 1 works for everything. Is that clear? So we are saying that the smallest good base, let us call this k, is greater than or equal to 2. So this is the question. I hope the question is clear. Given an integer n, return the smallest good base. For example, if your value is 7, then you are supposed to return the value 2. All right. So what can our approach be over here? What can our approach be over here? Let us start with the most brute force approach. Brute force approach. What will the brute force approach look like? In the brute force approach, we can simply check all the possible options. Right? We can simply check all the possible options. So we can go from base k equals to 2 all the way till n minus 1. Right? We can check all these different values. Now, once we have a base, we have to convert n into that base, right? Base k, and check if this is a string of ones. If this is a string of ones. Well, how much time does it take to convert a number into base k? How much time does it take to convert a number into base k? Can someone quickly tell me that? It will take me log of n time base k. It will take me log n time with a base k. This is how much time it will take me to convert a number. Why? Because I have to repeatedly divide that number by k. Right? I will say that, okay, the last digit equals to n mod k. Then I will divide the number. Right? I will say n by equals to k. N by equals to k. This is not or this is a simple division. Right? Then I will say d1 equals to once again n mod k. And then I will again say n equals to n by k. Right? And this will be in a loop. This will basically be in a loop. That is how I convert the base. So it will take me log of n time base k. All right. So what is the total time complexity over here? I have these many bases to check. I have these many bases to check, and it takes this much time to check each base. So it will be order of n times log n. Right? So my brute force approach takes me order of n times log n time. Is that clear? Yes? Now this is not very good, right? This is not very good. If my n is, let us say, 10 to the power 18, then it will take me 10 to the power 18 steps. That is definitely not possible. I cannot do 10 to the power 18 steps on any computer. Yes? So we should better come up with a faster solution. We should try to come up with a faster solution. Okay. So what can we do over here? What is the first thing that comes to your mind? What is the first thing that comes to your mind? The first thing, since we have been doing binary search, might be that, okay, let me make a guess. Let me guess base B. Let me guess base B and check if the guess is valid or not. Yes, that is what comes to your mind. That let us take a base B, let us consider a random base B, and let us check if it is valid or not. Well, this is not going to work for this case. This is not going to work for this case. Why? Suppose that my number was 7. I checked the base 2. I checked the base 2 and it worked. What does that tell me? Does that really tell me anything? That tells me that 2 works. That tells me that 2 works, but that is not enough, right? I also have to understand. Is my guess too low or is my guess too high? Yes. Just because 2 works, that does not mean that my guess is too low or that my guess is too high. Do you agree? It might be the case that 7 of 6 still works, right? So for this, for the base 7, 7 of 2 works, 7 of 3 does not work, 7 of 4 does not work, 7 of 5 does not work, 7 of 6 works. This works. So suppose you make a guess. Suppose you make a guess. There is a valid value to the right of it as well as to the left of it, and you do not know in which direction you have to go. So if it turns out to be false, if you figure out that, okay, the guess did not work. So are you supposed to increase the base or are you supposed to decrease the base? Are you supposed to increase the low or are you supposed to decrease the high? Does that make sense? We have no way of knowing in which direction should we move our guess. So we cannot do the binary search over base. Does that make sense? Because once again, if we go back to the first class, if this is our search space, then we need to come up with a proposition such that all the answers here are yeses and all the answers here are no's, so that we can search binary search for this midpoint. For this particular thing, the answer over here is yes. The answer over here is yes. The answer over here is yes. But all the other numbers can be no. Right? We don't really know. It can be randomly. It can be in a random manner. So binary search is not going to work for this proposition. Is that clear? Yes. It seems very, very seductive to try to apply binary search over here. I have a base. I can verify if it is a valid base or not. So let me just binary search over the base. That is not going to work, unfortunately. So what else can we do? What else can we do? So we have to look at the question from a different perspective over here. We have to look at the question from a different perspective over here. So let us suppose that we are talking in base B. Right? Suppose we are talking about in base K. Suppose base K. Right? Then if basically my number n in base K is a string of ones, I already know what the string of ones is, right? I can construct this string of ones, right? I know that this is in base K. I know that this is a string of ones. The only thing I don't know is how many ones there are over here. Yes, how many ones there are over here. Let us call this value I. Does that make sense? So n written in base 2 will have 3 ones. Right? N written in base 6 will have 2 ones. Right? So instead of trying to binary search over the value of k, let me try to binary search over the value of I. Okay? Let me try to binary search over the value of I. But let me first establish a relation between these two. So if n in base k is a string of ones in base k, so n is equal to a string of ones in base k, right? And let us say that there are I ones over here. Then what can I say? Is there any relationship between n and k? Is there any relationship between n and k? Yes, there is, right? What is the relationship? I know that 1 times k to the power 0 plus 1 times k to the power 1 plus 1 times k to the power 2 plus all the way till 1 times k to the power I, right? This thing equals to n, right? If I have this number in base k, then this is the expansion of it, and I know that this must be equal to n, right? What can I say? N equals to summation of k to the power I, or k to the power, let's say, x, for x equals to 0 till I, right? So this is a, what is this? This is a geometric progression. This is a GP. So can I write the sum of it? The sum of it is simply k to the power I plus 1 minus 1 by what? By k minus 1, right? So the sum of a GP, summation of r to the power I, for I equals to 0 till k, this is equal to what? 0 till n. This is equal to r to the power n plus 1 minus r to the power 0 by r minus 1, right? Yes. So just notice that there is this denominator over here, right? You can't simply say that the denominator is 1, right, Shazia? So Shazia, there's a small mistake in your formula. You have to make sure that this denominator is also dependent on k, right? So we can say that n equals to k to the power I plus 1 minus 1 by k minus 1. This is the relation that we have established between n, k, and I. Now I know that I cannot really binary search over k, but that's okay. Let me binary search over I. Right? Let me binary search over the value of I. All right. Now let us suppose that I have I1s over here. Right? Let us say that I have I1s over here. All right, and this is equal to n. Right? This is equal to n. Then what if I'm trying to minimize? So remember that I have to find the smallest good base. Right? I'm trying to minimize the value of k. So what am I trying to do with the value of I? If, see, n is my constant. Right? N is my constant. I'm trying to minimize the value of k. So what am I doing with I? I'm trying to maximize the value of I. Right? I'm trying to maximize the value of I. Do you agree? Yes or no? Right? Yes or no, guys? So that is one thing we know. Perfect. We know that we are trying to maximize the value of I. All right. Let us also consider what is the search space of I. Search space of I. What is the search space of I? So I can be, so this can be, so let us suppose that I write n in base 2, right? This is the smallest base that I can possibly have. So that will give me the largest possible string of ones. How many ones will I get when I write n in base 2? I know that n is a 64-bit integer. Right? So the maximum search space, the maximum value of I can be 64. Right? So I can have all the way from 2 all the way to 64 ones in my string. All right. Now, once again, the problem over here arises. If I know that this sequence of I works, does that tell me anything about this sequence of I or about this sequence of I? Does that tell me anything about this sequence of I or this sequence of I? It does not. Right? I know that I have to maximize the number of ones. But if this works or if this does not work, it doesn't tell me whether I should increase it or decrease it. So I cannot really binary search. Over the value of I either. That's sad. But how many i's can there be? We just established that the maximum possible value of I can be 64. On the other hand, when we were talking about k, we established that the maximum possible value of k can be up to n minus 1. So what would be the other search over? Should we search over k or should we search over I? This can be up till n minus 1. This can only be up till 64. Right? So this is much better, right? Do you guys agree? Searching over I is much better. So I can simply check for every possible I. For I goes from 2 till 64. Let me check for all the possible. Strings of 1. Right? Let me check all the possible strings of 1. Now what I will check? Now I will see whether n can be written in the form of 1, 1, 1, 1, 1, I1s to the base k. Whether I will try to see whether any such base k exists, that will give me this. Does that make sense? I can go over every I. Yes, but how do I find this k now? How do I find this k? I know the value of, I know the relationship between these two, right? I know the relationship between all these numbers. I know that n equals to k to the power I plus 1, right? N equals to k to the power I plus 1 minus 1 by k minus 1. I know this relationship. So now, if I have the value of I, and if I have the value of n, can I find the value of k? Can I find the value of k? Yes. How will I find the value of k? That is difficult, right? I will have to manipulate the formula. Right? If I want to find the value of k, I will have to manipulate the formula. I will have to extract k out of it. So can someone solve this equation for me very quickly? Can someone solve this equation for me very quickly? Well, you can't really do that, right? Because this k, this I might be a very, very large number, right? And you don't, so for higher degree polynomials, you don't always have a way of solving an equation. So you can always solve a quadratic. If you have a quadratic equation, you can always solve it. If you have a cubic equation, you can always solve it, right? But for higher equations, I'm not sure for the fourth power, but I know that from fifth power and above, right, it is not always solvable. It is not always possible to solve a higher degree polynomial. All right. So this equation might not be solvable. So what can we do? Do we have to give up? No. Here is where we can binary search. We can binary search for the value of k. Right? We can try to plug in the value of k and try to binary search for an answer that works. Is that clear? So what we will do now is we now have to find a k that works. What is the maximum possible value of k? The maximum possible value of k, so the minimum possible value of k is 2. The high maximum possible value is n minus 1. And now I can binary search over this value of k. I just have to find one k that works. I can binary search for k which satisfies this equation, which satisfies the equation n equals to k to the power I plus 1 minus 1 by k minus 1. Is that clear? So just like in the first class, we tried to binary search. So we did not do it in the class, but it was part of your assignment. Right? So in the assignment, you had to do a binary search for the square root of a particular number. Right? For the square root of a particular number. Yes, so n minus 1. Right? This is n minus 1. Right? So we can binary search over the value of k. Is that clear? So how much time will this binary search take? How much time will the binary search for k take? This is my search space. Right? This is my search space. My search space has size of n. And I'm doing a binary search, so it will take me log n time. Log n time to binary search for a value of k. But I have to do this 64 times. I have to do this for all values of I. So this will be times 64. So the overall time complexity of my approach will just be 64 times log base 2 of n, which will just be log n. That is amazing. Right? We went from an n log n solution. We went from an n log n. What happened over here? N log n brute force, and we reduced it down to a constant times log n. Is that clear? Yes. So even though the question does not directly involve binary search, there is still an involvement of binary search. And the moral of this particular question is that be very, very careful. Be very, very careful. For binary search, you just don't have to make and verify a guess. You also have to understand, given the guess, if that guess worked, then is the guess too high or too low? Right? If the guess worked or if it did not work, this is not enough. You also have to establish, is the guess too high or too low? Because if you cannot do that, then you will not be able to binary search for your answer. Is that clear? Perfect. Ankush has asked a very good question. Ankush is saying, how can we know whether binary search will be applicable for this particular question? Now, that is a very, very tricky question. So basically, the most common answer you will find to this is practice. Right? The most common answer that you will find to it is that, okay, if you just practice, then practice will make you perfect. You will get to know which approach you have to apply. But that is not the entire truth. There is a separate way as well. So there's a systematic way. There's a systematic way of approaching problems. Right? Now, unfortunately, I cannot teach this systematic way in a YouTube class, right? It cannot be taught in a 1-hour class. So the entire the scalar curriculum of DSM algorithms is based on, tries to teach you this systematic way. Right? So that whenever you get a new problem, you can just apply the systematic algorithm and try to come up with a solution for that. Okay, that is what we teach in the scalar classes. All right. So, I mean, we could cover this, but this is going to take a very, very long time. We will have to take a very long class. We'll have to consider all the DS algo things, and then we will have to tell you the approach. Perfect. So that is it for today's class. Let us end the lecture now, and see you then. So once again, you can find the assignment set in the video description. Please make sure that you attempt the problem set. Okay then. Have a nice day, guys.